Hi, good morning. I'm Dr. Carol Iddens. I'm the director of REACTS. Very nice to see you all this morning and or afternoon or evening, as Jill mentioned, because yes, we're seeing Belgium, Germany, Saudi, all over the place. So we really appreciate you joining in with us today. Our thanks to ACMT and everyone who put all of this together. There's a lot of work that goes into it, and we appreciate it very much. I'm going to go ahead and let my co-presenters introduce themselves in just a second. All I want to really get across to you, we're not doing a formal introduction, but REACTS for short, we are an emergency medical response asset for the United States Department of Energy, National Nuclear Security Administration. And we've been in existence since 1976. We've been on call 24/7 since then. And believe it or not, you would think we have seen it all in this number of years, but we always get some nice surprises or not so nice surprises, as the case may be. We very much appreciate working with our toxicology colleagues. We have a deep and long professional relationship and even personal friendships as well. So let me go ahead and let our staff hop on and do a quick introduction of themselves. Dylan, do you want to go ahead and kick off there?
I'll start it all, I guess. My name is Dylan Vogt. I'm one of the health physicists or one of the HPs on REACT staff. That basically means I kind of handle the more physical side of everything, where the physics meets the biology, and then kind of kick all that information over to our docs and our RNs. So my lectures today will kind of handle that more physical side as we kind of look at how it's going to affect biology. Thank you, Dr. Iddens.
Oh, certainly. And Dr. Kiernan.
Sorry. Good morning. I'm, I'm Emily Kiernan. I am a emergency medicine physician and medical toxicologist, and also work at REACTS. Thanks, Dr. Erdens.
Oh, certainly. Thank you for being with us today. And you'll be on tomorrow as well. And last but certainly not least, Megan, would you mind doing your introduction?
Sure. Hi, everyone. I'm Megan Diefenthaler. I'm also one of the health physicists here. So you'll hear a lot of math and numbers from me today.
Great, thank you. So that's our staff for today. We're always happy to answer questions. We'll do our best to track the Q&A and the chat blocks. If it takes a while for you to get your answer, please just bear with us. We do not have a large panel today, but that is about it. And I want to go ahead and turn this back over to Dylan. And Dana, if you're ready, we'll just get started a few minutes early for once, right?
Sounds good, Dr.
All right, Dylan, it's all yours.
I'm first today. It's okay.
Sorry about that, Megan.
All good. All right. All right, just making sure. Can everyone see my screen?
Yes,
all right,
looks
okay,
good.
thank you. So hello again. Like I said, I'm Megan Diefenthaler. I'm one of the health physicists here at REACTS. And to kind of get everyone on an equal ground when we start out this series, we kind of like to start with what is radiation? How does it interact with the body? What are some basic principles of how to protect yourself from radiation? And so some of this might be redundant for people that work more with radiation, but it is kind of a good refresher. So I have nothing financial to disclose with this lecture. The learning objectives today are going to be to discuss basic radiation terminology, describe the various types of ionizing radiation, whether it's a particle or a wave. I'll go into the nuances of those things, explaining the difference between irradiation and contamination, because that does affect how you would want to treat a patient. And then lastly, describing the radiation protection principles of time, distance, and shielding. Most of the public gets their perception of risk of radiation based on what they see in the media. A lot of people have watched HBO's Chernobyl series, or you've seen the new Oppenheimer movie. In earlier generations, you grew up with the Marvel comics, so you're exposed to gamma rays and become the Hulk, or you're bitten by a radioactive spider and become Spider-Man. I wish these things were true, but unfortunately they're not. But this just kind of goes to show that people think that radiation is scary and it's going to mutate you or it's going to immediately kill you no matter what happens. And that's just not true. There are ways to protect yourself from radiation. It can be used for good. You experience it every day. And so we just kind of hope to emphasize that throughout the day. And like I said, we're exposed to radiation every day. A lot of people think of bananas when they think of a radioactive food, and that's true. It has a relatively high amount of potassium-40 compared to other foods. But Brazil nuts are actually the most radioactive food per unit mass. They have a really high level of radioactive polonium and selenium in them. But again, it's not a dangerous level. You'd have to eat, I think, like 6 million kilograms or something of Brazil nuts to reach any sort of high level of radiation. And I think you're going to have a lot more issues if you eat 6,000 kilograms of Brazil nuts before you hit that radiation threshold. There's also atmospheric radiation. So there's radioactive nitrogen and oxygen and other noble gases in the air that you breathe in every day. But again, you breathe it in, you breathe it out. And it's just part of living on Earth. That's going to be, you're going to encounter it. There's also terrestrial radiation. So normally areas that have mountains, so like us in Tennessee, or if you live in Colorado, at least in the US, these areas typically have really high radon levels. Radon is a decay product from uranium and thorium, which are also naturally found in the soil. The problem with radon is it's a gas, and so it has a tendency to seep up from the soil and get collected in areas like basements that are built into the ground. So my husband is a medical physicist and I'm a health physicist. So when we bought our house here in Tennessee, we thought it would be a fun experiment to get a radon detector and stick it in the basement. And it's a good thing we did, because the EPA's limit for radon is 4 picocuries per liter, and our basement was at like 15 picocuries per liter. So then we had to work and get radon mitigation, which essentially is putting a fan and a sump pump underneath the house. And so it blows the radon out of the ground before it even reaches the basement. Some other ways to deal with that would be like sealing cracks or making sure that all windows are closed, just things like that. But that was a fun little radiation experiment we got to do. There's also cosmic radiation. This comes from stars being born and formed and dying. They're releasing subatomic particles as this process occurs, typically releasing things like electrons and muons, pions, small subatomic particles. And the higher that you are in elevation, the more exposure you have to cosmic radiation, because you have less atmosphere between yourself. So places like Colorado in the US kind of are a double whammy with background exposure, because you have the young Rocky Mountains and you also are at a really high elevation. So you have naturally just a higher background. These particles coming from the stars, when they interact with the atmosphere, are actually what causes the northern lights. So all the pink and green lights that you see are caused by cosmic radiation. And lastly, this is more like a fun fact, Grand Central Station has a relatively high background because it's made of granite, and granite has high levels of thorium in it. And so when you're in Grand Central Station, again, like all these, it's not a high level of radiation, but it's just a naturally higher background than you would experience somewhere else. So in Oak Ridge, we are very fond of the Manhattan Project because it was kind of born here. And during the Manhattan Project, that's when health physics as a field was kind of created. And it's named health physics, and it's kind of in an ambiguous way, because when you say, I'm a health physicist, that isn't, nothing about that says I work with radiation or I work in radiation protection. And so during the Manhattan Project, Oak Ridge created all of these posters to kind of promote health physics and promote a safety culture around radiation. And so this is one of my favorites. It says, radiation need not be feared, but it must command your respect. And that's kind of what we hope that you take away today. that radiation inherently is dangerous, but as long as you understand the nuances of how to protect yourself and how to treat patients that have been contaminated, it can be something that you can handle safely. And people have been doing it for years now. So now kind of getting into the atom and radioactivity. Again, this might be a little bit basic for some people, but it's always a good reminder, and maybe you learn something new as well. So this is the basic structure of an atom. You have your positive nucleus made of positive protons and neutrally charged neutrons. These subatomic particles are about the same size in mass. And then you have the negative electron orbitals surrounding that nucleus. At REACS, what we deal with is ionizing radiation, and there's a difference between ionizing and non-ionizing. So with non-ionizing, you're dealing with things like microwaves or radio waves, things that aren't going to cause biological damage to the DNA. With ionizing radiation, there's enough energy to strip electrons out of this orbital, and the electrons can go on to further damage DNA through direct or indirect processes. There's different types of ionizing radiation. So again, just energy and particles being emitted from the nucleus of an atom. There's subatomic particles. So these are alpha particles, beta particles, and neutrons. And then we have electromagnetic waves. We have either gamma rays or X-rays, and these are just forms of energy that are being emitted as a wave versus a particle. Gamma rays come from the nucleus, and X-rays come from the electron orbitals, but energetically they can be the same. So some people think that gamma rays have higher energy than X-rays, and in some instances that could be true, but really the difference comes from where they come in the atom. The process of radioactive decay is simply a radioactive atom, so an unstable atom. It has too much energy, it has too much mass, transforming into a stable atom. So this atom has an equal number of protons and neutrons, or it has the right amount of energy. So we call our original atom, the radioactive one, is called the parent. And then you get your decay product, your progeny, or your daughter is whatever atom comes out of that original decay process. Here, for example, I have iodine-131, undergoes beta decay and becomes stable xenon-131. In the medical field, iodine-131 is used a lot to treat hyperthyroidism or thyroid cancer because the thyroid naturally uptakes iodine. So if you are injected with iodine-131, your body doesn't see it as radioactive iodine, it sees it as iodine. So it will naturally accumulate in the thyroid. And I'll go more into that and how that works in a little bit. So with radioactive decay, you can have single-step radioactive decay, where you have one radioactive atom, it undergoes one decay process and then becomes stable. So here we have cobalt-60, undergoes beta decay, and then becomes stable nickel-60. Cobalt-60 is used a lot for external beam therapy for cancer treatments. It's kind of getting phased out, but it is still seen around the world. And then we have serial radioactive decay. And this is where you have one radioactive atom, and it undergoes a decay process, becomes another radioactive atom, undergoes another decay, becomes radioactive, and continues on until it becomes stable. So in this image, I have radon-222. This is that radon gas I was talking about earlier. And you can see it goes from radon to polonium to lead to bismuth, on and on until it becomes stable lead. And this is kind of why radon is such a huge problem. One is because it's a gas, so you're going to breathe it in, but then you breathe it back out. But any remaining radon in your lungs is going to start going through this decay process into stable lead. That's why radon is such a huge issue. So that's the difference between single step and then serial radioactive decay. But ultimately, you're working towards a stable atom. So going into more of the nuances of the decay processes, there's alpha decay. This is the emission of an alpha particle, which is essentially a helium nucleus. So it's 2 protons and 2 neutrons. So decay-wise, this is a very large particle. It's the biggest particle that can really decay. So you can think of alpha particles kind of like a sumo wrestler. If you have a sumo wrestler running at a bunch of people, they're going to hit one person and essentially lose all their energy and fall over. So alpha particles, thankfully, are easily stopped. Here in this image, I have americium-241. It undergoes alpha decay and becomes stable neptunium-237. Chances are all of you have handled americium-241 because it is found in smoke detectors. So the way that a smoke detector works is you have a small americium-241 source, and it's emitting alpha particles constantly. Those alpha particles are reaching a radiation detector, and as long as the radiation detector sees the americium, so essentially the alpha particles, it's happy, and the circuit will not alarm. If something like smoke or hairspray or some other sort of dusty material gets in between the americium and the detector, this will cause the alarm to trip. And the reason that you can use americium-241 is that it doesn't travel very far in air. So it's easily blocked by these particles, and it's blocked by the plastic casing that the smoke detector holds it. So it's not an exposure hazard to anyone that handles it, or if it's in your house. So they are safe to use. Like I said, alpha particles are a helium nucleus, so 2 protons, 2 neutrons, relatively large compared to the other decay modes that we'll talk about. Alpha particles are not an external hazard, like I'd mentioned. They're blocked by the dead layer of your skin. They can be blocked by a sheet of paper. They're blocked by plastic. So they're very easy to shield externally. The problem is if you inhale them or ingest them, or you have a wound with alpha contamination inside of it, internally, alphas are kind of like little wrecking balls. There's no dead layer of skin inside your body, and so there's nothing really to block them from causing that biological damage. And I'll talk more about how much more biologically damaging they are in just a minute. But if you have internal alpha contamination, that's a much bigger problem typically than if you have internal beta or gamma contamination. With beta decay, the beta particle is much, much smaller than the alpha particle. It's essentially an electron that's ejected from the nucleus of an atom. So here we have hydrogen-3 or tritium. It emits a beta particle and then becomes stable helium-3. Because beta particles are so much smaller, they can penetrate the dead layer of skin. They can go about 10 millimeters or so in skin. They are also an internal hazard, much like alpha particles, a little bit less so, but still very damaging. They can cause what we call beta burns, where it's not like a thermal burn, but it kind of manifests in the same way, where there's that skin reddening, just because they can penetrate that dead layer of skin. Beta particles can be blocked by plastic, but they can travel through paper. So you need just a little bit more shielding to protect yourself from any sort of beta exposure that you might have. With gamma rays and X-rays, these are not particles, they're waves. And so they can penetrate through the body. They can go through plastic, they can go through paper, just because they don't have that particle component. It's just a wave. So if you think of like a microwave traveling through your body, gamma rays essentially do the same thing, but because that frequency is so much higher, they will cause biological damage, whereas something like a microwave would not. So it's really just energy being emitted from the nucleus if it's in an excited state. So here we have sodium-22 emits a positron, but that sodium-22 still has too much energy in the nucleus, so it emits a gamma wave and then it becomes stable neon-22. And lastly, we have neutrons. Neutrons are kind of different because they are a particle, but they don't have a charge. So this makes them biologically damaging kind of on a spectrum. So if neutrons are what we call thermal or have a slower energy, they can be absorbed by things like sodium and potassium in your body. But if neutrons have a really high energy, then they may just pass through your body without really interacting at all. So they can travel large distances in air, like gamma rays and X-rays, just because they don't have that charge component to them. There are a couple common neutron sources. Thankfully, they are relatively rare to come across. So californium-252, this is a natural neutron emitter. There's 2 places in the world that make it. There's Oak Ridge here at the high flux isotope reactor, and then also somewhere in Russia. So chances are if you encounter californium-252, it's coming from Haifa here. Also, if you see any sort of alpha emitting nuclide paired with beryllium, this will also be a neutron emitting source. So something like americium, beryllium, plutonium, beryllium. These are more of the common neutron sources that we encounter. But again, relatively speaking, neutrons are very rare. Okay, so that went a little bit into what are the different modes of decay. So either a particle or a wave, what are the nuances with these different particles? So now I'll talk a little bit about how much radioactive material is present, because it's important to note that if you have a small source, that doesn't necessarily mean it's not dangerous. And I think that's something that we really like to emphasize here. We'll talk about case studies where people put tiny sources in their pockets and receive extreme damage from that. So the size of the source doesn't necessarily mean it's not dangerous. So talking about the activity, this is the amount of decays that it undergoes. So how many alpha decays, beta decays, gamma emissions over a certain period of time. Because decay is a spontaneous process. If I have 1 atom of americium-241, I have no idea when that's going to decay. But if I have a kilogram of americium-241, or even a gram or a milligram, I can say on average, it will decay at a certain rate. So the normal unit of activity here in the US is the Curie, named after Marie Curie, of course. 1 Curie is defined as the activity of 1 gram of pure radium-226, which is the isotope that she was able to refine from pitchblende. So 1 Curie is 37 billion disintegrations per second. And a disintegration is simply just one, essentially a decay. So 1 alpha, 1 beta, 37 billion. So that's kind of an awkward number to deal with. Internationally, you all use the becquerel. So this is considered the SI unit of activity. And 1 becquerel is 1 disintegration per second. So if you have a really large sample, it is kind of nice to use Curies, just because 1 Curie is 37 billion, but using small samples, becquerels are quite nice. But then you can also, use prefixes to change that. Converting, you kind of need a calculator to do this. It's not an easy conversion. So 1 Curie is 37 gigabecquerel, and 1 becquerel is 27 picocuries. So again, kind of awkward to go between units, but it is possible. A lot of times when you hear about radioactivity, you hear about the half-life, and this is really important because it tells you how active is your sample? How long does it take for your sample to decay into its daughter product? So here in this image, if the red is considered to be the radioactive nuclei and the blue is the non-radioactive nuclei, once you go through 1 half-life, your sample will be half radioactive and half not radioactive. After 2 half-lives, you essentially take half of your radioactive sample away. So now it's a quarter radioactive and 75% non-radioactive. So each half-life, you're decreasing your radioactive sample by a half. And it's important to note that the shorter the half-life, the greater the activity. So if your half-life is 2 seconds, that's going to have a higher activity than an isotope that has a half-life of 37 years. So thinking about activity and amount of radiation, I'll kind of visually demonstrate how much of a sample you need to reach the activity of 1 curie. So a couple slides ago, I said that 1 curie is defined as 1 gram of pure radium-226. And if you look here, the half-life of radium-226 is 1,604 years. So 1 gram to reach 1 curie of radium-226. For uranium-235, when people hear about uranium, they think, oh, this is scary. Like uranium is so dangerous. And it can be if it's enriched, but if we're looking at just pure uranium-235, the half-life of it is 7 billion years. And so if you compare that with radium-226, which has a half-life of 1,600 years, you can see that the half-life of uranium is much, much higher. So you would need about 500 kilograms of uranium-235 to have the same activity as 1 gram of radium-226. Going the opposite direction with cobalt-60, the half-life here is 5.25 years. So comparing that with 1,600 or 7 billion, you only need 1 milligram of cobalt-60 to have the same activity as 1 gram of radium-226, have the same activity as about 500 kilograms of U-235. So this is why we try to emphasize that the size of the sample that you may have doesn't necessarily say if it's going to be a hazard or not. There are small radioactive sources that aren't dangerous, and there are some like cobalt-60 that will be incredibly dangerous. So just really looking at the activity of your sample and not just the quantity that you have. So next, I will talk about how is the energy delivered from your source. So now we know kind of how activity works. It's the decay over time. How does the energy from my source interact with the body? Because this will kind of drive your medical decisions if you have someone that's been contaminated or exposed. So we have first exposure. Exposure really only relates to X-rays and gamma rays because alpha particles and beta particles don't travel very far in air. So it's really difficult to measure an exposure. An exposure is essentially just ionizations in air. So if it's not really traveling through the air, you can't really measure it. So for gamma rays and X-rays, how is the air being ionized by my sample? In the US, we use the units of Röntgen. This is 2.58 times 10 to the negative 4 coulombs per kilogram of air. So essentially energy per kilogram of air. Internationally, they don't use Röntgens, they just call it coulombs per kilogram. When we're looking at a radiation dose to a patient or to a worker or whoever it may be, you're looking at the energy absorbed per unit mass of material. So how is the energy of my source being absorbed by the body? In the US, we use rads as our base unit. 1 rad is equal to 100 ergs per gram. So again, just energy per gram of whatever material you may be looking at. Internationally, you use grays. This is equal to 1 joule per kilogram. And this conversion is very nice, especially compared to like curies to becquerels, because 1 gray is equal to 100 rad. So essentially just add 2 zeros or take away 2 zeros, and then you can convert between units. In most of the lectures today, we'll be discussing things in terms of gray. For absorbed dose, like I said, it can be calculated for really any material. So you can look at absorbed dose in bone, in water, or tissue. Sometimes we use water as a tissue equivalent. You can look at it in air, in plastic, in any material that you're looking to irradiate. And a really nice, rule of thumb, if you know that someone's been exposed to a certain amount, you can generally say that 1 Röntgen of exposure delivers 0.01 gray or 1 rad of absorbed dose to tissue. This is not exact. This is a basic thumb rule, but it's something that's really nice to use for a quick medical triage if you don't have a calculator handy or anything like that, but you have a meter and you can measure exposure with that meter. You can then calculate or estimate absorbed doses to the people near the source. Once you know absorbed dose, you can then take it one step further and look at the dose equivalent. And this is a way that can help you estimate how biologically damaging is my absorbed dose. Now I'll go through how to calculate that in a second, but in the US, we use the units of REMS, and then internationally, you use units of sieverts. To look at the dose equivalent, you use what's called the radiation weighting factor or the quality factor. And this just takes into account how biologically damaging is the radiation type that I have encountered. So like I said before, alpha particles, if they're inside the body, are a lot more biologically damaging than a gamma ray or a beta particle. And this is because if an alpha is inside your body, it's going to interact with the tissue that it's near because you don't have that dead layer of skin protecting you. And the alpha particle has to go somewhere. So it's going to interact with your lungs or your stomach or wherever it may be inside your body. With beta particles, they also interact, but because they are not as large as alpha particles, the interactions are less biologically damaging. With gamma rays and X-rays, if you've internalized these, there is a chance that it may pass through your body without actually interacting. And then with neutrons, like I said before, if they are thermalized or if they have a slower energy, there's a good chance that they can be absorbed by some sort of material within your body. But if neutrons are fast, then there is also a chance that they may just pass through and not interact. So here we're showing that alpha particles are 20 times more damaging than a beta particle or a gamma. And neutrons are on that spectrum of 5 to 20, just based on their energy. If you don't know the energy of a neutron, just assume 10. That's kind of the median radiation weighting factor that could be encountered. So essentially, to go from absorbed dose to dose equivalent, you would take either the rads or the grays, multiply it by the radiation weighting factor, and that will give you your dose equivalent in either REMS or sieverts. I know that could be a lot of new terminology for a lot of you. So this just kind of puts it in a flow chart nicely so that you can see how you go from one measurement to another, and then you can go into your dose calculations that will help you in making those medical decisions for your patient. So we start with activity. This is measured in curies in the US or becquerels internationally. This is just how many decays are you having per unit time of your source. From activity, if it's a gamma or an X-ray, we then go to exposure. This is measured in Röntgen in the US or coulombs per kilogram internationally, and this is ionization of air. From exposure, we can then calculate absorbed dose, and this is either in rads in the US or grays internationally. And this is energy absorbed per unit mass of whatever material you may be looking at, whether it's tissue or bone or whatever. From absorbed dose, you then take into account what type of radiation am I looking at? Is it alpha, beta, gamma, X-ray, neutron? Take that radiation weighting factor, multiply it by your absorbed dose, and that gives you dose equivalent, which is measured in REMS in the US or sieverts internationally. And if you really want to take it one step further, if you love math or just have a lot of free time or whatever you want to do, you can then look at the tissue weighting factor. And this takes into account what tissue was exposed. So whether it's your thyroid or bone marrow or a lung or anything like that, there's tables of tissue weighting factors that you multiply your dose equivalent by. And then this gives you your effective dose equivalent, which is also measured in REMS in the US or sieverts internationally. So this is really what, as a health physicist, we do at REACS. If we are given an exposure, we can then kind of estimate a dose to a patient and then give that to the healthcare providers, and they can this can help them make those medical decisions. So it seems like a lot of math, but really if once you break it down into each of its pieces, it's really not so bad. And if you're more of a visual learner, we have our activity of the source. The activity, the energy is traveling to the receptor through exposure, so ionization of air. The energy is absorbed in the source, in the receptor, so either a person or an object, whatever you may be irradiating. And then lastly, taking into account the biological damage, you can then look at its equivalent. All right, so now getting into the nuances of irradiation versus contamination. This can also really help drive how you're going to treat a patient. Because if a patient is simply irradiated, you don't need as much protection for yourself or for the treating staff or decon of a room or things like that. Versus if a patient has been contaminated, this will, while it's not really a huge problem, it just makes you have to take a couple more precautions. So we'll talk about those really throughout the day. So contamination is simply something where it's not wanted. I did my master's at Colorado State University, and there they have a really good vet program. And one common procedure that they do at the vet school is treating cats with hyperthyroidism. So they'll actually inject the cats with iodine 131. If you inject a cat with iodine 131 intentionally, this is not contamination because you want the cat to have the radioactive material inside of it. The problem with cats is that they don't really like to get stabbed by needles. And when a vet goes to do this procedure for a cat, they need to take that into account. So one day at that school, a vet was going to do this procedure that she had done a lot of times. And when she went to inject the cat jumped and she squirted the iodine all over the table. So now she has a contaminated table. And in the frenzy of trying to catch the cat and pick up her syringe and everything, her mask actually falls down onto the table and into the puddle of iodine 131. And rather than getting a new mask from a box that I'm sure is close by, she picks up the mask from the puddle and puts it back on her face. So now she has contaminated table, contaminated cat, contaminated mask, and now she has a contaminated face. Thankfully, they also have a good health physics program there. And so some of the HPs were able to go in and look at her bioassays and do a dose reconstruction. And they found that she only had a small uptake of iodine, like on her cheek. Iodine is one of the few radioactive materials that can actually get absorbed through intact skin. So that's kind of unfortunate for her. But it was a very small uptake of iodine, but I'm sure she had a lot of paperwork to do after that as well. So that's just kind of an example of radiation. If you want it somewhere, that's not contamination, but if it's on the table, on your mask, on your face, that is definitely contamination. So contamination can be in the form of a liquid, like with the iodine. It can be a powder, it can be a solid, it can be a gas. And so just thinking about the different chemical forms of these, or like the physical forms, I guess, of the radiation contamination can kind of drive what protections do you need. If it's a gas, you need to think about protecting airways. If it's a solid or a liquid, kind of containing it and cleaning it up, how do you go about that? Typically, we see that if there's contamination on clothing, if you remove the clothing, you can remove up to about 90% of the contamination. So if you have a patient come in to the ER that's been contaminated, the first thing you want to do is just get clothes off, because that will drive the doses down for the patient and also the treating staff. If there's contamination on skin, most of the time we see that you can wash it off fairly simply just with soap and water. And we'll go into the nuances of that in later lectures. With contamination in the hair, the important thing really to note is that you don't want to use conditioner, because conditioner locks in moisture in the hair and it also locks in radiation. So if you use conditioner, you might wind up having to cut the person's hair. And most people are not a fan of that. So that was external contamination, but we also have internal contamination. And this is a lot more difficult to deal with just because it can't be cut off of clothing. It can't be washed out of hair or off intact skin. Internal contamination can enter the body through inhalation, ingestion, absorption through wounds, or in the case of iodine, absorption through intact skin. And it's a lot more difficult to determine for a couple of reasons. One being that if it's an alpha particle or a beta particle, you can't use meters, like a handheld meter, like a pancake probe or something, to detect it. Your body is going to shield any alpha or beta emissions coming off of that radionuclide. So if someone has inhaled an alpha particle, you may not know it just by holding a meter up to their lungs. If it's a gamma or an X-ray emitter, then you would be able to detect these sort of emissions coming out of the body. The other problem is that dose is protracted with internal contamination, meaning that your body is naturally going to accumulate the radiation in a certain area based on the chemical properties of it. And I'll talk about that in a second. So your body may have a really quick turnover rate. So something like tritium follows water. Your body naturally removes water fairly quickly compared to other things. So in addition to that water removal from your body, tritium is also naturally decaying. So dose due to internal contamination is taking into account the biological removal rate and then also the radiological removal rate. So something with a really long half-life radiologically could be in the body for a longer time if the body doesn't have a naturally high turnover rate for that substance. To kind of give a few examples of that. So sodium and potassium, these are found in soft tissue in the body, so kind of everywhere. If you ingest cesium, because it's in that same column of the periodic table, so chemically, your body treats them the same. So any cesium that you intake would go to anywhere that sodium and potassium are biologically available. So cesium will be spread throughout that soft tissue. If you have calcium, this is in bone. So something like strontium and radium, because they're in that same column, will follow wherever calcium goes in the body. So strontium and radium get locked up in that crystalline structure of the bone. So there's not really a high turnover rate for these things. They decay at a relatively slow rate. They have kind of long half-lives, and there's not a lot of calcium turnover in the body. So if you ingest these elements, they will be in the body a lot longer than something like cesium, because sodium and potassium have a higher turnover rate than something like calcium. So this is also important to think about. If it is a gamma emitter, think about where in the body this radionuclide is going. So something like iodine, if you intake that, chances are you can hold a probe up to someone's neck and you can maybe detect if there's iodine present or not. If you intake something like strontium, you want to find a big bone surface, so something like someone's head, where there's not a lot of skin shielding there, you might be able to pick up a couple emissions from there. So just thinking about where in the body your radionuclide might be going. So irradiation is just absorbed energy. So you don't have radioactive material on you or in you. You've just been simply exposed to something. So think of it like a dental x-ray or an x-ray of your arm. If you break it, the energy is imparted on you, but you don't take it with you. So you are not a hazard to the treating staff. So if you have a contaminated patient come in, that's when you want to think about, I guess, keeping all the material that comes off the patient in a rad waste area, being really careful about runoff and things like that if you're washing out a wound. But with an irradiated patient, you want to think more about just simple standard techniques for protecting the patient from the treating staff, like a mask and gloves and things like that. So just important to note that an irradiated patient is not radioactive themselves. So going into basics of radiation protection, health physics can be boiled down into 3 words: time, distance, and shielding. We always joke that we're going to get that tattooed on us one day. Those are the 3 things that define us: time, distance, and shielding. So you want to minimize time, maximize your distance, and then utilize shielding when possible. There are a couple nuances with shielding that I'll talk about. So with time, you want to minimize your exposure or intake time. So essentially, the less time you spend with the source, the lower your dose will be. So some ways to use time as a protection principle is planning ingress and egress. So if you know you have a source or you know you have a contaminated patient, think about how you're going to enter that room and how you're going to leave that room, and make sure that you do it the same way each time, and kind of maximize, or you want to minimize the time spent in that room. You also want to remove patients from high radiation areas. So if there's an RUD or an RDD that's gone off, kind of the first thing you want to do is, if there's people there, get them out. You want to lower their dose rates. And also practice with non-radioactive sources. So at REACS, if you come to one of our home classes, we will actually contaminate, well, not contaminate because we want it to be there, but we will put a real live radioactive source on a patient, and you can practice washing that wound and irrigating it, and see how contamination control actually works. And while it is radioactive, it's done in a very safe way, and we're all watching and making sure it's done safely. So just finding ways to practice decon and taking care of contaminated patients before a real event actually happens. That can really minimize the time because you already know what to do now. With distance, radiation works in a geometric way. It's all kind of like a campfire, essentially. So if you're standing really close to a campfire, facing it front on, your face will get really hot and the front of your body gets really hot. But if you take a step back, you can feel that heat drop off dramatically. Or if you turn around, then your back is hot, but your front is cold. Radiation works essentially the same way. We use what's called the inverse square law, where if you double your distance from a source, you decrease your dose by a factor of 4. And I think Dylan's going to show you mathematically how that works later on today. So just finding ways to increase your distance from your contaminated patient or your source of radiation or whatever it may be. Some ways to do this is using long-handled instruments. So using like forceps or something like that with a really long handle. Also, just take a step back. So if you have a contaminated patient and you're not directly working on them, step to the side and just try to increase your distance as much as you can, and that's going to decrease your dose. Lastly, with shielding, there are a couple nuances of shielding. It's all based on the radiation type. So I talked a little bit earlier about how alpha particles are huge and they can be blocked by the dead layer of skin. They can be blocked by paper. So relatively easy to shield. You should have alpha shielding material everywhere. So they are, out of all the radiation types, the easiest to stop externally. Again, internally, different story, but externally, fairly easy to stop. With beta particles, they can travel through that dead layer of skin. They can travel through paper, but they are stopped by a thin sheet of plastic. So if you have like a plastic tarp or something like that, that can trap beta particles in it and provide you some shielding. Here's just some examples of alpha and beta shielding in medical facilities. These are things that we use at our home courses. I assume that they're available pretty much everywhere. Simple face mask, a face shield. This is plastic, so it would shield from betas. Latex gloves are a nice way to shield from alphas. And Tyvek suits, they're pretty thick material, so they also do a nice job of shielding. And also just keeping contamination off of you. I mean, that's really, PPE is the best shield, honestly. One thing to note with beta particles is what's called bremsstrahlung X-rays. So with a beta particle, if you have a really high density shielding material, so think like stainless steel or lead or something like that, the energy of the beta particle as it's getting slowed down by these more dense materials has to go somewhere. So this energy is emitted as an X-ray. So while you're stopping the beta particle, you now have a material that's emitting X-rays. And this can be a huge problem if this is not what you want to do. For things like linear accelerators, they take advantage of this bremsstrahlung effect. So they essentially have an electron accelerator, and the electrons hit a beam dump that's made of a high density material, and it creates X-rays. But these are intentionally created X-rays. So they can be a really good thing. But if you have a beta source that you're trying to shield, use plastic, don't use stainless steel or lead or something heavy. Next, we have gamma rays and X-rays. So they have a higher energy and they're not a particle. So you need something dense like lead or stainless steel to contain these. And here's a couple examples of gamma and X-ray shielding in medical facilities. When we talk about patient treatment, a lot of people ask, should we wear lead aprons if we have a patient that's exposed to gamma rays? And typically we say no. And this is because it's going to potentially increase your time spent with a patient just because they are kind of heavy and cumbersome. It might also decrease your distance from a patient because it's hard to maneuver if you're wearing something that's pretty heavy. Just lastly, the amount of lead in these really isn't going to protect you to a great degree. And so really you want to use time and distance before you think about using shielding, especially with something like a lead apron. For Linacs, they do have these concrete mazes designed, and these are meant to protect any patients or workers that are outside of the treatment room. And so if you have a gamma source and don't know what to do with it, a nice place to put it might be one of these concrete mazes that they use, until you know further what to do with the source, if you can remove it and isolate it and keep it away from people and keep everyone's exposure down. This could be an option to put it. And kind of going back to the lead apron, it really does depend on the energy of the source that you have. So a low energy X-ray or gamma potentially could be blocked by it, but something with a really high energy, you're going to need something like a concrete wall or 400 kilograms of lead or something just insane that's going to increase your time and decrease your distance to so much of a degree that it's really not a practical protection factor anymore. So that's why we kind of say, think about time and distance first, then utilize shielding when possible. It's also possible to kind of improvise shielding. So here they had a industrial radiography source. So this is a really high activity gamma source, and it was stuck inside a pipe. And so they were able to find exactly where the source was using a meter and then just threw a sandbag on top of it. And that was kind of enough to keep the dose rates relatively low. So then they could start to remove that source from the pipe. So using sandbags, we have a case study where people throw a rock on top of a source. So you can improvise shielding to fit whatever scenario you have. But again, think about using time and distance before using shielding. And then lastly, neutrons. Neutrons are always kind of weird because they are particles, but they don't have a charge. So you want to shield neutrons with something that is essentially the size of a neutron. So hydrogen is a great option. So things that have lots of hydrogen like water or plastic or concrete are all really great neutron shielding sources. Or neutron shields, I guess. Sources of neutron shielding. I don't know. So the way that these would essentially work is that the neutron bounces off the hydrogen nuclei like a billiard ball until it is slow enough to be thermalized and then captured by whatever material you are shielding it with. And like I kind of mentioned before, PPE really is such a great shield. It keeps you from going home naked. I'm sure your family and everyone will thank you for that. So this is another one of those posters that I love. But yeah, always start with PPE and then go on to different shielding if you need to. So just to summarize, I know that was a lot of new information, probably a lot of different units, but I hope that throughout the day today, the units will kind of get more familiar and just easier to use. I know that sometimes when I talk about grays, people think of a color, you don't think of an absorbed dose. So just getting used to things like that. So we talked about the different types of radiation, alphas, betas, gammas, X-rays, and neutrons. Exposure is just ionization of air from a source. Absorbed dose is that energy actually getting absorbed in the biological material or whatever material. And then dose equivalent is taking into account what type of radiation are we looking at and how biologically damaging is it. Then we talked about contamination being radiation where it's not wanted, and irradiation being just simply exposed to that radiation. And then basics of radiation protection, health physics, all defined as time, distance, and shielding. And that's all I had. So thank you, everyone.
Are there more questions for the chat? I know we've been tracking that throughout Megan's presentation, and thank you, Megan.
Thank
That
you
was a
all.
great job. Yeah. Lots of clapping and thumbs up.
Thank you.
Oh, and a few hearts in there. All right. Let's see. Here is one that hasn't been answered yet. In what circumstances would a higher level of respiratory protection be recommended? REACT usually recommends this surgical face mask. This isn't us, but are there times when an N95 or a PAPR should be utilized? We will go into that a little bit later, but Megan and Dylan, do you want to give any thoughts on that right now?
Sure. I'm actually going to talk about PPE, I think at the very end of the day. So hopefully that answers your question better. But
Okay.
if I can quickly just say that if there's a suspected aerosolized radiation source, or if something is volatile, that's when you would want to think about a higher respiratory protection. So using something like a PAPA or an SCBA, you should definitely just look at the nuances of the source that you are working with. And then you can always bring it down to a lower level if you determine that something isn't volatile or it's not aerosolized.
Okay, thank you. And the next question, any thoughts on graphene composites for shielding?
I don't have any. Dylan, do you have any comments on that?
Not particularly. I know there have been problems with it in the past. It was also a really useful one in the past. So outside of looking into those that use kind of graphene shielding, nothing in particular for me.
Yeah, I'm sorry.
Okay, if we find something, we'll put that in for you.
Yeah, definitely.
And can you expand on thermalized?
Yeah. Thermalized is essentially a neutron that's been slowed down enough so that your body or whatever material that it's encountering can absorb the neutron. So it actually gets incorporated into the nucleus versus a non-thermal neutron would be one that has a high enough energy that it would just bounce off the nucleus and continue moving.
Okay, great. Thank you. And this question is, while attending to internally contaminated casualty, what safety precautions need to be taken while handling blood and urine samples?
Mm-hmm. I think we talk about that later today too.
Yes, we'll go into much more detail on that, but that will go along with all the PPE, and not to put you off and make you wait, but we'll go into that in depth here in a bit. So let's see. Thank you, Megan, for verifying that lead shields are not required anymore for basic X-rays. As I questioned them this year when they didn't put a shield on me. Okay, all right, well, there you go. And then the last one in here is, can you explain the usefulness of counts per second for survey meters? If we have a reading of 15 kilo CPS but unknown source, how can I use that information?
essentially counts per second is looking at what is your meter, and Dylan's going to talk about this later actually, but essentially what's your meter seeing, and then you have to take into account meter efficiency, and this will get you to disintegrations per second. And then in terms of like kilo counts per second, I'm not sure I really understand the question. Dylan's going to go a lot more into interpreting meter readings and what that means as a kind of a medical indicator of if it's concerning or not.
Wonderful.
To cover the basic of that question without going too much into what the next lecture or what the future lectures will cover, we can take those counts per second, kind of identify how efficient our detector is, and that will tell us how much activity we have. If we know how much activity we have, once we identify the isotope, we can start finding out how concerned we are. So it's kind of the first step to finding out if we're concerned or not.
Mm-hmm.
I was muted. Wonderful. All right. Well, thank you, Megan. That was fantastic. Yes, appreciate that very much. I am up next, so I will work on sharing my screen and video. Thank you. That not only educational, but an interesting way to discuss basic health physics. So, all right. Let's see, let's share. You're going to see some oddities here for a moment. Actually, my cute doggy and my busy screen there. And let's get into presenter mode. Can everyone see this now?
Looks good, Karen.
Okay. Oh, lots of thumbs ups and a little heart. Okay, thank you. I appreciate that. And let me move this out of the way. And let me come on video. Sorry about that. All righty. So we're going to talk about acute radiation syndrome. And as we go through this, oh, hang on. Let me make sure I'm back in here so I can advance my slides. As with all of us today, ACCME does require that we disclose whether we have financial interest or not. We do not. You'll hear us get shorter and shorter on this slide as we go through the day, but none of us have, we're not trying to sell you anything. None of our partners, family, dogs, cats, or anyone's going to try and sell you anything today. And we will possibly go into the realm of not FDA approved uses or off-label uses of medications. I should be letting you know that as we go. And is my camera on? Can you guys see me? I can't see if you can see me. Well, it's all good. We'll press on. So as far as our objectives, to say we're doing a brief overview of radiobiology, my apologies to any radiobiologist out there. It's more than a brief overview. It is like a 10-second review. But given that we are compressing a full course into one single day, there are going to be some things that we do not catch. I will say that we do have as one of our panelists today, Dr. Adeobalam Balaji. He is our director of our cytogenetic biodosimetry laboratory. So if you do have some questions, you're welcome to put those in the Q&A, and he can address those a lot more in depth. So, but let's go. We're going to go through triage, medical management, and one case study to help drive these home. Now, I don't want to focus on all of these. As you see, there are some red arrows here for a reason. But let's talk about why radiobiology is what it is. We look at the biological effects, and so many of these are very intuitive. We're looking at total dose. We're looking at dose rate. We're looking at volume of tissue irradiated. That all makes sense, I think, right? It's very intuitive. The type of radiation, you just heard Megan talk a lot about that. And I think that's kind of the key on this one. And I just found that I hadn't shared my camera with you, so my apologies on that. But so at any rate, that is what Megan just discussed with you. Pre-existing conditions. We won't be able to get too much in depth about comorbidities, multimorbidities, burns and or trauma with radiation. But these things will all worsen the prognosis and the outcome. A radiation combined injury, which is radiation with burns and or trauma, certainly has a much worse prognosis for an individual. When you triage these individuals, depending on your resource availability, it will really change your categories. These may become your expectant patients. They may be the patients who receive comfort care, palliative care, if resources available. But always do reiterative triage, and I will talk about that a little bit more as we go. So typical dose recorded in the Chernobyl workers who died within a month, and this is in millisieverts. And we listen to things a lot like Fukushima. Did people ever talk about anything other than millisieverts or sieverts basically in Fukushima? No. If you followed a lot of Fukushima, and Megan has just given you a great discussion on this, while I will say the units are one of the most difficult things to get familiar with, they are incredibly important. And a lot of our US based policies, guidance, et cetera, is not in our international units. So if you can start trying to brush up on those, and I will admit we're all guilty of, sometimes doing the wrong unit conversion. So just try to get more familiar with those. But 6,000 millisieverts. If you want to look at, let's do a comparison. The Fukushima plant on March 14th, the max radiation level, 400 millisieverts. If you look at an airline crew going New York City to Tokyo per year, 9 millisieverts. And then if you look at a chest x-ray, a tenth. 0.1 millisievert. So just some things to keep in mind. The individual susceptibility factors we won't really get a chance to go into, but these fortunately are getting much more attention, much more research. If you can come to our advanced radiation medicine course, sorry, shameless plug for the course, but we do get more into some of those issues, and you will definitely get a much deeper dive into radiobiology from Dr. Balaji. So when we're talking about radiation, I think most people know DNA is the target. People always know about mutations. That's one of the things that the public will focus on, are mutations. But there's, and I don't know that we got too much into this with Megan's, but we did a little bit. So we can have direct action with those alphas and neutrons. She did a great job describing kind of the differences between these and why they can deliver more of a punch, if you will. I'm going to use a very crude analogy to describe, and I know we've got RSOs, we've got health physicists, we've got all the brainy types on this webinar. So I want you to bear with me for a minute because I'm going to make this very simple. I think simple things are easier to learn and keep in your head. So the way I like to think of a high linear transfer is, I like to think about someone who's at let's say a calm lake, and they find a smooth stone, and they pick up that stone and they toss it to where it skips across the water. So it's going to hit the water, deliver a little energy, hit the water, deliver a little energy, hit the water, deliver. Oh, and actually, I'm sorry, I'm doing low. Sorry, I just got myself reversed. So low energy transfer is going to be that skipping, giving off a little bit of energy there. Sorry about that. Yeah, yes, thank you. Yes, like I said, we all do, make those mistakes because we're human. But yeah, so skipping that rock. If, on the other hand, you end up, thank you, getting, let's say, a child, and I see this anytime I'm around the grands now. Used to, it was just the nieces or nephews. Now it's the grands. But inevitably, if you're near a body of water, they're going to find the biggest rock they can possibly pick up, and usually it's bigger than they are, and they're going to go over to that pond of water or that lake, and they're just going to go thud, and poof, all that energy is delivered right there at once. So if that helps to kind of conceptualize that, sorry, I got you confused on the front end of it, but hopefully you can conceptualize the difference between that high energy transfer versus a lower energy transfer. And so obviously if we have, and this takes you way back to high school and all that kind of neat stuff, but if you have a single-stranded DNA break, it's okay, right? Because you've got that other template that you can use to replicate. So, hey, not damaging, no harm, no foul. You can still replicate. With a double DNA strand break, well, that's difficult because you can't replicate. And there are some conditions in people where they genetically, I'm not going to go into detail, but they cannot repair DNA damage. These individuals are a much higher risk for having all types of malignancies. And if that might help you keep that conceptualized in your head a little bit too, these double DNA stranded breaks aren't repairable. Let's put it that way. Now, we also have the indirect action that goes on. And usually it's the hydroxyl free radical, but there are other free radicals, but X-rays and gamma rays can induce these. And we'll talk a little more as we go in this section, but also in another one later on, about some of that oxidative stress and nitrositive stress. That's a little bit further in depth, but we can get those free radicals that will cause oxidative stress. So we have both a direct action and an indirect action that causes the damage. And I hope Dr. Biology isn't sitting there going, oh, Dr. Iddens, so, while I'm butchering his radiobiology section. But anyway, let's get back on track here. The law of Burgundy and Tribondeau. And someone criticized my French pronunciation recently for that. I'm sorry. I am originally from East Tennessee. That's as good as my French gets. But this law, in fact, a lot of people at REACTS used to call it the two French guys rules because they didn't even want to try saying their names. But this law that they established really built the basis for radiotherapy. They recognized that there were certain cells that were much more sensitive to radiation. And this was in 1906, 1904, 1906. Someone ping something in the chat if you got that year specifically. I think it's 1906. But at any rate, they found that certain cells would be more sensitive. And these were very active metabolic cells, actively dividing cells, and immature, undifferentiated cells. And that is literally what we have based the world of radiotherapy upon, are these cell sensitivities. So if we look at the top, and I don't know if my pointer works, but we're going to just, I'm going to show you the top, see, 3, 4, 5, 6. Mature lymphocytes. Right away, just hearing that phrase, some of you ought to kind of scratch your head a little bit and go, mature. You said these were undifferentiated. Why are they so sensitive? Because they don't meet all this criteria. I'm not sure anybody knows exactly all the nuances as to why they are essentially the most sensitive cell type in our body. But it's a good thing for us that they are, because we can use this as a triage tool. So we'll come back to that later. Think about the lymphocytes. I know for all of our clinical types, we're always focused on febrile neutropenics, which we are in this case too. However, a lymphocytopenia, or a decrease in those lymphocytes and a decrease in the absolute lymphocyte count, it can be something we use to our advantage on this. Spermatogonia, we're not going to talk a whole lot about. You could spend a whole hour talking about that. We will not do that. The myeloblast in general, we're going to discuss intestinal crypt cells. We're going to talk more about those. Epidermal stem cells and endothelial cells. So just those top 6 are going to be what we primarily focus on. And you can see the other ones as you go. Now this curve, and oftentimes people like to, do all kinds of things with this curve. I want to just point out a couple of simple things. LD 50/60. Now tomorrow you are going to hear a lot from our toxicology friends on LD 50s and 50/30s, but it's the lethal dose for 50% of the population, and in this case in 60 days. Now think about that for a minute. Lethal dose for half of the population within 60 days. This curve has been used a lot. And basically the gist of this and the takeaway on this is that with supportive and intensive care, we can shift that LD 50/60 from 3.5 to 4 gray, or if you like your rads, let's see, add 2 zeros, so that'd be like 3,500 to 4,000 rads. You see why we have people to do math and not me. But with that, you take that curve and you shift it to the right with care, much further to the right with care. However, this is not talking about long-term survivability. It's not talking about an inhomogeneous absorbed dose. There are a lot of nuances to these. So I want you just to keep that in the back of your minds, and just keep in mind, yes, you can save people for a longer amount of time with good treatment. Now, this is old modeling. I'm going to fess that right up from the get-go. This is 2015, 10 kiloton detonation, New York City, Times Square. I want you to see the bottom line, total injured, 1.3 million, essentially, okay? And they did a nice job. They modeled this, broke it down into all these groups. Now, and this is Brooke Bodemeyer out of Lawrence Livermore National Lab. I will highly recommend, we should put this in the chat, go to the Lawrence Livermore National Laboratory website. They have all kinds of teaching graphics and some videos that are open to the public to use. They're fantastic. They do a really nice job with those. So back to what we're talking about. By just doing really good triage, we're going to be able to save roughly 500,000 of these individuals. We're going to have those who are, walking wounded, worried well, all those terms, we've all heard in the past. They really don't need a whole lot, though. Unfortunately, they will flood the system, and we'll have to deal with that. And then there are those that you're not going to be able to save no matter what you do. That doesn't mean don't provide treatment. If you have the resources, palliative comfort care are absolutely indicated. And this is my soapbox that I'll probably repeat about 10 times, reiterative triage. Now, thanks to COVID, and that's an odd thing to say, COVID did help two things for the medical community. Well, a few things, but it helped point out how to wear proper PPE. It helped us, to an extent, reduce the hand to mask kinds of activities. We see less of that when we are doing our exercises here, but we do still see it, and it is everybody. So that's one of my soapbox issues. The other thing that I hate to say helped, it gave insight into scarce resource triage. Also, somewhat of a mindset of what a military triage consists of. So those are my big things, reiterative triage, and it's going to be tough, a tough situation for triage. Now, with this, so this modeling 4 million people in the path, in the area of the fallout. This is Times Square. It's a little distorted, but I wanted to make it bigger. About 1 million casualties and acute deaths, 50% burns and trauma within 0.8 kilometers. So, you know, that narrow region, that zone is going to be very important. Out of those, about 64,000 who survive will have a dose greater than 6th grade. And I want you just to think about that for a minute. Now, will it be a homogeneous whole body exposure? Likely no, unless they are right there. And if they're right there, they aren't going to be making it. But if you have, and this comes out of our registry, approximately of the individuals who have and we'll say a mostly whole body absorbed dose of 6th grade, will have cutaneous radiation injuries and or cutaneous radiation syndrome. And we'll get into that later on today. So I want you just to kind of stick that away just a little bit. So let's move on to this next one. We do have these predictable phases, and the case that I'm going to show you really does shows you this concept quite well. In that prodromal phase, initially 24, 48 hours, don't want to eat, nausea, vomiting, fever. If there's a high fever, not a good sign, maybe some diarrhea. A latent phase, they may feel better for a short amount of time. The higher the absorbed dose, the shorter that phase, and the worse of the prodrome. And for our French and Italian speaking friends, the prodromy, if you will. So with that manifestation of illness, that can last weeks to months. You can have an immunocompromised individual that may require some very intensive care. So the question has to come if it's a mass casualty. So for instance, a nuclear power plant excursion, whether we have a detonation, IND, or a nuclear detonation, which sadly we now have to discuss. These would be patients that you really want to be careful with that triage so that, and I hate to say it this way, but so you're not using critical resources on individuals that no matter what you do are not going to survive. That's an important concept. So there are 4 major organs that we talk about classically for the acute radiation syndrome. These are sub syndromes, if you will. And what I'm going to show you are generally the dose ranges or thresholds where we would see that classic presentation. And I want to emphasize that, the classic presentation, because these vary all over the place. They're not set in stone. Really, it depends on the individual and comorbidities, et cetera, et cetera. But we generally have a subclinical phase up to 1 gray. And if you're a rad fan, add your 2 zeros for 100 rads. Hematopoietic. So greater than, maybe even equal to 2 gray. And we're going to dive into this a little bit deeper in a second. Gastrointestinal, greater than 6. Cutaneous, and there's going to be some caveats to this, but if you had a mostly whole body cutaneous absorbed dose greater than 6 gray, you could have that organ syndrome, but we'll get into the finer points of that later on today. Multi-organ failure, greater than 8 gray. Neurovascular or cerebrovascular, 10 gray. Now, I'm not going to give a plug for something that hasn't been published yet, but there are some textbooks out there that do include chapters on radiation. And we were recently revising one of those, and they still had in there that greater than 50 gray. Well, yes, absolutely. If you're greater than absorbed dose greater than 50 gray, you're going to have all these things, and it's not going to be good or pretty. So let me go ahead and dive into the subclinical. We're just going to spend a second on this. So 0.1 gray, and here I threw in for centigray or rad, so you get to choose what you'd like to look at for units. No difference whatsoever. Okay, we can have a sperm count decrease, takes 45 days at 0.12 gray. This is not azoospermia. That takes a much higher threshold. 0.2 gray, and actually technically this is probably lower. Dr. Balaji is very good in finding those dicentric chromosome aberrations, but we're going to stick with 0.2 for now. So you can start to see those DCAs, that's a dicentric chromosome aberration. Oh, and I didn't even show you a picture of those. Our lab can do those in a clinical setting for a clinical case. You can go to our website. There's a whole section on the testing. You can even take a test on how to become a scorer for dicentrics. It's pretty fun. It's cute, but it's also helpful. And then finally, you have to get pretty close to 1 gray before you can start detecting bone marrow depression, and only a small fraction will have some vomiting at that point in time. Now, this document is required reading for all of our medical clinical staff at REACS. It's an excellent document. Very little has changed dramatically from this. It's excellent going through the pathophysiology, treatments, and there have been a few changes there. And you do see these assumptions that are in this document. However, this document still holds up even with these assumptions. And NATO is actually working on a triage app using the Metropole hematopoietic ARS model. And AFRI has worked with them on this in a NATO group, and I think they were trying to combine both of these, and I haven't seen it just yet, but if you ever see STARS out there, the software tools for triage of acute radiation syndrome, if you get a chance to go to that workshop, I highly recommend it. It's a very good workshop. So here's the Metropole hematopoietic system, and this is as close as we get to really good grading for these organ systems. And I want you just to focus, it's a busy table, but focus on this serious or fatal, and hopefully you can see my cursor here. When we look at those lymphocytes, they're going to decrease further and faster than any other cell line. Very important. That's a foot stomp moment. Look at the absolute lymphocyte count. That is going to be your key indicator. Are you going to, when you get one of these individuals, let's say there's no hemorrhage, no major trauma, are you going to get them type and screen to transfuse them immediately? No, you will not. And we'll get into what you do need to do here soon, but HLA typing do as quickly as possible in case they become a good candidate for bone marrow transplant. So let's jump back into this. So you do get a nadir, and you're going to have that linear decrease. It's going to reach low levels within 24 hours when you've got a serious or possibly fatal case. I'll show you some tables here in a few minutes that will help with this. With the ANC, absolute neutrophil count, the nadir, a nadir is that lowest point. The nadir for this, let's say a week, essentially. And then for platelets, okay, let's say a little over a week. So these would not be immediate transfusions, but a lot of caveats to that. And this is with your serious or fatal category. Can't emphasize that enough. Now, our own Dr. Goins, whom many of you have met and heard speak, has decades of experience in this and has written most of the consummate publications, if you will, for lymphocyte depletion kinetics and many other things that have contributed to our science with this. He actually has done work on the lymphocyte depletion kinetics. And what we find from this, again, that lymphopenia, early indicator of dose. Now, can there be a red herring? Absolutely. We have had a situation, some of the individuals that were on that call are on this webinar, I feel certain, but there can be some red herrings that go along with this. So the full clinical picture, the full prodrome, you really have to look at and use a bit of the art and the science of medicine, if you will. Typically, we can see that aplasia of the bone marrow, pancytopenia 3 to 4 weeks later, but we can also have recovery of that bone marrow generally around the 30-day point, and we'll get more in depth with this in just a minute. Now, you can read these bullets on the left, and I think they're very intuitive to everyone. I just want to show you on the right, here we have bone marrow from a healthy person. Here we have bone marrow from someone who was exposed to 4-gray. And you can see lots of nice cellularity. You see down here, lots of fat globules, not a lot of cellularity. Looks very much like aplastic anemia. So that is what you would see with this. GI system, and we're going to keep rolling because I did not start my timer, and Dylan or Megan, if you see me getting about 10 minutes from the end, please ping me, okay? So for GI system, let's again focus on serious or fatal. So rapid onset of diarrhea, prolonged, explosive, watery, loss of mucosa severe. That is something that you're not going to know initially. You're not going to be doing biopsies to tell. Oh, that popped up. That's not going to tell you anything unless you do a biopsy, GI bleeding, abdominal pain. So let's jump on into this one a bit. When we do the longer version of our courses, we get more in depth on these topics, but especially in our advanced course. But on this one, let's suffice it to say that those stem cells live in these intestinal crypts. They travel in a single layer up the villus, and that's what gives us all that wonderful absorptive capability. Well, if we knock out those cells, they're not going to be able to travel up and propagate and protect and absorb nutrients and be a barrier for bacteria. They're going to end up like this image below, where you see these raw denuded edges, where everything within the intestines can gain access to the systemic circulation. We could have bleeding, so you can see what a difficult problem this can be. And then here is an example of a individual with necrosis, and this was a 20 gray absorbed dose. So absolutely, that's a difficult issue. There are some things in research that are looking to hopefully get approved or have emergency use authorization. They're still in the research pipelines, if you will. If you can come join us for an advanced radiation medicine course, we get an update from, and a big shout out to NIH, National Institute of Allergy and Infectious Diseases, for the Radiological and Nuclear Countermeasures Program, Dr. Andy DiCarlo and her team. We always get a nice, fresh update from them on the current status of all the things in research. So continuing on, neurovascular or cerebrovascular, yes, greater than 10 gray. Now, if you had a whole body homogeneous exposure, certainly this could be fatal at lower doses. We're talking a classic subsyndrome. You're going to see this really without too many caveats if you've got a mostly whole body absorbed dose of 10 gray or more. And I like to not focus on this one so much, except for the bottom, the neurological aspect of this. If you have an individual from an accident, there's no other indicator that they should have a mental status change, loss of consciousness, anything else, and they have that pretty rapidly, within minutes, within an hour, very rapidly after an incident, then these are going to be those individuals that may become that expectant category. You certainly need to retriage. You certainly need to keep checking on them, comfort measures, etc. But this can be fatal. A lot of cases out there that we don't really have time to expand on in this course, sadly. Now, I'm not going to focus on this one because we're going to cover this later. And if you don't mind, I'm going to skip right over it. All right, so just to keep us on time a little bit. So time to vomiting. You've probably heard it. Let me just preface it with this. If it is the only thing you have for triage, you're in a field setting, or because of a blast, now the city is a austere field setting, you have an ad hoc area where you're trying to pull individuals out or figure out who can we save, who can we not save. Time to vomiting can be your friend. We'll get into the caveats. Decline in absolute lymphocyte count. As soon as you can get a CBC with differential, you're going to have a great data point. You're going to want to get further data points. But if it's already abnormal, let's say within 12 hours, that individual is not going to have a good prognosis. So keep that in mind. It will take more time to look at the dicentric chromosome aberrations, but you can do this. And I'm going to throw this in right this very second. To collect this, you can get a dark green blood collection tube, lithium or sodium heparinized, dark green tube without the plasma separator gel. Okay, so that's what you need to collect this. Now, if there's a little bit of, let's say, wiggle room in the timing of this, our team can send you a kit with the proper tubes, how to package it properly, how to make sure there's no spillage, etc. If this is done for clinical decision making, we can provide this test. So we are operational with our DCAs. So I'm going to move on from that, but if you have any questions, we can sure put that, get you more on that. Dr. Balaji also has a how to collect your specimen on our website, so you can learn everything off of there as well. Now let's look at the other side. So we talked about CBC, usual medical trauma labs, HLA typing early. Also see the RITN guidelines, Radiation Injury Treatment Network. We just finished teaching a course for them in Buffalo. Very good course. They have a great system. We are perhaps the only nation with a system of cancer and bone marrow transplant hospitals throughout the U.S. that are networked together to receive casualties in case of a mass casualty event with radiation. Also, the cytogenetic biodosimetry assay, gold standard for biodosimetry. Yes, there are other techniques. And again, come back to see us in a longer course and we can go through those with you as well. All right, here's a table. It is an old table. Some people really don't like this table. Some people really love it. I just want to get the gist of this table across to you. So, onset of vomiting. It is not a great test. Look at the percentages. If you are in these lower absorbed dose ranges, as you see at 2 gray, 200 rads, you're only going to have a third of the population vomiting. And we're not talking a single episode of vomiting. We're talking protracted, prolonged vomiting. We hear all the time, oh, but the sympathetic vomiters. Okay, yes, yes, people can do that. But I also kind of toss out the counter to that. For those sympathetic vomiters, when your child is sick, when your pet is sick, are you sitting there vomiting with them? Or do you keep it together and then maybe you share the experience with them? Also, if you look at mass casualty incidents, you do see a small number of people who may panic. But you also see a large number of people who do not, and people will take leadership roles. And they can just respond. Look at the Boston Marathon always pops into my mind. You've got all these people running, these people watching. How many people did you see vomiting when that happened? I'm just going to toss that out there. So obviously it's something that kind of bugs me a little bit when that gets talked about. Now there is a pretty easy way to look at this, though it is important to talk about it. I'm not just not saying that's a wrong thing. An easier way to get a handle on this, and absolutely for first responders or anyone if you're near a detonation site, these are good tools. With vomiting at, let's say, the 4-hour point, 2 gray. So 4, 2. Vomiting at, and bear with me, I know I'm playing with the numbers a little bit. Vomiting at 2 hours, 4 gray. Make sense? 4 hours, 2 gray. 2 hours, 4 gray. It's very nice how it works out like that. 1 hour, 6 gray. This is when you're going to start getting into some real issues with survivability, because this is when that GI subsyndrome can become a factor. Currently, no FDA approved medications, though. Absolutely, you would do good GI intensive care for these individuals. That is around an hour. And if you see the unfortunate individuals who at half an hour are having just protracted vomiting, they may not have long-term survivability. And I choose my words carefully there. That doesn't mean you don't re-triage them. That doesn't mean you don't do anything for them. But those are the group that, if you're scarce in resources, may not get a whole lot of your time and attention. With the lymphocyte count, ALCs, look at this. Isn't this interesting? At 4 days, and we're abnormal, 2 gray. If you don't drop that lymphocyte count for 4 days, well, you're probably going to do okay. You might need a little support if you've got other comorbidities, et cetera, et cetera. Let's look at this one. 2 days. Oh, this is kind of nice. Using some liberties here, but abnormal range. Oh, that correlates with 4. So you'll hear a lot of people talk about the 2-4-4-2 rule. This is essentially what we're talking about. 12 hours. Yikes. You're looking at 100% of the population having prolonged protracted vomiting, and this is in half an hour. Abnormal ranges here, not compatible with long-term survivability. Let's look at the dicentrics. Very sensitive. This is a gold standard. This would be triage. This would be more standard scoring. It stops at 5 gray. And why? You might ask yourself, and many of you are already there, because you don't have enough lymphocytes to actually be able to culture and do the test. And with DCA, yes, it does take a few days. Because you have to collect them, ship them overnight to us. No special preparation for those blood tubes other than using the correct blood tube. Get it to us overnight shipping. We will get it processed, cultured 24 hours, and then processed, and you'll have a result in days. And it can be used to help guide treatment, absolutely, especially in unknowns. And it can be used for sentinel testing. Say you've got a group of responders, you've got NATO military, you've got this, that, or the other, these individuals running towards the disaster, not away from it. These would be key populations where you want the gold standard dosimeter for them biologically. Okay, dawn of the global nuclear age. Every person on this planet should know these dates. This is the 80th year, and I hate to say anniversary, it makes it sound like a pleasant thing, but 80th year. Hiroshima, Nagasaki. I got the opportunity to speak both at Hiroshima Medical University and Nagasaki Medical University. They were amazing hosts, phenomenal individuals. Love Japan, love the Japanese people. This is at the Hiroshima Museum, picture I took. There's the A-Dome. If you don't know about that, Google it. Here's the more strong building that survived it. Just a brief aside, I was walking with the graduate students from the train over to our building, and we're walking past this building, and it looks kind of familiar to me, and it shouldn't because that was my first trip. And I glance over and see this plaque. It is that bank building that survived. It's still there. I mean, obviously they had to do a little build up for it. It's still there with a plaque because it survived. Very famous pictures, not doing this to trigger any emotions with anyone, just famous pictures. If you haven't read this book, it's this thick. It's $4 on Amazon. I should have had a prop over here to show you, but very good book. This was written very soon after Hiroshima. And the physicians, the Japanese physicians, the military physicians noted these 3 stages. It's going to sound very familiar to you, I hope. That first group, if they didn't die from the burns and the trauma, and there were a lot of burns and a lot of trauma, they had days, nausea, vomiting, diarrhea, fever. Then they did all right for a few days, and then they would have this second phase, about 2 weeks, we'll just say, where they might have had some hair loss, diarrhea, fever, high fever, 106 degrees Fahrenheit for all of our international friends, 41 degrees Celsius. This last stage, about a month after, We're talking pancytopenia, all those cell lines drop out. We're starting to see bleeding happening spontaneously, epistaxis. Oh, good grief, I'm getting some kind of notification. Sorry. Bleeding gums, bleeding mucous membranes, everything. If you start seeing bleeding from all orifices, I'm sure many of you are familiar with disseminated intravascular coagulation, or DIC, that is a bad prognosticator. High, steady fever and low white blood cell count, very poor survival. Sounds very familiar, right? In 2011, the World Health Organization did some evidence-based recommendations. I've just been with another WHO consultancy group looking for evidence-based recommendations on a different topic, and these are very difficult to do in the realm of radiation. Why? We don't have randomized controlled studies. What we have are historical incidents. We have experiences in radiotherapy and animal studies, so it's very difficult. The one strong recommendation they had: consider prophylaxis with a neutropenic, which you would also consider that anyway. These, again, were their recommendations. Back then, they were weak recommendations. We also have Dr. Andy Yeager speak in our advanced course on infectious diseases. And if you're going to do something, go with levofloxacin, not necessarily Cipro for certain. Let's see, I've already gone through a lot of this. Always consult your infectious disease specialist, IDSA, NCCN guidelines. All right, so let's talk about this for a few minutes. If they're not responding, it's probably fungal. You can get all kinds of resistant species of Candida. Part of my past experience, I'm an obstetrician gynecologist. I have seen a lot of different resistant species of Candida, and they can be very difficult to manage. You can also get aspergillus. One of the things to think about, which would cover both of these, would be posaconazole. There are also others. We try not to keep these things printed because we know that the world of ID changes so frequently. Antimicrobials, let's continue. HSV, herpes simplex. Yes, absolutely. Get serology. Acyclovir, okay. It can also be myelosuppressive. And let's go to the next one. It's on here. Yes, thank you. If you're looking at CMV reactivation, that's going to happen within the first 100 days. For CMV reactivation, think of letermovir. That would be, oh, and I've got it on the slide. I updated that. Yay. Think of that. That would be a very good choice for you. As far as pneumocystis, urobetsii, pardon not having the second eye, Bactrim, still okay. And one of the best things you can do, and this strong recommendation from the WHO consultancy, was to give colony stimulating factors within 24 hours if you anticipate a greater than or equal to 2 gray mostly whole body exposure, and or they're neutropenic, and if they're febrile. What I will point out, for those of you familiar with giving filgrastim, this is a different dosing than we normally use, 10 mics per kilo. And that's going to be sub-Q every day until you get your levels up, etc. Now, for a mass casualty, and maybe for strategic national stockpile or your country's stockpile, you can think about pegylated filgrastim or pegfilgrastim. 2 doses, 6 milligrams each, given 1 week apart. Yay, right? That makes sense. Give them a dose, send them away. They follow up with some CBCs, and then you give them their second dose. Sargramostim, used in the rest of the world quite frequently, not quite as much in the US. And I have given you the pediatric dosing. We're not going to delve into pediatrics in this talk. Again, this is a very condensed version of a much longer course and much longer courses. Can you have adverse reactions? Absolutely, you can. You can have bone pain. Splenic rupture is rare, but it can happen. We're no longer using the category C's anymore for pregnancy. It's risk versus benefit. ARDS, all kinds of things. However, if you're trying to keep the patient from having infection when they're dropping those, all of their counts, when they're pancytopenic, neutropenic, it's probably more important for them to have the filgrastim and or colony stimulating factor. Rhamaplastim, also US FDA approved, essentially building up the platelets. I think there's also some work being done with TPO, EPO, and there are so many biosimilars getting approved just very rapidly that we've just thrown in this category. And obviously, we could all use off-label uses for biosimilars. I think that's a given. Now, the nice thing, if you have a pre-filled auto-injector, boy, that's a great thing. Now I'm going to carry on. I'm going to talk about this briefly, and I'm going to give the caveat to this. This is a very small cohort. No one would disagree with that. 31 individuals. This is a look at accidents, and there's a few more that could be updated in this. As you can see from this publication, that is an old publication. It's one of our REACS publications, in fact. In 31 transplants, 27 patients died, 4 survived. Okay, that does not look good. There are reasons for that. Anytime you do a transplant, you need for that individual not to have burns, trauma, organ dysfunction / failure. And you look at these individuals, they absolutely had reasons. Graft versus host disease, host versus graft disease, for those of you if you're not familiar with that. The ones who survived, had the grafts, they rejected their grafts. It's a little misleading. So I want to throw in the caveats. This is a small cohort. There's no significance to the statistics on this. You cannot do that with this cohort. Again, we mentioned the other things with the other organ failure, et cetera, and confounders. There are so many confounders in this. So go to either RITN website directly or go to our website. We also link up with RITN and we work with them. We love them. They do great work. All right, so in summary, and hopefully I'm doing okay time-wise, and that wasn't what that nice music was for on my phone. So it's very important to be able to triage and know what the magnitude of casualties is going to be, particularly with a nuclear detonation. You've heard me mention that a few times now. If we gave this course 5 years ago, you would hear us talk about an IND, mention it a time or two. This time in our world, it's important to talk about detonation. It's important to talk about state-owned detonation or non-state-owned detonation or tactical nukes. Also, of course, more common or could be more prone to happen more commonly, that's the right way to say that, nuclear power plant accidents where there's a release, there's an excursion. So we have really changed the way we look at how we teach now. We didn't really have time to put it in today's course, but you can certainly cruise our website, lots of free materials, and come to our courses, and we'll certainly get a lot more in the weeds. Triage, key. we all know this. Triage is key. No matter what you do, if you're related to medicine, you got to be able to triage. You already know the medical aspects of how to treat these individuals with some caveats. Once we get some of these things that are in the research pipeline, emergency use authorization, which we did learn from the pandemic, hey, that's a thing that can happen. We will hopefully have more in our arsenal to be able to treat these. But you already know how to treat the other basic medical issues. Be aware that these cutaneous injuries may occur. So RITN has now for the past few years teamed up with the American Burn Association. Great pairing, love that. We have also with NNSA, I'm going to digress for a minute because I think I'm doing okay on time, but we at NNSA and the Nuclear Emergency Support Team, the NEST assets, have taken a stance to lean forward with the current global situation, particularly with the Russian invasion of Ukraine. It is a global, thank you, Megan. It is a global situation that bears close watching. Even if something isn't purposefully targeted, it can be accidentally hit or it can be purposefully targeted. This is with this stance of leaning forward, NNSA gave us the opportunity to work with some of our burn colleagues, some of the RITN colleagues, many different agencies, HHS, state, you name it, USAID previously, where there's been a lot of work done to develop humanitarian kits. There are publications coming out on this. I'm not going to go into details. There won't be details put in the chat. There will be more information on this coming out, but essentially for blast burns and for acute radiation syndrome. And a lot of you are already going to, think ahead of me and go, ooh, but so many of these medications are cold chain. Yes, they are. And that does cause some problems. However, when your front lines extend everywhere, you may have certain places where you can keep things and get them forward deployed and maintain that cold storage chain. So we're looking at a different world, different way of sadly conducting warfare. Our medics are being targeted on purpose. There's no Geneva conference law that exists anymore, sadly. I digress. I'm getting back on track. So obviously, psychosocial distress. We're not just talking for the patients. We're also talking about the caregivers. A shout out for my dear friend and colleague, Dr. Ala Shapiro. She was on call during Chernobyl. She's a pediatric oncologist. She worked at FDA for many years. She has a fascinating book that talks about her experience as being a doctor during that time and being a doctor on call. Plus, she's in a lot of documentaries and she's in a movie, and she's a wonderful person. So that is another good reference for you to read from a firsthand account. And talking about a lot of the psychosocial distressors. Our Japanese colleagues post Fukushima and the East Japan great tsunami and earthquake have also written about a lot of the psychological distressors that affected not only the communities but the responders. This maybe is a bit unfair. Countermeasures, okay, technically are lacking beyond bone marrow, but there are other things that are being researched and I think would be on a fast track to an EUA if needed. And thanks to our colleagues at RNCP. We can test for this, we can detect it. This is so much easier than biological or chemical, so much easier. Now you're going to hear tomorrow the chemicals, so much tougher to deal with. Biological, we dealt with COVID, right? Not that they're fun, not that they're easy, but this, relatively speaking, is a lot easier. Always save the patient's life first before thinking about the radiation. Please, please, please. You'll hear ways later on today how you can protect your caregivers and the facilities from becoming massively contaminated. You don't have to shut them down, etc. Boy, I'm really droning on, so I'm sorry. I'm going to wrap it up. If they're only exposed, no risk. If they're contaminated, there's some risk. We had somebody recently say, oh, well, REACT says that there's never been an incident of a caregiver with a clinically significant exposure. I'm going to say that that was a little misquoted. There, in the history of the documented accidents, there are not first receivers who have had a clinically significant exposure. There have been first receivers, and Chernobyl is one of our #1 examples of that. So if you're a first responder, that can be very different. If you're a first receiver, that is a much different way of looking at it. I think I've said enough. I think I've done enough. We can handle some questions if there are some. Triage, surge. Please go to our website. Please put this phone number in your phone. This is our after hours number. If you call this, it will go through the DOE Oak Ridge Operations Center, and they will connect you with one of our administrative assistants who will be getting some intake information from you. Then you are going to get the full team of REACTs on call with you to take care of whatever questions and or needs that you have. We're also on call 24/7 to respond anywhere throughout the US and throughout the world. So with that, I'm going to leave you with the slide with our RadMed app and our QR code. You can download that quickly. We're about to do some revisions with that. Also, our website, again, lots of free resources. We do have them in Ukrainian and Turkish and Spanish. I think that's all we've got right now, but a whole lot of references for you out there. I'm going to go ahead and show just one brief page of references. I took a whole lot of these out, but here are just some of those, and then I'm going to go right back up to this one. Were there any questions? And I'm trying to find where I can pull that up. So
I can read them off to you, Dr. Hiddens, if you want to keep your slides up.
great, thank you.
The first one says, do you mean that waves cause less damage than particles because they're bigger? Talking about the difference between those single and double strand breaks and which one's more likely between our X-rays and gammas versus our alphas.
Okay, can you read the second half of that again?
Basically, the question is, why do the alphas cause more double-stranded breaks?
That is a good question, and Dylan, please feel free to fill in. But it is the fact, and this goes back even to the radiobiology of it, that energy with an alpha is deposited like that, like so. Bang, deposited, right? Whereas X-ray, gamma ray, it's going to deposit a little, it's going to skip, it's going to deposit a little, and skipping may be the wrong term. So for your purist out there, you may not like that, but they're going to just give off a little bit of their energy. They're not going to cause as much damage. The most part of their damage is going to come from those free radicals and that indirect action. So did that answer the question? Or yeah,
I'll go a little bit farther on that.
Sure. Okay, thanks.
To get more on the physical side. It's not that the alphas are bigger or heavier. That's part of it. More so bigger and heavier. They have that massive +2 charge on them. So they're very likely to interact. All their energy gets deposited much more close together. And so when we have that, they're more likely to interact directly kind of in those DNA change and cause that direct action. The gammas and X-rays are much less likely to interact So because of that, because that nuclear package is so small compared to the overall mass of the cell, they're more likely to interact indirectly, which means they're more likely, if they interact in the cell, they're going to cause those free radicals. Then those free radicals will go on to cause that DNA damage. So it's all about how efficient they are at imparting their energy. If you want to look more into it, we'll talk a little bit more about it later. It's a property called LET, or linear energy transfer, that's really going to cause one or the other.
Yay! Thank you, Dylan. Yeah, that fed right into it. I actually found where my chats were hiding, so they were hiding out. So I also see. I assume most of the people in the green zone, most likely to recover, are generally farther out from the center. What is the overall geographic distribution of that kind of injury relative to the center? That is an excellent question. Okay, this is going to sound like another shameless plug, but please come to one of our courses. So we have actually included medical implications of a nuclear detonation into our courses. And I'm going to give you the classic and always best answer to almost every question. It really depends, but I'm going to elaborate on that. I'm not going to leave you hanging. In US terms, all right, first, it depends on the yield. It depends on an airdrop or ground burst. And I can't delve into all this because there's so many caveats, but I'm going to give you a good reference. In fact, I might even actually have a picture I can show you guys, if you'll pardon me stepping out of the camera view for a moment. I had it up here earlier. And I'm not finding it, of course, because those of you who know me have seen my desk. So let me get back to the question. All right, so it depends on the yield. It depends on the height of actual detonation. It depends on ground and or water, and that gets really deep, and no pun intended with the water. It also will depend on the geographic and atmospheric conditions. So as you see, this is a really deep and multi-layered, it's a great question though. So what I'm going to tell you as a generality, not taking all of those specifics into consideration, let's say if you were at Hiroshima when the bomb dropped, if you were 2 kilometers out and you were in a somewhat decent structure, you survive. Same, we can kind of extrapolate to today. Let's fast forward. If you're in the bottom garage, underground, no open entrance to the outside of the parking area in a high-rise building, modern day times, and you are, let's say, 2 miles, mile and a half, 2 miles, let's go with 2 miles, a couple of kilometers, you have a very good protection factor. So I refer you again to the Lawrence Livermore National Lab. They have some great videos, great graphics. Also, FEMA has put out very recent guidance for response to a nuclear detonation. They've put out guidance for the first 72 minutes response. Every first responder ought to have that. Also, they have put out communications for a nuclear detonation. So 3 very recent, very practical, brilliantly done publications from them and Lawrence Livermore. Can't say enough about those. So I think that probably is the best answer I can give you in the amount of time we have. Now I see, let's see, where do you see the value? Sorry, I've got my chat over here. Where do you see the value of a community reception center other than to, Dr. Balaji's typing an answer. Hopefully we'll give pretty much the same answer. But I see the community reception centers as being critical. They're hugely of huge benefit. Please go to the CDC website on community reception centers. Part of what they would do is not so much do those ad hoc setup, triage, and basic first aid type stuff, types of things, but they're going to be able to get intake histories, demographics, how close were you to the blast, yada yada. They're also going to be able to weed out those who are, maybe they're grossly externally contaminated versus not so much. They're going to be able to put people into different bins to help separate them, yet not separate families, and to have start the process for the family reunification. They're of huge benefit. Please go to the CDC website. And if our good friend and colleague, we have lots of good friends and colleagues at CDC, but I do know that, and she's retired, but she's still doing work for them. Dr. Adela Salome Alfie did a lot of work on the website with that. So please check that out. I think the next one, LD 5060 curve demonstrates how medical intervention shifts to the right. The dot shaped markers on the graph with numbers beside them signify. Those are actually, and I keep meaning to put a reference in there. Those actually show the number of actually, I'd have to go back and look at it. I think that that's showing the number of different gray and populations throughout that. But again, the takeaway on that is not to memorize numbers. Know that LD 5060, which is designed for people to be a mostly whole body exposure, is 3.5 to 4 gray. And that is real readily agreed upon. Bring me 10 references, and that is what you're going to see most quoted on that. The key is just knowing that we can extend lives for a longer period of time with modern medical care. It just boils down to that triage area as to whom you can really get long-term survivability and whom you can't. And that is really a tough question. And that's where it comes into play, that looking at that clinical prodromy or prodrome, doing the multi-parameter triage of, taking all those factors together. You can't just look at one thing and get an answer. It takes the whole picture. Please include suggested books in chat. Okay, I will do that. Medical logistics, ensuring ready supply of medications, PPE, et cetera, is most important. Have been empirically delivering care and response. Domestic, yes. Yes, I will let our colleagues from HHS really answer that. I think, and maybe even Jill can put some things in there. I'm not entirely certain, but our strategic national stockpile and the world learned a lot of lessons through COVID. We have learned that, okay, having X number of ventilators and X number of N95s was not enough. The whole pan flu experience and all the planning for the past decades for that really got, if you'll pardon the expression, just shot to pieces with COVID. And a lot of lessons were learned and a lot of lessons have corrected. So the Strategic National Stockpile in the U.S. Does have some PPE. Somebody yell at me if I'm totally wrong on that, but I'm pretty sure we've got some stockpiles of PPE. Hospitals have PPE, maybe not enough. Some things can be basic use for PPE. This I usually say in one of the later talks, but I'm going to throw it in right now. We had 2 incidents occur during the pandemic when workers were wearing the COVID just procedure mask, not N95s, just those good old procedure masks, where their masks were contaminated they weren't supposed to wear respiratory protection. Had they not been wearing their COVID masks, they could have potentially had some internal contamination, but those COVID masks stopped it. So a little bit of digression, we'll talk about that later today, but that's just one of those instances of, yes, you're right, PPE is very important. Discussion included on potential, and I know we're going to have to cut this here at some point, discussion on potential of dirty bombs. Um, yeah, with and I don't know if you'll touch on this later, Dylan or Megan, but dirty bombs are more of a hazard given, again, you have to think of payload or yield, if you will. So dirty bombs are, as a generality, and take this with some grace here, as a generality, are going to be more of a hazard to those close at hand. Dispersion devices can be more of a threat, particularly if they're not known, and a great case for that is Litvinenko. Also, another good dispersion, look at the Goiânia case. We'll talk about some of these, I think, later on. So I'm going to put you back on that, and I'm going to move on to the next one since we're running short on time here. How long does a fever last from exposure versus when do you start chasing down an infection causing fever despite prophylaxis? That is a very good question. When you see a fever initially from exposure and before you start seeing indicators of infection, I mean, that's a bad prognosticator. Timing wise, it depends on a lot of different things. Again, it depends on how much of the body was exposed or radiated, let's say, what the absorbed dose is. What body parts, is this homogeneous, inhomogeneous? So there's a whole lot of factors that go into that to not really give you a real specific answer. But if you see the fever before any signs of infection, know that that's a bad prognosticator. So just keep that in the back of your mind. And finally, danger in delaying decontamination and increased dose to those who arrive at the CRC. Very good question. And the danger in delaying decontamination for healthy people or non-critically injured people, sure. And we're talking radiation only. Now, keep in mind, tomorrow it's going to be very different because chemicals and or biologicals are very different from radiation. We're talking about radiation solely as an issue here. Delaying decon for a massive group, yes, you could spread to your CRC personnel. That's why they're going to go through portal monitors. That's why they're going to be hopefully kind of bend out into different areas. And again, I'm going to refer you to those FEMA documents because you can do dry decon. And dry decon, often people don't think about cutting off the clothes as dry decon. That is dry decon, essentially. You're taking off that outer layer. There are other ways to do dry decon. I will point you back to the civil defense videos back in the day where they show the guy coming home from work and he's been in fallout and he's casually just coming into the house and he takes off his hat and carefully places it down. He takes off his outer garments. He carefully places them in an area. And not that I recommend using a broom, but you can do some gentle brushing as long as you have your airway protected and your mouth protected. You can do some gentle brushing to remove some of that, or some very simple wet decon with some moistened towelettes, baby wipes, whatever you want to call those. And then I'm going to look at the rest of this one. Definition of first receiver, first responder. A first receiver is going to be those who receive the individuals from the first responders who are going into get bodies, to transport bodies. So as a rule, we generally look at law enforcement, firefighters, EMS as first responders. We look at our first receivers as that next line of defense at a facility. So hopefully that gets that done, and we'll talk a whole lot more about that. Why delay decon at all when you reduce dose immediately? Primary, I think is what's meant. Issue in these events is external exposure not committed in early stages. Yes, we will get into a lot more of this, but I'm gonna summarize this answer right now because I want this to be a take-home principle for all. If we're talking small numbers, absolutely. That's what you learn here is how to decon small numbers. You do it rapidly, but you're first and foremost, if there is a life-threatening incident going on, if they have a life-threatening condition, you can decon them all day long. If they die, it's not going to do you any good. However, that being said, a lot of these things can be done simultaneously. Anyone who's been in a trauma, you know how it's like a symphony. You get everyone doing all their things simultaneously. We're exposing the body. We're starting the IV. We're getting the labs drawn. We're assessing in that primary and secondary trauma survey. Yes. But the point is, don't delay decon, but delay decon until your patient is stable. Because if they're dying, I mean, if you're sitting there trying to clean off some deconned area, well, that's ridiculous. If your patient's dying, save your patient. You can be doing a lot of these things simultaneously. So hopefully that got that point across, and you'll hear more about that through the rest of today. And yes, I'll put some of those books in the chat for you. And thank you guys, a lot of great questions, and I know I'm busting my time. So we have a break, Dana, or whomever's working on us here.
Yeah, thanks, Dr. Edens. I think what we're going to do is we're going to take a shortened break for about 5 minutes just to give people a chance to stretch their legs and check their emails. And then Dylan is going to dive into some early dose magnitude estimation and radiation instrumentation right at, in my time, 11:22 a.m. Eastern time. And I'm sorry for everybody that needs to time math on that, but we'll see you guys in about 5 minutes. You can feel free to keep putting questions in the Q&A. And then I know our wonderful REX team will keep an eye on those and can type responses as they are available. Thanks so much.
All right, everybody, welcome back. Thank you for your time. I'm assuming everybody can see the screen pretty well and can see me. I've had some bandwidth issues in the past, so I'm going to go ahead and take myself off camera. If one of my co-presenters, that is to say one of my cats, comes up, maybe I'll give you a preview of them. Both of them are currently napping on the cat tower, so I don't think we'll have any interruptions today. So kind of moving from that, we'll start going on. This lecture here is going to be talking about radiation instrumentation, kind of how are we looking for, how are we identifying that radiation that we've talked about so far? How do we monitor for it? Kind of getting into that question we asked in Carol's lecture about why do counts per second matter. We'll start talking about how we go from those kind of steps into numbers that we can actually use. Once we do that, we'll start talking about the early dose magnitude estimations. That is every HP's either favorite or least favorite part. The early dose magnitude estimations are wrong on purpose. I say they're wrong on purpose because they're right on the orders of magnitude, and they give us that kind of first immediate medically significant time frame that we can say we expect this much dose, we expect this much activity, so we're going to start going down whichever procedure we have to go down to kind of prep for that. So I'll get more into that as we talk about it. Before I get too much over my own self, I do have no financial or commercial interest. You'll see the slide in every one of our presentations today. No one is kind of funding me. Everything we talk about is either what we see most commonly in the field or what you'll most likely be interacting with when you're doing this kind of work, when you're kind of looking for these different types of radiation or detection equipment. So we start talking about our equipment. There's a number of different things we can use, and there's a number of different reasons we have to use them. The first and foremost is radiation detection is difficult. Radiation detection kind of works off of those secondary effects of that radiation. Nothing that you as a person can do has any kind of effect into what you can see, what you can smell, what you can taste. You as a person make an excellent dosimeter, as Dr. Balaji will attest, as I will attest, having worked in dosimetry. You make an excellent radiation shield. One of the old guys I used to work with, he said, for me, it was time, distance, and shielding. For him, it was time, distance, and junior HPs. I didn't really appreciate that as a junior HP, but now that I'm more of a senior HP, I kind of appreciate it more. With that said, I don't recommend you use your dosimetric or shielding purposes. You really only get to use them once or twice in your lifetime, so save those for something important. Because we don't want to do that, we want to use these devices. They're going to kind of take advantage of those secondary effects and tell us what we're kind of working with. Those secondary effects that we're talking about are going to be either these excitation events or these ionization events, kind of what Megan was talking about earlier. When these interactions happen, that atomic structure gets either excited, and when they become excited, that kind of orbital electron goes to a higher level. At some point in time, that electron will fall back down to its ground state. Since energy can't be created or destroyed, that loss of energy has to go somewhere. It is given off as a photon of light. We can kind of collect and monitor for those photons specifically, and that will tell us how many events that we had. The other thing we'll be looking for is going to be those ionization events that Megan talked about. In this instance, we have some form of interaction with that atom. There is enough energy imparted to do more than just excite that electron, but to completely free it from that orbital shell. When we do this, we have that free negative electron, and now our atom has that positive +1 charge because it's now missing one of those electrons. So we can kind of take advantage of that difference in charge. If we put some kind of voltage across a wire, we can start drawing these two away from each other, kind of monitor how many of these ion pairs were created. That will kind of give us something to look back for as we start trying to find out how many ionization events we had, how much activity we're looking for. This is kind of what we're measuring when Megan talked about exposure, those ion pairs in gas. And when we talk about specifically counts per second, like with our devices that we mentioned earlier, this is kind of that first step. We see where those counts per second are, and we're going to start using that information relating back to one of our more referenceable numbers. When we're looking at these types of events and these types of detectors, we can take advantage of these systems really in any state of our matter, whether we're looking at the ionization in gas, which will be kind of like our GM detectors and our ion chambers, whether we're looking at excitations in solids and liquids. Typically, that's going to be one of our scintillation systems, and whether or not we're looking at any kind of change in chemical systems. The chemical systems aren't necessarily great for detection. There's one or two different detectors that actually work off of that. Our chemical systems typically are going to be used when we're talking about dosimetric purposes or after the fact monitoring. So as we're looking for any of that kind of stuff, we'll be using those techniques, those devices to move forward. So when we're trying to collect those, what we'll be doing is we'll be taking a survey, a radiological survey as it's called kind of in the industry. When we're doing those surveys, we'll typically have some kind of instrument very similar to what you see here on our screen. This is far and away one of the most common types of detectors that we've seen, whether we're working with other governmental labs, whether we're working with first responders, fire departments, and what we see in hospitals. There are a few different models very similar to this. Really what we're going to be seeing those differences there are some of the knobs are slightly different, kind of how they scale will be slightly different, but all of them will follow the same kind of general layout of these devices. So that first thing we're going to be looking for when we're doing our surveys is we want to make sure our detector actually works. We want to make sure the detector isn't broken. So things we want to do for is kind of check for any of that damage, make sure nothing on here is falling off or broken. Some of the big pieces to really look out for are going to be this initial kind of screen here. For especially our more analog systems, this screen is held on by a very light glue. If that glue kind of degrades or falls down, that glass can sink in. If it applies any kind of pressure to that needle, it's going to either stop the response or it's going to show an under response from that. These cables, since they kind of get coiled up and curled along most of the rest of the time, especially anybody who's worked with their iPhone chargers on the side of their beds or the side of their tables, where these kind of move over, can become kind of kinked up or crimped, especially if you have any kind of exposed wiring. You want to kind of fix that or exchange your cables out. That just adds more noise into the system. Do either over respond or under respond accordingly. And then probably the other biggest source of damage is going to come from this probe head itself. If you'll notice, or if you're familiar with these devices, there's kind of a mesh right here on this probe head. And behind that mesh immediately is going to be some kind of mica window, very thin film window, so that we can kind of pick up some of the alphas, some of the betas that are coming through there. Because this works on one of those gaseous chamber type systems, if we have any kind of puncture in that mica window, that gas will escape. We won't have good ionization chamber. We won't have good ionization or ion pair creation, and we're not going to respond very well. And then congrats, you have a very cool, very nerdy paperweight now on the table in front of you. Those are all the kind of things you want to look for immediately when you kind of pick this out of your cabinet, preparing to start trying to use this. Of course, you also want to install your batteries and make sure all that kind of goes in as well. The batteries install under this handle here and they kind of slip right in. There are these two, I'll call them champers on the side. Whenever we have this course in Oak Ridge, I'll say, go ahead and open it up. And a lot of people will open those sides up. Don't go in there unless you're doing calibrations or unless you want to make your calibration team very unhappy. Because I am the kind of nerd who likes to know how our things work and know why our devices work the way they do. Here's kind of one of those examples of those detector head chambers, kind of with and without that mica window to kind of show you what's going on. We will have whatever infill gas we want inside this detector head. Then that charge goes across that wiring in there. We pick up those different charges as we draw those ions and electrons towards them. That creates a pulse in our system. The number of pulses will directly correlate to how much activity or what kind of flux we're currently in. Once we've kind of pulled those devices out, we've made sure they've worked, we put our batteries in. The next thing you want to do is make sure that your devices are within their calibration date. Typically, they're calibrated either every 6 months or every year more appropriately. Just want to make sure that it's inside that date line. This is basically saying that we took this detector up to a known source and it read within our bounds of allowance for what this source should be. If our detector is out of calibration, let's say you haven't calibrated your devices in 2 or 3 years, you're in a hospital, suddenly somebody comes in as a radiological patient, you want to know if they're contaminated or not. You go in, open that cabinet, you say, well, oh man, this detector is out of calibration. Don't not use it because of that, but be aware that our readings are going to be very skewed or potentially very skewed. At this point, this detector really is going to be more of that go, no-go type of system. If you do take any kind of readings, make sure you write down what they had and make sure you write down that calibration date. Best case scenario, we can apply some back calibrations and kind of find out a correction factor for what the device should have been reading. But if this is your only detector and you're trying to find out, please don't let that be the stopping factor on calibration, so long as it passes that source response check that we'll talk about, I believe, in a few steps from now. Once we've done that, we've checked that, and our source and our detector is ideally inside that calibration. What we want to do is start turning this device on, make sure everything works. That first kind of response check we're going to do is going to be that battery test function. Make sure the batteries we put in were good, make sure they're applying the proper voltage so that we get the appropriate readout on our device. When you turn these devices on, we'll turn them on to their lowest setting, just simply turning off of the off function. We'll turn these devices on. In this device here that we have pictured, we'll notice that there is actually a battery test function on the knob right around here at 12 o'clock. You'll turn that to that battery test function, and then the needle should move within this range of battery tests that we have on the device. If, let me preview the next slide, we don't have that kind of function like this device does, instead we would turn this on to our lowest setting or our 0.1 time setting. We would then push that battery test button there that we see on the side, and then our needle should move and respond into that battery test zone. Once we've done that, we know our device is actually reading, or we know our device is actually working. We know that device is going to respond appropriately with our battery voltage. Now we want to move into that response check that I mentioned earlier. The response check is simply taking some known radioactive source, typically a check source like we have here with that small red coin. We have a known radiation source in there. We hold this device up to it, and it should start going off, or it should start reading that source. This tells us that, hey, we are actually responding to this radiation. We're not just taking a dead meter into a potentially active zone. We know we're going to respond to radiation. This is proof that we do. Once we've done that, ideally we want to start getting our background. Background's very important, and background will vary from place to place across the United States, across your town, and potentially across your building. So anytime you go into a new area, you'll be surveying, you really want to try and get your background counts there. The background counts will be taken away from whatever count you're getting to try and give you a more accurate reading. And this is accounting for all those radiations that are naturally in the world that Megan talked about in that very first lecture. Everything from the uranium, the thoron in the concrete blocks in the walls, any cosmic radiation coming from the windows, any kind of radon that may have seeped through the ground. This accounts for everything that we can't really take away just by order of being on the planet. Once we kind of get a good reading for that, we'll kind of mark that down in our notes or mark it somewhere we can keep track of it. And any reading we take later, we'll have that subtracted from it to give us something more accurate. Typically, our background will be on the order of single to a few dozen counts per minute. And if we're reading anything significant, it's going to be fairly negligible, but we should always account for it, especially on those lower end scales. Once we've done all that, we actually can now start doing our surveys. When we're doing our surveys, we're going to start on those lowest level of magnitude. So typically either our ×1 or our ×0.1 scale, depending on what model we have. Initially, when we're surveying, what we're looking for is the presence of radiation. So we're going to be monitoring on our fast setting, which is monitored in the universal symbol for fast of the rabbit, the hare, whichever one you grew up being told that it was. The fast and slow setting on these devices is kind of a, I don't want to say resolution time, because anybody familiar with devices knows that's a very important moniker. It really determines how fast, how efficiently that needle is going to move whenever we have a pulse. When we're on our fast setting, any pulse will cause a pretty big spike on that needle to jump and indicate that we're actually working with something radiological or there is something present here. Because that a very initial type of survey is to first find radiation, that's why we use that fast setting. The slow setting is on the other side, and if we're working in some kind of system or setting with either multiple HPs and everyone's devices are kind of going off and pinging, or we're working either in a more medical setting and the patient is very off-put or psychologically concerned about those beeps from our devices, we can also turn those audio signals off and just watch that meter. Really, it's going to depend kind of where we fall into that, how you want to do your own surveys. Once we can start doing our surveys, this is really where we're going to start interacting more on the medical side of things, especially if we're working in those medical settings or those first response type locations. This is a poster hopefully you're all very familiar with, and if not, you'll hopefully become very familiar with kind of how we recommend, the algorithm we recommend using when we're going through and talking about these patient treatments. So as we go through, we see that red is kind of those life-threatening issues. Once we've stabilized those, like Carol said, we get no points for a clean dead patient. Once we've stabilized that, we can start stepping in and helping out our medical team. That very first thing we're going to find out is, are we on the contamination pathway or not? So we're going to take our meter up, we're on that fast setting, kind of do a very quick survey. We're just looking for the presence of radiation or not. If we find it, good, we're going to move on to that contamination pathway in the purple. If there is not, we can continue moving on down those kind of exposure pathways. Like Megan and Carol have talked about, if we have exterminate or contamination on those outer clothings, we always want to cut those off, kind of bag those, tag those, put them somewhere in some storage facility outside and away from our location. That's going to help us keep those background rates as low as possible, give us a good kind of measure of what's in the actual room and on our patient. And if we need to do labs or any kind of surveys later, we can go back, pull those, and run either gamma spec or any kind of identification procedures on those. Once we've gone through that, ideally we want to start determining our radiation type, whether we're working with those alphas or betas or gammas, identify that contaminant if we can, and then start going into our surveys and our documentation. When we're working with these, ideally we're going to know what we're working with. Typically, if we're coming from some kind of national lab or governmental facility, our patient will be accompanied by somebody from that facility who will give us a rundown and a history. Ideally, if we're working with a patient, they'll say, hey, I was working with an americium glove box, and they'll know exactly what we're working with, and we can get straight to those points. If for some reason we can't, or that patient is non-responsive, or we just don't know what we're dealing with for any number of other reasons, there's a few things we can do kind of using those probes and the basics that Megan talked about to start getting an idea of what we're working with. The probe hebs, thankfully, and basic physics will allow us to kind of determine and discriminate between alphas, betas, and gammas. So if we have that contamination source, and you can do this with a coin source at home before we do this ideally on a patient, we know that the alphas are only going to have a few centimeters of distance in air. So if we're getting counts on one of our individuals on skin or on their wounds, and we pull back just a few centimeters, and we start losing 90, 80, a very large percentage of those counts, we're going to say that, hey, we're probably dealing with those alpha radiations. The mnemonic for that is that both alpha and air start with A. So if you pull back and that air is enough to attenuate it down, it's probably dealing with an alpha source. If we pull back a few inches and we're still getting counts, we know that the alphas wouldn't get that far, so we're probably not dealing with an alpha count in this instance. If we pull back a few inches, we're still getting counts. We're probably dealing with some kind of beta or gamma emitter. So we can discriminate between those with another fact that Megan talked about. We know betas are attenuated by either a sheet of paper, a few sheets of paper, or like a little bit of plastic epoxy, some kind of small thin metal. Thankfully, the back of that probe head is made out of aluminum for the most part. That will attenuate a large amount of those betas away. So if we pull back those few inches, we still get counts. We can turn that probe head over. If the back of that probe head attenuates all of our counts away, we're probably dealing with a beta emitter. The mnemonic for that is that the back of the probe head and beta both start with B. And if we turn that probe head around and our counts don't really change at all, and those counts and those radiation kind of go right through the meter, we're probably dealing with a gamma emitter. The mnemonic for that one is that goes through and gamma both start with G. So we can kind of start getting a little bit discriminatory. Now, if we have some kind of mixed field or mixed contamination, this can get a little bit iffy. especially since any alphas will hide under betas and gammas pretty good. So it's not a surefire way, but it's definitely something we can do in that kind of immediate term to start looking at and getting the idea of what we're working with. If I back up a few centimeters and I only lose, let's say, a third to half my counts, I know there's probably a gamma component. And if I'm reading from more than 5 or 6 inches away, I'm probably dealing with some kind of either high beta, potential, most likely gamma. So a little bit of finesse comes into it as we start working into those points, of identifying what we're actually working with. As we're actually doing these surveys and going through, we really want to start being systematic from this point forward. So we want to start moving, we say 5 to 8 centimeters, which is about 2 to 3 inches. Really what we're talking about here is you want to go about 1 width of that probe head every second. A lot of people really like to try and stop once they start hearing those beeps and try and get a count on those meters immediately. We highly recommend you don't do that. You kind of continue on, notate where your counts go up, notate when your counts drop back down. That's going to give you kind of the idea of the whole suspect area if we have something more akin to a spill as opposed to a hot particle or some kind of fixed contamination. If we continue on over that until our counts drop back down to backgrounds, we'll kind of find the entire area, and then we can go back over, switch into our slow mode, get a very good quantitative count on what our numbers are starting to look like in that area. That's what I'm talking about here. We can switch over to that slow meter. That's going to really make that needle rise a lot slower, a lot more systematically, and especially on these analog systems where they jump up on the order of thousands. It'll give us a much better readout, kind of an approximation of what number of counts we're actually dealing with and working with. Moving into kind of going from our surveys into how we're accounting for our individuals in general, we'll move into dosimetry, which is where I spent the first 5 years of my health physics career getting involved in. Kind of starting from the oldest technology, moving into more current ones. We start out with these pocket dosimeters. These pocket dosimeters pretty much fit in that kind of shirt pocket or lab coat pocket that we have. They typically clip on the same place you'd wear your normal dosimetry. They work based off this small ion chamber in the center. They are calibrated with a very thin needle to a scale. Because this whole thing is kind of transparent and works off a lens type system, you can actually get an immediate read in the field by taking this off your chest, holding it up to a light source. When you look through that lens, that needle will be superimposed over some graph like we see here with our Miller-Ronkin scale. And you can get an idea of how much dose you've gotten on that job so far. As kind of the ionization events happen in that chamber, that kind of volt pressure changes, that pushes that needle to one side or the other, whichever you're calibrated for, showing the dose that you have acquired on this job. There are types that can't be read in the field, have to be brought back to your actual RadCon office where they'll kind of take the readings there and tell you how much dose that you had. Regardless of the type of either immediate or indirect read, both of them suffer highly if you're in any kind of humid or high moisture environment. And the really bad part about these is they're highly sensitive to any kind of percussive force. That needle's very light, very sensitive. So if you're taking off your Tyvek and it falls out, hits the ground, that data is going to be very skewed. So very important to kind of keep up and track with those kind of pencil dosimeters and just be aware of their placement on your body due to that fact. They are very reliable. They used to be cheap. I've recently been told they're not that cheap anymore. But most of the time nowadays, these are going to be our backup dosimeters. Going into more familiar territory for some people, what I initially started off with very shortly are the film badges. These are typically a photosensitive film contained inside a light-proof packet. With these ones, as those ionization events happen, this is more kind of that change in chemical system I talked about very early on in this lecture. Typically, these are some kind of silver halide crystals or something similar. When we have those ionization events come in and happen, they actually break those silver halide bonds, pretty much turn into metallic silver. We get a discoloration in the different quadrants of our film badge. The amount of discoloration correlates directly to the amount of dose that was acquired by this dosimeter. Because now we're working in this quadrant system, we can put filters on 1 or 2 of our quadrants, say stuff like lead, tin, aluminum, plastic, And if we can start comparing these different quadrants to each other based on the attenuation rate of those different filters, we can start getting energy dependence of any kind of gammas and X-rays that came in and interacted with these dosimeters. Some of the kind of downsides to these are going to be that kind of fogging that can occur from either high temperature or any kind of just general exposure to light if it sits on a table for too long, especially under UV lighting, any kind of mechanical pressure. And then fading can also occur as those kind of bonds kind of reform or come back in if we're talking with other types of film badges. So any dose that we might have acquired, say, early in Q1, if we turn our dosimeter in late, may have faded off and kind of blurred out into the background. Where I spent the majority of my time in dosimetry, and what I think a lot of people are familiar with, especially if they've been in dosimetry for more than 5 years, are going to be these thermoluminescent dosimeters, more commonly called TLDs. These are typically a lithium fluoride crystal that we have very similar to those film badges set up in some quadrant system or some other system that we can use to do all the things that we wanted to do with those film badges. We can put different filters or films in front of them. We can get that kind of energy discrimination from those. These are more sensitive and can monitor for betas as well. The way these work is we have that lithium fluoride kind of crystal, and then on purpose, we've put some impurity in that crystal. That being, when we have these excitation events, our electrons get excited, they escape from those lithium fluoride atoms, they get caught and trapped by those impure additives, by those dopants. The reason for this is at some point later on, we can heat these crystals up in a process called annealing, basically putting them in a highly specialized oven. That thermal energy kind of re-excites those initial electrons. They excite to a higher state and then fall back down to their home states, kind of resetting that chip entirely. When they fall back down and fall to their home states, like we mentioned earlier with those excitation events, that gives off a light. Depending on the amount of light that we find in our system, we can say how much dose was acquired by these crystals. Not that we knew at the time, but the con for this is that we can only really read a crystal one time for an instance of dose. So if you take this crystal over your entire Q1 exposure, I can read it one time. If there's any kind of anomaly in that system, that's too bad. That dose has become anomalous. Some other downsides, these are also very sensitive to any kind of presence of moisture. They have a process, if you have a significant exposure, they have a process called bloom, or for the first 4 to 8-ish hours, they might over-respond. And they also have a process called fade. Like we mentioned with those film crystals, just as those trapped electrons generally over time just fall back down to their home states naturally. We don't get to catch that light given off, and so that kind of becomes lost dose. Depending on the age of the crystal, those problems are either more prolific or not as bad for our newer crystals. Since most of these have been made 20 some odd years ago, it's kind of problematic occasionally. The newest type of dosimetric methods right now are going to be these kind of OSLs. OSL stands for optically simulated luminescence. These are typically aluminum oxide crystals, and they work very similar to those TLDs. Very same way that we have an impurity added on purpose to kind of trap those electrons. The big difference, instead of a fancy oven, we now shine a small green light onto a portion of that chip. That green light will excite a portion of those trapped electrons. When they fall back down, they give off a blue light. We kind of collect that the very same way. More light means more dose. Our fancy algorithms will tell us how much. Some of the big advantages over the TLDs, because we're only exciting a portion of our chips, we can read these a number of times over the wear period. So if you go into a job, do something you're not sure you should have done, we can get an immediate read off that dosimeter, and I can give you the exact same dosimeter back. Not that it's great to try and do dose mapping with your dosimeters, but it is an advantage that we can have in specific instances. They're more sensitive to kind of the energy ranges, so we get more information off of that as well. And depending on how you like it or not, these most often get sent off to kind of their parent company, which just is another advantage that we can chalk up to benefits of the technology. That all kind of accounts for how we're monitoring and how we're looking for that kind of dose estimation or those hard numbers to give us activities, to give us how much material we're dealing with. The rest of this lecture is going to be saying, how do I use those numbers that I found to start talking about how is this going to affect my patients, my team, my rad workers? So this is where we kind of move from that immediate frame, especially for any of these emergency accident situations. We want to do something that is reliable, quick, and efficient, and generally representative of our potential dose. If my individual really got 8 gray of dose and my estimation is saying, hey, I've got 12 gray of dose, we're expecting 12 gray, that's fine. Any treatment we would do for 12 gray will work for 8 gray. We don't want anything that would happen to say my individual got 8 gray and my estimation comes in and says we only have 2 or 3. So any of our estimations, we want to be wrong on the right order of magnitude, and we want to be wrong conservatively. So all the processes and things I'm talking to you guys about are with keeping that in mind. A lot of times, especially my more mathematically inclined CHPs, will look at me and say, hey, that's not quite right. You're off. You're overestimating by about 20-ish%. To which point I say, good, that's the point. So we can talk about how to get more accurate after everything's said and done. If I'm trying to wait 2 or 3 days for a bioassay to come back before I tell my doctor we should start doing chelation therapy, that's going to be a lot of uptake, a lot of deposition that could have been prevented if we had moved on in those early timeframes. So with that whole caveat, we're also going to try and use these estimations, especially if we have any kind of mass casualty event where we have a number of different responses or a large number of individuals coming in. Like Goiânia, Brazil, when their event happened, they had some 120,000 people show up to the Olympic Stadium. So anything we can do to start looking at our individuals, making these very quick kind of back of the envelope calculations can start helping us put these individuals into different categories. We know if they're less than 1 grade, they're not really going to be concerned. We can tell them to come back later on. 1 to 3, we might want to start monitoring. We know 3 to 6 is that really sensitive range. And then everything over 6 grade is going to need that immediate intervention. So we can start using these estimations, applying those to these ranges that we're familiar with, and we can start applying our resources appropriately, like Dr. Iddens mentioned. When we're looking at these, one of the first things we can start doing when we take these numbers, find all this information out, is start trying to find out what is our dose rate. This is more aptly going to be applied in our medical facilities, but could also account for any kind of point sources or potentially contaminated individuals if you're concerned or trying to talk down your team and staff about the threat. Megan mentioned radiation kind of works in those geometric patterns. So if we're ever concerned about our dose rate, we can find that out. And the only information we need is really going to be the activity and how much time we spent there. This gamma constant is going to be something you'll have to look up. You can kind of do shorthands for it. You can either look it up in the tables, in the handbooks we've given you, in the app that you'll download, self-plug, or you can call REACTS and we'll kind of help you find it out for you. So once you've found that or haven't given to you, we really care about that activity and the time. And we notice that it's divided by the square of the distance we are from the source. That really goes into show just how massive distance will come into play when we start talking about these radiological sources. For our dose rate constants, or especially for those gammas, we're really only going to be concerned for those gammas, and they only exist for gammas. Because betas can be attenuated by a few meters, but they also can't really penetrate that dead layer of skin very well, except for like high energy betas. We're not really concerned about the betas or the alphas from that kind of external standpoint. So for that, we really only have these defined for our gamma constants. The big 3 accident gammas are pictured here. And we can kind of see that our units can get very convoluted. So let's try and take one of our examples. Let's use the source that we had in the Yanango accident. A welder ends up with a radiography source, puts it in his back pocket for about 6 hours. Let's take that same source and find out how long do we have to stand near that source at about 10 meters or 30 feet to reach our annual dose limit as rad workers. So we know that our dose rate we're looking for is going to be A gamma T over D squared. We know how much dose we can acquire. So we do a little bit of algebra, identify and isolate for that time. We're going to plug in all of our known variables. My favorite part of physics is once you know everything, you just plug and chug the answer. And we find out that if we stood 30 feet away from this source for about 11 hours, we would get our annual limit of dose. If we start taking that on the bottom where we had 1,000 centimeters and we turn that down to a few centimeters representative of that pocket, that number goes down to seconds. We can kind of use this information, use this math to start kind of thinking about how we're going to work around these different systems. If instead we walk into a place and we know where our source is and we take one distance or we take one measurement, we can start kind of mapping out the entire area of concern that we have. Anybody's familiar with the only American soil fatal reactor accident? That was the SL1 accident. This is exactly what they did. They had a very good blueprint of that kind of reactor floor plan. They knew where the reactor vessel was. At the top of the stairs at the doorway, they got a reading and they mapped out the kind of dose plan of the entire area. So as they went and saw how they would kind of get in and get out, evacuate those individuals there, this equation is what they relied heavily on. Again, we see that our distance is squared, and that's going to play a massive account for that. That's why distance is one of the primary things we want to use when we're talking about how we're going to keep our doses low and keep our doses safe. Megan told you earlier with the inverse square law, if you double your distance, you cut your dose rate down by 1/4. So I'm the kind of nerd who likes to prove my math. I took 2 classes in college and I paid tuition, so I'm going to use that money. Let's prove that to ourselves right now. Little bit of algebra, we want to find out what our intensity 2 is at 2 meters away. Let's isolate for I2. Best part about physics, we have all the things we need. We just plug it and chug it. So if we double our distance, that 4 goes to 1. We've proven that math works. So that's kind of how we can use that. We can plan that out for any kind of number of systems wherever we're around. Doesn't account for shielding, doesn't account for contamination on the ground, but a very good thing that we can do in the early phases to kind of help keep ourselves aware and be kind of present on it. When we talk about those doses and those distances, I said the farther and farther we get away, the lower and lower it goes. Inversely, that should mean if you ever touch a radiation source, you get infinity dose. Because that's not how math works, and you would immediately just evaporate if you got infinity dose. We have to account for those kind of contact source or those contact doses. When we're doing that, again, all we really care about here is going to be this A in the activity and the T in the time. That S constant is going to be something we have to look up or something you're going to have to need a table for. So in our same table from earlier, we see that that's also given to us for our big 3 gamma sources. We'll see they're a lot higher because we don't really have any kind of distance factor on these now. And if you pay attention, our units are slightly different. Our exposure rate constant was in factors of megabecquerels. For our surface rate constant, now we're dealing in a factor of gigabecquerels. When we're doing the math, it's very important you keep all of your units the same or convert to the same units, or your numbers will be off massively. So that's just one of the things to kind of keep in mind. Some of the other factors to keep in mind are that these equations, these systems really work in approximations. Once we try to get more specific, that means somebody touched the source, their hand dose might be massive. How is their whole body dose going to represent that? You're a really good shield, you're a really good dosimeter, but you're a terrible point receptor. So kind of what that top picture is getting at is if you have some angle of radiation on you, that dose profile can look very different depending on how you're laying, how you're sitting down at it, how all that's going to be affected. If we start getting localized doses, that's going to offer problems for all of our estimations, potentially for any of our bioassays we might be doing. So all these things have to start being accounted for. When we're talking about internalized contamination, there's a number of other things we can do. The hard parts for this are now the same way I mentioned, alphas and betas are only concerns inside the body because that dead layer of skin protects them. That works both ways. If we have alphas and betas inside individuals, that skin, that muscle, that tissue is going to kind of be working against us to find them. So we need either very sensitive or very precise kind of detectors to look for that from the outside, or we have to take material from the body and start counting that directly. Things we can do with this are these whole body scanners, if anybody's ever familiar with them. The one on the right was Savannah Riverside's favorite. That was your yearly government mandated 30-minute nap time. We have to count for so long because of just counting statistics. We're looking for very low energies. We're looking for things that have to have pushed through. So that's why these numbers go up. Looking at thyroid counts, if we have any kind of iodine in that thyroid with that net counter, or looking for just your overall amount of activity in your body with that whole body counter on the left. Our lung counters are good, very effective pieces of equipment, but as this picture might show you, not very good field equipment. These are highly sensitive. Typically, they are entire facilities that have been built around these detectors to kind of shield out all of that radiation. Going so far as to get pre-World War II steel to build these rooms around, as these will pick up very low levels of radiation, having to count for those long amounts of time. So they're not great for that kind of immediate read, especially if we're looking for anything on that front. When we start talking about other things we can do, especially for any alphas or betas, we're really going to start looking at the bioassay counts. Particularly, that's going to be either urine analysis, fecal analysis, or any kind of material excised from the wounds if we're dealing with punctures, scrapes, cuts. This is everything from as simple as taking exudate and putting it through our counting system, or putting it into an LSC cocktail, which is a liquid scintillation cocktail. But these also can take time. If we're looking at that kind of common urine analysis prep from a routine sample versus our emergency sample, we see that our time frame really doesn't change much here. Between that routine and that emergency, we're only really cutting out maybe 2 hours-ish of time. Where the big difference comes is going to be the fact that in that emergency type setting, we're running overnight. So as opposed to doing sample prep on day 1, going home, coming back on day 2 for our collimations, and then depositions and counting on day 3, these are running overnight. So that's going to put a larger strain on your team, on your systems. Kind of accounting for all that, especially if we have mass casualty, becomes important. As we start talking about how all this kind of works, once those radionuclides get past those bodily systems, past the skin, into the mouth, into the nose, into the orifices, once it's broken that outer body boundary, we call that an intake. Once it's gotten inside your body, it has officially become that intake. There's a bunch of better mathematics, but like we said, we're here for that kind of early dose mag estimation. So we know that roughly half of whatever makes it past the body barrier gets taken into the bloodstream. Once it makes it to the bloodstream, we call that the uptake. So it's made it into the body. Now it has been taken up by the blood and starts circulating around through the bodily systems. Like we said, same thing with a bunch of numbers, but we're here for that quick, easy math. We know that about 10% of that initial intake will actually make it to deposition wherever it's trying to go. If that's something like strontium, radium, that's going to be a bone seeker. If it's something like iodine, that's going to be more along the lines of your thyroids. And there's differences in all of these, but we're going to use that rough 10% estimate as kind of that initial time frame. That intake, that number that we start looking at and acquiring that we just kind of estimated, we're going to have to compare that number to some reference level of intake. That reference level of intake is going to be a number set aside by your facility, by your incident commander, that says, hey, if we reach this level, if we identify X amount has been taken into the body or made to deposition, we're going to start doing our procedures. We're going to start doing countermeasures. Internationally, these are called operational intervention levels. And they're just saying, at what point do you mandate yourself to proceed further down these lines? Some of our different radionuclides are listed here. The ones more commonly invested with our accidents. We have our RLIs by the side in units of becquerels. And if you're familiar with what kind of emitters these are, you can kind of start putting into place. Our beta emitters, our alpha emitters have a much smaller number than something like our cobalt 60s. And all this is going to depend on how these move, where they target the body. That's how most of these numbers have been identified. A different kind of RLI that especially the more American-sided folks might be familiar with is going to be called the ALI. That's our annual limit on intake. This number will reference if we identify this much material in the body, we're going to have hit that 5 rem yearly limit. If you're working internationally, the limit is most likely going to be that 20 millisieverts or that 2 rem limit. So just knowing the difference between those is nice, neat, and if you ever respond across seas, being familiar with their limits is important. But so the ALI is going to relate to that 5 rem or that 50 millisievert yearly limit. So for example, let's say we had an inhalation event and we said that Megan inhaled 10 billion becquerels. I identify that Megan has 10 billion becquerels in her lungs. That means that Megan will have acquired 5 rem of dose from that tritium inhalation. The same works for all the rest. There are ingestion ALIs, there are inhalation ALIs. Most of the time, they're kind of similar. Sometimes they're different, just based on how that isotope is going to propagate through the body and how it's going to make it to the bloodstream. So that's all nice and good that we have something to count back to, but where are we going to actually get the intake data? How do I identify that Megan actually breathed in 10 billion becquerels of tritium? And the answer is I'm going straight to the source, which is going to be kind of the wound, if we have a wound event, the nose, or the nares, if we have inhalation, kind of thinking about all of those instances. Everybody who had a COVID test, I apologize to you, I was one of you. We are not doing that. When we're talking about that kind of reference between what we have in the nares and what we have in the deep lung, it's going to be very representative just on those outer nares alone. So when we're taking those nasal swabs, we really only want to go just around the outer edge of those nares. If we start going further back and doing those kind of COVID test depths, we're going to, one, make our patients very uncomfortable, but more importantly, we're potentially pushing radiological material further back into the nares, which is going to increase dose, just increase time that material is there before it naturally clears, which we don't want to do as professionals. So once we've collected that data, we've taken those nasal swabs, we want to add up our left and our rights if we have those. Differences between our left and rights can be numerous. Everything from there was directionality of blast to, hey, our patient might just be a nose picker. So we want to start looking at all of those. There are really good, really in-depth pathways that show how this material propagates from being breathed in into the deep lung. In general, about 10% of what we find in the lungs is what we see in the nares. So because of that, we can do some simple, efficient kind of calculations and start multiplying by 10 to get these numbers. So let's take an example. Let's say I take Megan's nasal swabs and I find, let's say 20,000 on the left, 20,000 counts per minute on the right. I'm going to add those together. I got 40,000 counts per minute on my nasal swabs. I bring my detector out. I pull it away. I don't lose counts. I turn that detector around. I don't lose counts. I know I'm probably working with some kind of gamma emitter. So in general, I'm going to apply a 10% efficiency, which is to say, because my detector is only, so let's say 2 inches wide, and I'm only reading from one direction of this 360 degrees of radiation, I'm really only picking up about 10% of the counts that come off of these swabs. So because of that efficiency, I'll multiply by 10 or divide by 0.1, whichever you like. That 40,000 counts per minute multiplied by the efficiency now becomes 400,000 disintegrations per minute. So we've gone from counts that we picked up on our meter to disintegrations, which is actually indicative of the activity, the actual material we have in those swabs or in those lungs. We can convert that to our becquerels if we so choose, and we'd see that's about 6.6 thousand becquerels. And that's what I found in the nares. I know the nares are about 10% of what's in the lung, so I can multiply by 10 again. 400,000 DPM times 10 becomes 4 million DPM. So I'm going to estimate that Megan has breathed in 4 million disintegrations per minute into those deep lungs. Again, with that kind of, if we like to work in becquerels better, that's 66,000 becquerels. So now I have that intake data. I'm going to look at that. I said, well, we think we have a gamma source, so I'm going to apply that to my inhalation ALI. I have 66,000 becquerels in those deep lungs. I know the ALI is 2 million becquerels. The ALI is 5 rem. I am significantly below any kind of concerned dose. That's kind of how all these numbers are going to work together. So when we take those counts, we find our activity, we use those rules of thumb, We convert that to an ALI. We can start comparing and getting an idea of how much dose we have. If we're not sure of the nuclides, let's say like in that instance, all I could identify was it was a gamma emitter. Megan wasn't sure what she was working with. I'm going to assume some different nuclides depending what I'm working with. If I have an alpha source, I'm going to assume it's americium 241. If I have a beta source, I'm going to assume it's strontium 90. And if I have a gamma source, I'm going to assume it's cesium 137. Ideally, they will tell you what you're working with, and everything will be fine and dandy, or somebody will come with you and tell you what you're working with. You can take those ALIs directly. In the case where they're not, we can make these assumptions, and these assumptions are kind of based on what's most prevalent. What do we see a lot of our accidents coming from? And among the other alphas or betas or gamma emitters, amongst their different types, which one's the worst to have internalized? We start looking at wounds. We have a number of different things we're going to look at as well. The ALI only really works for inhalation or ingestion. So when we start looking at our wounds, we have what's called a derived reference level. REACS has kind of identified this as its own unit. The same way an ALI gives you 5 rem from that inhalation or ingestion, the DRL will give you 5 rem from those wounds. The DRL is based on a number of different things, from how the isotope moves throughout the body, what organ it targets, and you can start looking at your chemical class as well if you know what kind of solubility it has in the body. If we don't, we're going to assume that weakest solubility. That's what's going to stay in the body the longest and what would give us the most dose. So using that weak DRL is going to give us the most conservative estimate of what we're working with. The big difference here is for our DRLs, we're already working directly with our bloodstream. So we're only counting for that 10% efficiency. Let's say Megan comes in with a wound. I count 6,000 counts per minute on her wound. I do that 10% efficiency. I have 60,000 DPM in that wound. I know I'm working with an alpha emitter, so I'm going to assume that we're contaminated with americium 241 until I get a later date. Compare that DRL to my RLI, which is going to be the DRL for americium 241 of 1,650. And I am orders of magnitude over that DRL. So I know that I'm going to have to start trying to think about any kind of countermeasures we can start providing, how we're going to start countering these agents and getting those nuclides back out of the body. Things to keep in mind, especially when we're working with these wounds, are that all wounds are just built different. Lacerations, scrapes, and punctures each bring with them different concerns with how that exudates, how that tissue is going to lay on those wounds. All of that's going to become a problem, especially if we're working with more of those alphas or our beta sources. So kind of keep that in mind. If we're doing our decon and counts go up, it's not necessarily that we recontaminated the wound. We might have just taken away some of the blood or tissue that was shielding our alpha sources, and now we see them better. Like I've mentioned, all of these things are taken with a grain of salt. These are kind of the weatherman effect of health physics. We get to be wrong, but we get to be just right enough. We're allowed to be wrong. This is all going to help us work with those medical professionals, with that medical team, as we kind of put all the pieces together to find out where we're going to fit, how we're going to start moving along with these individuals. And with that, I'll open it up to any questions. Hoping everyone's still there.
Actually, Dylan, we are running a bit behind. So
Yeah.
If you will take on the questions and leave those up with the answers so everybody can see that. And thank you. Thank you very much for that. And I'm going to go ahead, and I think I can get my talk in and get us back on schedule. If everybody will bear with me for just a minute here. I think I'm already sharing. And my goodness, what all am I pulling up here? So here we go. Can everybody see my slides?
We cannot, girl.
You cannot. What can you see?
Your smiling face.
Well, yeah, that's always a scary thought. Let's see. Should be screen 2. Tell you what, I'm going to turn off the video for a minute. I'm going to share screen 2. Are you seeing?
Let's see your desktop.
You can see my doggy?
Yes.
Yeah. Unfortunately, he's no longer with us, but a great doggy. So, all right. Now, are we good?
Looks good to me. Thanks.
Oh, fabulous. And here I can try and do the video part 2. Okay. All righty then. And Dylan will be addressing the Q&As, so don't hesitate to keep those going, but we're going to keep everybody on track. We're going to try and get everybody to lunch on time. I am just going to briefly, I should have done this in the beginning. Can you guys see this with me showing this? You know what? We'll leave it till the end. I got some of the books to show. So, but yeah, let's get through this. This is a very good topic. It's important. Not trying to sell you anything. We're going to talk about cutaneous radiation injuries and what cutaneous radiation syndrome is. And to do that, we're going to go through signs, symptoms, clinical phases, medical issues, diagnosis, and management. I'm going to go pretty fast on the things that you guys kind of either already know or we can go faster on so we can stay on time. And somebody give me a time hack when we're getting about 5 minutes out, if you will. Terminology. All right, we got a lot of terms here. And probably everybody's familiar with radiodermatitis, right? Radiodermatitis, great term. It is those expected reactions that we get with radiotherapy. Now, sometimes they can be worse than expected, granted, and that varies on a lot of different things. And fortunately, the radiotherapy is so much better than it used to be, to where we can have good tissue sparing, etc. Different topic, different day. However, I will throw in that one of the reasons I have such a passion for this area in particular, and my background's too complex to get through everything, but when I was doing gynecology, I really loved the surgery, the science behind gynecologic oncology. However, I felt the patients who get GYN cancers are the nicest people in the world, and it took a toll upon me. So I'll just leave it at that and say that while I found it fascinating with the surgeries and the science, the toll it takes for you is very tremendous. And my hat's off to everyone, all the clinicians and first responders and planners and everybody, public health on the webinar today for doing what you do, because we all know it can take a toll upon us. But at any rate, I digress. I saw a lot. Now this has been a few years. I don't want to date myself entirely here, but back in the day, we would get a lot of late radiotherapy injuries, per se. A lot of these women would come back and they would have these non-healing wounds and they would necrose, and sometimes we'd get osteoradionecrosis, the bone would necrose, we'd take them to the OR. Oftentimes they would succumb to sepsis, and we really didn't get great outcomes. Those still occur, but only rarely these days, fortunately, because our techniques are so much better. Now, I'm not going to be talking about that today. We're going to focus more on acute effects from radiation and damage to, primarily talking about skin. But when we get into cutaneous radiation syndrome, we can also talk about deeper organs, tissues, etc. And I'm going to use my crude pen, which you guys may or may not be able to see. If I held on to the point of the pen, I'm going to consider this my source. I didn't get any more good props, so sorry. But you know a little bit about a industrial radiography source, like shooting X-rays for a bone fracture, except it's gamma rays for a structural crack or fracture. And these often have a sealed source at the end of them. Well, these turn out to be a lot of occupational injuries, which is another aspect to my career, and we won't get into that one either. But these individuals, if they handle the tips of these, or if someone sees something that looks like it's all metal, though this does not, metal equals money, what are they going to do? Put it in a jacket pocket, put it in a pants pocket, coat pocket, etc. So those can turn into, if it's only fingers, a more localized radiation injury, what we now call a cutaneous radiation injury. But let's say it was a large portion of the body, and I was over that 6 gray, mostly whole body absorbed dose. I can have a cutaneous radiation syndrome. I mean, it's one of our, if not one of the largest organ systems. You can argue that out with yourselves, but extremely important and can be very deadly. Now, the only time I will use the term burns in conjunction with radiation are the beta burns. And Megan mentioned this. And the one case where we really focus on, boy, the beta burns were so severe is when we look at Chernobyl. With Chernobyl, 16 of the 28 acute deaths were from cutaneous radiation syndrome. That much of the body was affected. They essentially were in turnout gear and literally waded through depths of contaminated water, did not change out of their gear, stayed in it extended amounts of time, and died because of this. It wasn't the acute radiation syndrome that got it, it was specifically cutaneous radiation syndrome. So that's why I have in here maybe as deadly as the GI or gastrointestinal syndrome, subsyndrome of ARS. Because right now we don't have good treatments. We're working on them in research, but GI, once if you knock out your GI system, there's not a lot of coming back from that until we get some more of these interesting research projects approved. So I'm going to hop off of that. And the next slide you have seen, if I can get it to advance. Oh, come on. There we go. And it's just to go back and reiterate that if you have a high enough, mostly whole body homogeneous, even inhomogeneous dose, absorbed dose, you're likely going to have a decent amount of those individuals with cutaneous radiation injuries and perhaps cutaneous radiation syndrome. Now, predisposing factors. I love it when Dr. Balaji is lecturing, and he is on our panel, so he's going to hear me talk about him. But he is one of the most wonderful human beings and one of the most impressive scientists I have ever had the privilege to work with. But he likes to talk about ataxia telangiectasia mutated homozygosity. And I only giggle at that a little bit because for me, it was one of those things initially that it was like a PTSD back to taking the USMLE medical boards, because it seems like they always threw a question in on that. But these individuals lack the ability to correct, to repair double-stranded DNA breaks. So they are highly predisposed to having an injury because they're naturally, with this mutation, more predisposed to having, cancers, 100-fold, perhaps, we could say even more than that. Also, other things, though, and practical things I want you to think about. Previous radiation. That doesn't necessarily mean radiotherapy. However, if you, a family member, patient, have had radiotherapy, let's do prostate, for example, let's say 15 years ago, they may have a lot of issues with radiation proctitis, and you would not really want to irradiate that area again because it's not going to do as well. So that's one thought process for previous radiation. But think a little differently. What do our interventionalists do all the time? Um, someone with coronary artery disease is going to have a percutaneous coronary intervention at one point or another, let's say, if it's severe enough. And if one vessel is diseased, odds are another vessel may be diseased. So repair of these vessels each time would be another episode of radiation. So much so that in the 70s, mid to late 70s, FDA recognized a trend and went on an education campaign about fluoroscopy-induced cutaneous injuries and also other issues. Body habitus. If you've been in X-ray at all, you know that a larger body habitus, larger patient, you've got to penetrate deeper for those X-rays than you do for a more thin and petite person. And I'm kind of just shotgun blasting this out to you a bit. So I'll get us more into more seriousness here soon. So autoimmune disease makes sense, prone to sclerosing, fibrosis, diabetes, that's poor wound healing anyway, makes sense. All of these are, I think, very intuitive, maybe perhaps with the exception of ATM, unless you're familiar with it. And Dr. Biology, good on you. We love it when you do your talk on radiobiology. So acute versus delayed effects. For the acute, we'll go through this primarily in this talk. We'll also talk a little bit about these long-term issues, because these long-term issues are what make these unique, make these different from a chemical and or thermal type of burn. And another shout out to our NIH, NIAID, RC or RNCP groups with Dr. DiCarlo and her team is they do these great workshops, and one was looking at cutaneous radiation injuries and chemical injuries. So a great workshop you can find. Think that publication's out there, and if anybody from Dr. DiCarlo's team is on there, we'll try and put that in the chat, and I'll try and find it on the next break. So anyway, let me get back into track though. So long-term issues, we obviously have some issues with fibrosis, with atrophy. We have real issues with vascularity, particularly microvasculature, and re-injury, and this can occur not even just months, not even just years, but actually decades. So very unusual. The biggest caveat and the takeaway I want you all to get from this today is that these really difficult issues tend to occur at the necrosis threshold. And you're going to hear this many times throughout the next 40 minutes or so, or whatever I'm on now. But that necrosis threshold is at or above 25 gray or 2,500 rads. Okay, so just keep that in mind. We're going to come back to it. That is when these become really complex injuries. This, I'm just flashing this up here for a minute. Epidermis, dermis, and you're going to see the epidermis here minus the bottom layer of the dermis. I'm still not quite sure why our artist didn't do that, but at any rate, I only want to talk about the epidermis for the moment. You all know there's a rapid turnover of these cells. We get to that stratum corneum. It's a protective barrier layer. It sloughs off naturally. We talk about the stratum granulosum with these granules that contain histidine. Histidine converts to histamine. And usually, and I know I do have a large toxicology crowd on here, and for those of you who have sat in on this with me before, you know I always like to ask you, so what disease process is out there that is an overwhelming reaction with histidine? If you guys want to throw it in the chat and have a good discussion, you can, but I am always trying to fish out the answer. Scromboid, sorry, that was a bad dad joke or something, I don't know. So at any rate, we get a lot of inflammation with that second layer. Stratum spinosum, we have antigen presenting cells there. Basal layer, we have melanin. I like the fish, I love that. The basal layer, which helps us repair damage. Now, one of the clues to why these get so much more complex in some ways compared to chemical and thermal burns, and I'm using this a little loosely, if you will, give me some leeway on this one, but these endothelial cells, and if you recall, they were in that top 6 listing of cell types that are very sensitive to ionizing radiation. Well, they line every vessel in our body. This is a generic vessel in cross section, a little crude, I will admit, but these cells get injured. They die. They're going to swell up. They're going to pull away from that basement membrane. They're going to allow, the margination and activation of leukocytes. They're going to allow everything to get into the connective tissue, which is going to activate and degranulate these mast cells. The macrophages will get all kicked in. So a lot of inflammation, a lot of pro-inflammatory things are going to happen. We can't get too deep into the pathophysiology in this course, unfortunately. Come see us in the advanced course and we do a much deeper dive into it. So how do we repair? Well, we've got to have those stem cells, right? Having those are critical to this. I'm going to skip on to the next one because we're really trying to catch up some time here without a detriment to the material. But repair, how do we do a good repair? Okay, you have to have the progenitor or stem cells, right? You have to have a blood supply. You have to have an infrastructure. All of these things, no infection, no trauma. You must have all these things for good healing. Well, we have some real issues with these things, with these radiation injuries, because we're going to end up damaging some cells. Some cells will repair, but others will just die. And that's going to come with more inflammation, of course. We'll have some, and I know there's always a good debate on this. I personally go with the Greek, I guess, derivation and say apoptosis, but I'm sure apoptosis, everyone is thinking out there. But we'll have a few of those cells doing cellular suicide. And they won't have as much inflammation associated. However, with these, we have iterative cycles of inflammation. We have iterative cycles of free radicals, reactive oxygen species, reactive nitrogen species. Along with that, we've got the DNA damage going on. So all of these things go on to really create some complex issues when it gets right down to things. As with ARS, we can have that prodrome. This is that initial pro-inflammatory response, massive response. So we'll have some redness, we'll have some paresthesias, numbness, tingling, we'll have some itching and burning. If we took that source and stared at it for a while, we could get a nice conjunctivitis that would be very difficult to diagnose without knowing radiation was present. And in a lot of these situations, individuals will obtain sources and not realize they're radioactive. Latent phase. This is when the anti-inflammatory mechanisms counteract the inflammatory. Hopefully they equilibrate and the symptoms go away. However, the higher the absorbed dose, the shorter this phase is and the worse that prodrome is, and the worse all the signs and symptoms will be. Then we hit the manifestation of the illness, and it can be a spectrum of color changes. Primarily, we've already talked about that damage to the microvasculature. That is going to lead to difficulty in healing. We could become immunocompromised in these situations. And again, here you see that necrosis threshold equal to or above 25 gray. So, like thermal burns, depth and TBSA are important, are huge to this. Unlike thermal burns, we're talking about radiation. We're talking about the dose rate. Once that damage is done to that tissue, it is done. The thing to think about, and we'll get into this when we get into a case, is whenever you get a cutaneous radiation injury, you must think about deeper tissues, what is in the neighborhood, as I like to say it, because I think that really encapsulates that very well. So we could be talking about deeper tissues, other organs, etc. Now, like thermal burns, greater than a 10% TBSA, okay, that's going to maybe have more difficulty healing and may have more difficulty in survivability, perhaps, although we're much better treating burns than we used to be. But that threshold, these are the ones that are going to cause us the problems. They're the injuries that will have these recurring episodes of inflammation, some recurring free radicals and oxidative stress. They will evolve over time, and not like a frostbite evolution over a few months. I mean, these initially in the acute phases will see an evolution over about a month, but I mean, they can evolve, they can heal, and then reappear with or without trauma. And oftentimes when they recur, they're worse than the initial injury. And sorry, I get very passionate about this. I will pick up my pace. So this is the Metropole system. I blasted right through this earlier. So I like this, that they're serious or fatal category, greater than 40% TBSA. Well, yes, you know that from thermal burns as well. So let's keep moving on with this. These clinical thresholds are really, really helpful. We've actually looked at cases with video reenactments paired with dosimetry, physical dosimetry, and looked at the clinical picture. And the clinical picture has been really a better indicator for us. But now it can also trick you because these do evolve. This is derived from our National Council of Radiation Protection and Measurements, NCRP 161, which I do have as a prop, not as a prop. I use it every day. Well, not every day. I use it a lot, and it's right behind me. But let's go through this. And this is a modified version of this. But dose, 3 gray, 300 rads. You can see temporary hair loss. 6 gray, 600 rads. Well, you can get some redness from that. Distinguish it from a thermal burn. If you touch a hot stove, oven, what have you, fire, immediately it hurts. Immediately it's red. Fairly rapidly, it's swelling and or potentially even blistering. It takes extraordinarily high uh, doses of radiation to see effects in minutes. So that's a big discriminator there. 10 to 15 gray, dry desquamation, just sloughing off those cells. 15 to 20, moist desquamation. 20 and above, we can see blister formation. And again, to reiterate, and this really should be greater than or equal to 25 gray. And the timing of this is key as well. As you can see, we're looking at 2 to 3 weeks for almost all of these. The faster you see all of this, the higher that dose is. So we will go through this in a moment. Let's go through some treatment considerations, and let me keep an eye on time. Yikes, okay. So treatment considerations. These are, I will admit, not very well evidence-based because we don't have published evidence-based recommendations for cutaneous radiation injuries. We do have a lot of fairly well shown, if you will, techniques to try. And one is pentoxifylline with or without vitamin E, alpha tocopherol. Pentoxifylline, for those of you who aren't as old as some of us, Trintol, we used to use it, I mean, you can still use it for peripheral vascular disease, intermittent claudication. It happens to not only help increase some blood supply to the area, but can also show antioxidant and anti-inflammatory properties, especially when paired with alpha tocopherol. They tend to be synergistic. Some of our radiation oncologists will oftentimes recommend this for some of their patients undergoing radiotherapy. Growth factors. TGF beta is just one. There are many of them out there. There's fibroblast growth factor, so many of them out there. Nutrition, obviously, pain control becomes an issue with these, just like it does with burns, very refractory to all pain management techniques, with one exception we'll talk about here in just a minute. Constructs, BioBrain, Integra, all these different things work quite well. When you're doing your consults, remember to consult surgical oncology. While they may have dealt with late radiotherapy tissue injuries, they will have dealt with some pretty major ones. Though, again, those aren't as common as they used to be. Certainly radiation oncology, great start, dermatology, surgery, mental health, physical rehab, everything, OT, occupational therapy, PT. So all of these things should be taken under consideration, and especially that mental health, because these can be devastating injuries. When they're at or above necrosis threshold, which actually right now I would be asking you the question in person, what is that? And it is greater than or equal to 25 gray or 2,500 rads. That's your quiz for the end of the talk here. So what else can we do? We can do topicals. We can do non-steroidal anti-inflammatory drugs. We can do infection prophylaxis and treatment. Certainly if they're going to become immunocompromised, obviously you got to focus on that. And silver-based therapies. Silverlon is an FDA-approved device for these injuries. We don't have anything else that's approved, though there are a lot of things in the pipeline. Hyperbaric oxygen therapy. Here are all the things that happen with HBO therapy. What we have seen at REACTS is that it takes many more treatments than traditional wound therapy with HBO. We have seen 30 is really not enough. 60 may do it for you. We've had one patient who, after 120 treatments over a couple of years period of time, was able to get to the point to where he could have a wide local excision and have a lot of wound care to get some healing. So I'm going to keep moving on. Surgical debridement. You'll read in text, don't do surgery on these patients after 48 to 72 hours. Yes, if they are immunocompromised, you don't have to do that surgery. That would be a best practice. However, you do treat these complex injuries at or above what number? 25 gray or 2500 rad with surgical debridement when appropriate, grafting. When you get full tissue healing, pain goes away. Sometimes that's through grafts, sometimes it's with flaps, sometimes, sadly, it's with amputation. There's another alternative. Well, there are many right now, and this just scratches the surface. Again, come see us if you want to get deeper into some of this stuff. But stem cell therapy, stromal cell therapy. In the US, we do not have this approved or in clinical trials for cutaneous radiation injuries. However, go to the NIH clinical trials page. You will find lots of clinical trials for use of stem and stromal cells for thermal burns. It hasn't translated over, and frankly, there aren't really enough of these injuries that occur frequently enough or geographically close enough to get a cohort to put into a clinical trial. However, the French, the Japanese have done clinical trials with their delayed radiotherapy effects individuals with the stem cells from the French and stromal cells from the Japanese. There's a whole thing on nomenclature that I'm not going to get into on this. Just know that the stem cells, technically, we're talking more about bone marrow aspirate cells, adipose-derived, and these can be autologous. Stromal cells or stromal vascular fraction tend to now be grouped more into being called stromal cells. Sorry about that. Obviously, there are a lot of confounders. This is not a panacea for treatment. However, we have shown in their clinical trials, we did a humanitarian case with these as well, where the pain went away rapidly, generally within 48 hours. Paresthesias go away rapidly, generally 48 hours. They heal faster. They tend to not recur with subsequent re-exacerbations of the injuries. Not the panacea, holds a lot of promise. There's a deeper dive that can be done on this, but not for today. Sorry about that. Case review, Yanango, Peru. This is a very remote hydroelectric plant in Peru. High flow water goes through these pipes. There was a crack in a pipe. And this is 1999. This is a famous case. I'm sure many of you have worked or read this or at least heard this. But they had to do a rush repair job on the pipe on a Saturday. So the company said, well, let's do it at noon, that people will be at lunch. That'll be a lot safer to do it. We mentioned industrial radiography is like doing x-rays on bone fractures, except in this case it's gamma rays on structures, and in this case cracks in a pipe. So thank you, Megan. I can slow down a little bit. All right, so but we need to save time for questions though. So this is that source that I was talking about, people handle, and this is the point, a sealed source on this, and this is what people will tend to pick up and see as valuable. Hopefully you can see my cursor and go, hey, this is metal, this is valuable, I'm going to stick this away in a pocket. Well, on this particular Saturday, when this was being done, the radiographer who had this type of device, this looks similar, with this type of a source, and at the day of the event, it was an iridium 192, 37 curie for our US crowds, and 1.37 terabecquerels for our international group source. So the radiographer shows up at noon to do his study to see if these cracks are repaired by the welder. Welder was not done. The radiographer leaves this on site and goes off and does some other things. Well, that's a big safety violation right there. It's got a radioactive source. It should not be left on site. At around 4 o'clock that afternoon, the welder and happens to find this source at the site and looks at it, sticks it in his back pocket. Fortunately, he was wearing some loose denim cargo pants, but he spent 6 hours with this in his pocket. 3 of those hours he was, welding in a pipe. So some close contact, not necessarily direct skin contact. But as little as some of you may know, or as a lot of you guys know, we're looking at a pretty bad situation. So the welder starts having some pain. It's time for him to go home. He goes home at 9 o'clock. He rides a bus, by the way. Everybody was okay. But he rides the bus. He gets home, takes off his jeans, tosses them in the floor. He shows his wife because he's starting to have a little pain, a little itching. Yeah, something's kind of bothering me there. She thinks nothing of it. He goes off to see his doctor because it's really bothering him. She both squats and sits over those jeans with the source in the pocket so she can breastfeed their 13-month-old, about 10 or 15 minutes. He comes back. He starts thinking, hey, maybe there's something to this. My leg is hurting more and more, and gee, I had that thing in my pocket. So he takes the source and puts it in their outdoor restroom. So now we're going to switch back to the work site. The radiographer shows back up at 8 o'clock with his assistant with the survey meter, and he reels out this source, which once this source comes through the tubing out of the shielding, that meter should go off, and it did not. So they made the assumption, so many have done, oh, well, it must be broken. It didn't go off. So they go ahead to develop those films. The films weren't exposed. So they now have 2 very strong indicators they don't have a radioactive source. They spend from 8 p.m. until midnight doing who knows what until they notify the company. They notify the company very quickly. The company realizes, gee, this is going to be bad. Let's start off. Who was at that site? And they go to the welder's house. And they say, hey, by the way, did you happen to see this? Oh, yes, I did. Let me go get that. Well, they had meters too, and they knew theirs worked, and they pegged out. So they have him throw it in the street, throw a rock on it just to temporarily secure it until they could get things taken care of. After talking to this guy, the next day he goes to their cancer hospital, like our RITN network. I had more shout outs for RITN. But they take him to the nearest cancer hospital. Day of admission, well-heeled, well-nourished, not a whole lot to see on that leg. I think we'd all agree. Day 2, he's got blister formation. Day 2, remember we said blisters came in that chart. Oh, anywhere from 15 to 20 gray on up, but that's at 2 to 3 weeks. So this is not good, obviously. Let's keep going with this. Day 6. I don't care if you know anything about radiology. We're going to tell you these are his 2 thighs in cross section. Pretty easy to tell the affected one. You can see all the edema, all the swelling present. That's at day 6. Day 24. These will get graphic. I did surprise a group recently when I had all the pictures on one slide at one fell swoop, and so sorry. But yeah, these will get more graphic. If you don't want to see them, look away. Please do not take pictures of the patient pictures. Please do not do screenshots of patient pictures. I won't say it again, but please do not do that. So day 24, he's starting to have paresthesias. He's having the spectrum of color changes. You're starting to see everything, some dry desquamation, moist desquamation. Day 28, deep ulceration. Day 28 is when the IAEA team arrived, including our own Dr. Ron Goins. Which is another reason why we ask, or actually demand, do not take pictures of our pictures. We have permission to use these. Some of these are ours, some of these are from IAEA. We have permission, but please do not use, don't take pictures of them. So continues to ulcerate, more painful. They start morphine. It's not doing a whole lot for him. He's got a sciatic neuropathy. Remember what I said. Think about what's in the neighborhood. Let me go back up here. Think about what is in the neighborhood. You've got active red bone marrow, proximal femur. You've got bone marrow in the pelvis. You've got genitalia in the area, the rectum. You've got all of this in the neighborhood. You have to think about that. So sciatic neuropathy. They know at this point, the IAEA says, look, you need to do a hemipelvectomy. That's an amputation half the pelvis. You need to do a colectomy. You need to divert his ureters and create a new bladder pouch. At the time, they couldn't come to any good consensus. So they said, well, let's send him to Percy Military Hospital just outside of Paris, France. Very good with doing skin grafts. That they are still superb in their treatment with these injuries. They said, okay, yeah, we could try to do a graft. Well, it starts getting rapidly worse on them. He gets septic. They know they have to do the hemipelvectomy, yet they can't because he gets septic. They delayed it. So we're getting lots of debridement, massive debridement, excision of dead tissue. And they end up sacrificing his sciatic nerve. So they finally do get to do the hemipelvectomy. They do the colectomy. They do nothing with the bladder at all. And yet his perineum continues to ulcerate. The damage is still there. It's going to keep going. They get him back home, not sure if he would survive. He does get home. His ischial bone is exposed. These are the types of things I dealt with my gynecologic oncology patients. He has urethral necrosis, yet he does have an indwelling Foley catheter. Maybe not great, but still there. So this is November. This is the posterior view. I'm going to stay on this slide for just a moment because or I'm sorry, that's not a posterior view. We have that coming up next. But you see the fistula tract come up. Sorry, I've got the preview slides here. This is the fistula that developed from that urethral necrosis, having all this ulceration and having an indwelling Foley. This is the posterior view, and I'm just going to stay on this slide for just a moment. We got follow-up in 2011 from his treating physician. He showed us pictures, also video of this gentleman. They're doing fairly well at that point in time. Instead of beefy red granulation tissue, it was nice pink healed tissue, still with the fistula, still with that Foley, doing well with it, and you certainly would not want to start getting in there to do a lot of excisions at this point. So he still looked like this, but healed. He could move himself across the bed using his arms. His kids could get him in the wheelchair. All of his kids did very well. They are still monitored. He's done well. He got a stipend from the government. His wife did well, though. I'm going to go ahead to the next slide. She had initially about let's say 4 to 5 centimeter lesion, which required numerous surgeries, and over 2.5 years, she finally achieved healing with about a 10-centimeter scar left, which compared to her husband, you think, well, she got off pretty easily, though she went through a lot for someone who was just over those genes for just a short time. You can read these. I'm going to just give you the FAQs right off the bat, and I have a feeling we're going to have to skip the Q&As and do those in the chat because it is time for lunch. But how did he get it? How did he get the source? The screws on the lockbox for the industrial radiography device were loose. They didn't pursue it further. That was that. He certainly received more punishment than he really should have gotten. No markings on that device. The kids did well. The wife finally did well. There were no legal proceedings taken against any of them. That is all I've got for you. Dana, you can tell us if we're going to take time for questions. Oh, I do have additional resources. I've got 2 pages of this. If you want to do a screenshot of these, please feel free. Anything else we have, feel free to do screenshots, just not the patient picture. So, and then there's another one for you. So a lot of good references. Dana, what's the call?
Dana's having some technical difficulties, but it looks like we are going to try and jump into our break, our lunch. So okay. We will resume at 1:30.
Okay, wonderful. And we will answer everything on chat, and we'll put resources in. We'll answer on Q&A, et cetera. So, and certainly if you need these, I'll just have these up. Actually, you guys probably want to go to the break music though. So I'll stop sharing and go off camera and enjoy your lunch, dinner, breakfast, whatever it shall be for you. Thank you.
right, can everybody hear me okay?
Yes, we can.
Okay, great. All right, well, thanks for coming back after lunch, everyone. My name's Emily Kiernan. I'm an emergency physician and medical toxicologist, and also part of the REACTS team. And sorry, let me minimize myself here. Okay, I don't have any disclosures. And so today we're going to be reviewing pre-hospital and hospital planning, discuss environmental controls and setup, identify how the importance of health physics and medical staff coordination can positively impact the response to a radiological incident, discuss appropriate use of PPE or personal protective equipment, identify methods for patient decontamination and care, and review methods for managing a radiological mass casualty incident. So over the next few slides, I want to give a brief overview of some of the processes and procedures that are likely in place at your facility or that are in your emergency management plan that are ready to deploy if there is a radiological or nuclear incident, or that are working every day to keep you safe if you do work around these types of materials. Incident action planning is a really important concept that outlines the objectives, strategies, and tactics for managing an incident as defined by the Incident Command System, or the ICS, which we'll talk a little bit more about in a bit. This is necessary for a successful response if an incident were to occur. Many folks who have worked in the Incident Command System structure are pretty good at it, and they've developed and refined their incident action planning process based on lessons learned in historical accidents and incidents. Practicing and planning ahead of time with tabletop exercises or drills and coordinating with key players from various agencies and organizations is really key to the successful execution of an incident action plan. Now, the HICS, or the Hospital Incident Command Structure, is an incident command system that is specifically designed for hospitals and are flexible and adaptable to meet the specific needs and capabilities of the hospital that you're working in. So this won't be the same for a small hospital as it is for a large tertiary care center. This also allows a system to establish clear roles and responsibilities, including who the incident commander is, and things like this may change throughout the event depending on who is available. Now, we don't have time to go through this entire infrastructure of the HICS system, but if you aren't familiar, this is a really good time to check in with your disaster preparedness or emergency managers to understand where you fit into this structure. There are also free courses available online provided by FEMA and other agencies that can walk you through a lot more of these incident command systems. So a radiation protection program establishes best practices for protecting workers from ionizing radiation, and usually is managed by a qualified health expert like our health physicists, or sometimes I'll refer to them as an HP, or radiation safety officers, or your RSO. Engineering controls are often put in place to maintain radiation ALARA, or as low as reasonably achievable. This includes things like having negative pressure rooms, HEPA filters, and containment devices. These controls are typically incorporated into the design of a facility. Administrative controls generally support these engineering controls, and these can include things like written policies and procedures, education and training, and signage posted for awareness in areas of high radiation contamination. Control of access may be necessary to inform workers of the status of an area and if there are potential hazards there. These controls can include ingress and egress points, authorized personnel badges, different badge systems, and then doors that are under key and lock. Now, once we've established where our treatment area will be based on our incident command system, we'll work with our HPs to ensure that we have as much protection available as possible using some of those radiation controls. But we still need to set up our controlled treatment area, or sometimes referred to as our hot zone. As you'll hear repeatedly in this course, you never want to delay care to establish a controlled area. Once we know that a patient is stabilized, we're able to establish these different treatment areas. In this area, we want to remove any unnecessary equipment and people, as we don't want to make more contaminated objects than we have to, that will ultimately have to be decontaminated later on. Additionally, we want to get all of the necessary equipment so that when we receive our first patient, there's no need to be looking for additional items or coming in and out of the room, ultimately saving time. This type of equipment can include things like your PPE, survey meters, dosimeters, and supplies for documentation. We can also place floor coverings down if we have time and have the materials available. At REACTS, we'll frequently use butcher paper and then tape it to the ground. And this will be helpful when we're actually cleaning up the area after the incident is over. This is an example of some of the material that was created by REACTS and some others, and can be posted as a reminder of the different algorithms that you can follow, which can be really helpful in stressful situations. This is similar to your BLS or CPR, ACLS, or PAL, some of these different algorithms that help us walk step through step in a stressful resuscitation. This is part of a series of stages that includes information for pre-hospital, hospital, and post-hospital management, and they're all available online for free or on the REACTS mobile app. As mentioned before, we do need to set up our treatment area, and this is a schematic of one potential layout. So don't be fooled by the terminology. Here we see a contaminated area, buffer zone, and clean area, but you might also see this listed as a hot, warm, and cold zone. So make sure that you're familiar with the terminology that is used within your hospital's emergency plan so that you're very familiar and you're not caught up on this terminology when there is an incident occurring. Either way, what we see here on the top right is we have a separate entrance for patients who potentially are contaminated with radioactive material. We have a center is going to be laying, and then we have our ED staff, so our medical staff, and then our radiation survey and charting staff. So this will be our HPs. And then we have a designated area for contaminated waste. Now, once the patient has been stabilized and decontaminated, we're going to cross over that hotline into the buffer zone. And this is where we're going to make sure that the patient has no more radioactive contamination on them. We're going to perform our radiation survey, get rid of any additional waste. And then at that point, they can move into the clean area. Once a patient enters that clean area or that cold zone, they're going to be treated like any other non-radiation patient, and we can continue our medical care or next processes in place. So how do we triage these patients? You always want to follow your institutional triage guidelines, but I will reiterate here again, we always are going to treat our life-threatening conditions first, whether that be medical or trauma. Most patients who are going to come in from either a nuclear detonation or a dirty bomb scenario or an explosion at a power plant will have traumatic injuries and burns. And these are going to kill the patients way before any radiation will be the issue for them. So once we have ruled out that they do not have any life-threatening injuries, we can move on to our radiation triage. We want to know where the contamination is located on a person, what type of radiation we might have, and whether there's a lot of contamination or just a little bit. We also want to identify who these patients are. So we want to know, who they are, their age, their comorbidities, and we want to try and get a very focused history and physical. Additionally, we want to know where they were at the time of the event. Why were they there? How long were they there? How long after the explosion did they start to develop symptoms, and did they have symptoms of nausea and vomiting? Because this can be really important information to help our HPs determine the patient's dose later on and help us to triage who might need more emergent medical care. So do you think this point is important? Again, I will reiterate that we always want to treat life threats first. And one thing I like to point out is that although we say that we need to treat life threats first, we still need to protect ourselves. Just like during COVID, we still need to don our own PPE and make sure that we are caring for ourselves. So if you look at the picture on the right here, you notice that there are some firefighters. And if this was a radiological or nuclear incident, great, our firefighters have on some, they have on their gear, so that might give them some skin protection, but that they don't have any mask on, they don't have any eyewear. And so they are then at risk for getting that radioactive contamination onto them or inside of them and then becoming a patient themselves. Now, the EMS paramedic seems to do a little bit better. It looks like he might have a mask and a face shield on, and then, has gloves. So he's done a bit better. But we do want to make sure that we are protecting ourselves, and then we can go to address any life threats that the patient might have. Now, if we are bringing in someone who is covered in radioactive contamination, one thing that we can do is that we can wrap them in multiple sheets to try and secure that radiological material. Much like if someone were covered in dirt and we didn't want to get the dirt onto the floor of the ambulance, we can put multiple sheets around them to try and contain it inside of them until we get them to a safe place where we can decontaminate them later on. If you have a patient who has non-life-threatening injuries, we can hopefully decontaminate them at the scene and leave all of that material there. Not just the radioactive material, but also the clothing that the patients had on before we transport them, so that we're not bringing that material with us and potentially making additional areas that are now contaminated. Ideally, your incident action plan, like we talked about before, will be put in place ahead of time, and you will have practiced this, so you will know, who needs to be transported, how you're going to transport them, whether it be via ground and air, and where your local or where your closest hospital that will be receiving those patients will be. But again, these are things that you're going to want to discuss and practice with any other key players before an incident happens. We're going to watch a quick video about pre-hospital transportation.
Emily, I don't think you're sharing your sound.
Uh-oh.
Any emergency situation can be a high stress, fast.
Hold on, I think I did this wrong. Okay. Sorry about that, everyone. Should be good now. Is that better?
That's good.
Sounds great.
All right, sorry.
Any emergency situation can be a high-stress, fast-paced environment where time is of the essence. Scene safety, medical treatment, and patient transport all take well-trained professionals who are quick to act and knowledgeable about the impacts of their decisions. Emergencies involving radiation are often seen as more complicated events, but most radiation-related incidents bring little risk to those providing patient care and transport. Knowledge of the real radiation risk is crucial when dealing with radiation-related injuries. In these events, the key is that emergency medical care of the patient takes precedence over decontamination. Unlike with chemical contamination, medical stabilization for patients with radiological contamination takes priority. Irradiation occurs when all or part of the body is exposed to radiation from a source. Irradiated patients are not contaminated, and irradiation does not make a person radioactive. These irradiated or exposure-only patients are analogous to those who have had an X-ray and therefore pose no radiological threat to the care provider. Contaminated patients are those who have transferable radiological material any place it is not desired. A person is externally contaminated if radioactive material is on the skin. A person is internally contaminated if radioactive material is inhaled, ingested, or absorbed through wounds. A person contaminated with radioactive materials will be irradiated until the radioactive material, the source of the radiation, is removed. The vast majority of external radiological contamination can be detected with a basic survey meter. Radiological contamination can be readily detected, pinpointed, and addressed, and the area can be decontaminated with simple cleaning methods such as mild soap and water. Basic radiological instrumentation is used to understand risk and assess effectiveness of contamination control techniques. It is important to remember that contamination can be mitigated and contained with appropriate measures. Doing so makes the transport of a contaminated patient safer for ground ambulance and aeromedical crews, which helps expedite patient transport to definitive care. Providers can mitigate the radiation contamination risk by wearing available personal protective equipment. Various examples can be seen in this video. The following steps will help emergency personnel provide high-quality patient care while mitigating radiological contamination risk. Assess and treat life-threatening injuries. Do not delay life-saving measures in order to assess radiological contamination status. Perform routine emergency care during extrication procedures. Move the patient away from the radiation hazard area using proper patient transfer techniques to prevent further injury. Patients should be monitored for possible contamination only after they are medically stable. Radiation levels above background indicate the presence of contamination. With an external radiological contamination event, outer garments typically retain a large percentage of the contamination. Removing the patient's outerwear helps control the spread of this contamination. In this scenario, a patient is extricated from a radiologically contaminated area in an occupational setting. Therefore, removal of personal protective equipment in a controlled manner should be done expeditiously, provided removal can be accomplished without causing further injury or delaying necessary care. If possible, before removing clothing, the patient's airway should be protected from airborne contaminants. This can be accomplished with an oxygen mask, a simple surgical mask, an N95 mask, or an inverted face shield as shown here. As with any intervention, the patient's respiratory status should be continuously monitored. In this demonstration, a 3-sheet method is used to help control the spread of contamination from the patient and from surfaces. The bottom sheet protects the providers and the medical equipment from contamination on the ground. The top sheet is used as a surface to provide initial patient care and will be left behind with the patient's contaminated clothing. The middle sheet is used to cocoon the patient, thus containing any residual contaminants. Based on medical necessity, a limb or other body part may be exposed to facilitate acquisition of vital signs or intravenous access. With the patient appropriately packaged to contain any contamination and mitigate its spread, the patient may now be placed on a covered stretcher at the control line, if one has been established, and prepared for transport by securing them in the appropriate manner. Do not remove the patient from the spine board if one was used for medical purposes. If possible, the patient should be transported by personnel who have not entered the control area. In a setting where the patient is wearing only personal clothing, the same concepts and approach apply. Variations to this cocooning method include using plastic sheets, tarps, or garbage bags. Isolated contamination may also be fixed in place by using a pre-made bioclusive dressing or plastic wrap. If aeromedical transport is warranted, the landing zone should be upwind and away from the contaminated site, which may require intermediate transport from the incident site. The patient may be placed onto the helicopter via a cold or hot load based on medical priority and local protocols. The patient should be transported to the most appropriate facility based on their medical or trauma needs. During transport, the concepts of time, distance, and shielding can be used to minimize risk. During transport, a standard medical history should be obtained. Depending on the type of radiological incident, other questions that might provide useful information include about where the patient was in relation to the event, how long the patient was in that location, and any recent nuclear medicine tests. The patient may have anxiety related to the event, and psychological support should be offered. If the ground or air ambulance is needed for another medical trauma emergency, especially if returning to the same radiologically contaminated scene, it may be used prior to surveying and decontamination. If radiological instrumentation is available, it can be used to identify any areas of contamination, and those areas may be covered or decontaminated as time allows. Medical care takes priority for all patients, and therefore response to another emergency call should not be delayed. Otherwise, the ambulance and crew should not return to regular service until the crew, vehicle, and equipment have undergone monitoring and any necessary decontamination. Consider common areas touched by medical personnel as a priority for survey, such as oxygen regulators, monitoring equipment, medical cabinets or bags, and radios. For this video, a glow powder that can be seen under ultraviolet light was used to simulate transferable radiological contamination in a moulaged wound. In this demonstration, a bioclusive dressing was used to mitigate the spread of contamination. Ultraviolet light shows powdered simulated radiological contamination is easily contained using simple dressing techniques without any aerosolization, even when loading a patient on a helicopter with engine on and blades spinning. Understanding contamination control can provide for the safety of emergency responders and medical providers and lead to better patient outcomes. For more information on the medical management of acute ionizing radiation illnesses and injuries, or for a REACTS course schedule, please visit our website. REACTS may be reached for emergency advice and consultation 24 hours a day, or for general information during normal business hours.
All right, brilliant video. Pretty much everything you need to know about in this lecture. So this is just another example of the triage pathways that REACTS has available. Again, they're free online, they're free in the mobile app. But the key point here is that, which they talked very well about in the video, is that you have to determine if you're going down that contamination pathway. So am I covered in, I like to think of it as radioactive dirt, but do I have radioactive material on me? Or am I going to go down the exposure pathway as if someone just came back from getting a chest x-ray? But knowing the difference between that is really going to help you make that key distinction and will really change how you're going to triage patients, how you're going to decide what PPE to wear, whether or not they need to be decontaminated. So this is a really, really important point that I hope you can take away from this course today. Okay, so back to our hospital. Now we have our contaminated patient, so covered in radioactive material, radioactive dirt. And let's say that they need to go to get a chest x-ray, right? We said that a lot of people will have traumatic injuries after coming in from a scene. So how are we going to get them there? We need to plan our pathway to avoid areas with a lot of patients or equipment that could potentially get that radioactive contamination on them. Because again, we don't want any additional things that are going to have to be decontaminated or taken out of commission because we got material on. So we can mitigate this by, again, wrapping our patient in the multi-sheet cocoon that we saw in the video. But we can also take a different path. And maybe this goes outside, maybe this goes down a lesser traveled hallway. It might not always be the shortest route, but this is a route that should be worked out ahead of time so that we know the best way to get someone to where they need to go. Here is another picture of a potential setup. And note again on the left side of the wall where there is that printed REACTS posters and material that we talked about. And these are really great to have hanging when you are, again, in a high stress situation so that you can look at something and go stepwise down an algorithm to make sure that you're not missing any steps and that we can effectively and safely take care of ourselves and of our patients. So if this was our trauma room or our hot room, and then we have our control line. So again, within the room, we're going to have our patient, we're going to have our medical staff and our HPs all working together to get the patient decontaminated. And once we're coming across that control line, we want to make sure that we're performing our radiation survey to make sure that we're not bringing any of that contamination from that room over into the clean area. So who are our key personnel and resources in an incident response like this? Again, this is going to be something that will be discussed as part of your incident action plan. And we want to make sure that everyone knows their role, that they feel safe and educated and empowered to perform their role in a stressful situation, and that everyone can work efficiently in a group. So this is going to include your emergency department and EMS personnel, your health physicists and radiation safety officers, respiratory, radiology, and nuclear medicine, your lab medicine, environmental services, so your folks who are cleaning up after you, your security and engineering, and then any specialty consultants like your burn, your hematologist, your oncologist who might be dealing with these type of patients once they're medically stabilized and admitted to the hospital. We briefly touched on, so in this capacity, we have two major players are going to be the medical staff and the health physicists. So medical staff needs to understand why the HPs are asking for specific interventions like nose blows or why they're having them move certain ways or how they're helping to decontaminate a wound. But our medical staff also has to have a basic understanding of radiation and radiation safety. Likewise, the HPs that are in the room need to understand the importance of life-saving intervention. We don't want someone, coming up to do a survey of the face while the medical staff is trying to intubate someone or perform a life-saving intervention. Additionally, we want to make sure that everyone who doesn't typically spend time in an emergency situation or in an emergency department is well aware of the sights and the sounds that injured patients can sometimes have. and make sure that they are okay with kind of what's going on in that subsequent resuscitation. And this will allow us to all work quickly and efficiently as a team to do the best thing we can for our patients. So we briefly touched on PPE in an exposed and contaminated patient. And remember, exposed patients are just like those patients who went to get a chest x-ray. We don't need any special PPE to take care of them. Standard gloves, eye protection, or gown that you would wear just from taking care of patients is completely adequate. If we have a contaminated patient, again, think about someone who's covered in radioactive dirt, we're going to need some additional PPE in order to make sure that we keep that off of us and that we keep all of that external contamination from becoming internalized by us or by the patient. So as you saw in the video, making sure that we have the appropriate gown and gloves. We're usually going to recommend having 2 different pairs of gloves on, ideally different colors so you can see if one has been broken. A mask with a face shield or some sort of eye protection. We want shoe and hair covers. And then we're going to tape all of the seams and cuffs at our wrists and at our ankles. And then we also want to have a personal dosimeter to make sure that we are, later on, we can figure out how much, what our actual dose was absorbed so we can take care of ourselves if needed later on. So once a patient has been decontaminated or we identify that they have only had an exposure, your PPE choices can be de-escalated. We want to make sure that our PPE is as functional as possible. For anyone who has ever worn a level A kind of spacesuit level PPE, you know that procedures can be very technically difficult, and those suits get very, very hot and cannot be worn for a long period of time. So this might limit our ability to utilize some of our radiological protective measures like time, distance, and shielding. And they're not going to confer any additional protection. So we want to make sure that we're picking the right level of PPE for the situation that we're in. Now, how are we going to don our PPE? It's a lot easier to do in person. But again, there are flyers available free from the REACT's website and also on the mobile app. And again, when we look back at our room before, you can hang pictures of what you need to do and what order you need to do them in order to keep yourself safe. But this is REACT's way of doing it. There are other ways of doing this. So you always want to follow your institutional policies. And this is just an example of how we do it here. When we're performing patient decontamination, as seen in the video, removing the clothing will account for about 90% of the contaminants that are on the patient. As you can see in the picture here, we have the inverted face shield, and that's to protect the patient's airway from anything that gets aerosolized, and so that they're not breathing it in. The video does a really good job of showing how we cut the clothing in a patient and roll the contamination away from the patient. Again, we're trying to, if someone is covered in dirt, we want to make sure that none of that dirt is going to get inside of them. So we're going to try everything we can to keep it away from them. You're always going to cut away from the airway, so from the neck down, and then you're going to roll the garment to contain all of that radioactive material. Obviously, we're going to be, in a lot of these situations, we're going to be cutting people out of all of their clothing. And so we want to try and maintain modesty of the patient as much as possible and cover them as quickly as possible. And then we're going to take all of that clothing and place it in a properly labeled bag. And our RSO or our HPs will instruct us where to put that material. We don't want to bring it with us, and we want to make sure that we're putting it in a safe place. Now, the initial radiological survey can be done after clothing and contaminated sheets are removed, because again, that's going to be about 90% of the contaminant that is on that patient. So we want to get rid of that so we can see what residual contamination we have left. Surveys can be done simultaneously with a trauma exam if the patient is medically stable. So, and anyone who's ever performed a trauma survey, most times we will roll them on their side to evaluate their spine and their back. And so again, if the patient is stable, this is a perfect time for our HPs to come in and do their survey to see if we have any contamination that needs to be taken care of on the back. When we are doing those surveys, we want to document, and the picture you can see here is someone documenting where we're finding contamination on the patient. So we want to document what the location is and what the counts per minute. And then also, this is a great time to collect biosamples that can be analyzed later for the radiation dose the patient has absorbed. So this would be things like nasal swabs and blood samples. For patient decontamination, showering is a great way to get rid of any additional contamination. We want to make sure that the water runoff is going away from the face, mouth, and nose. So if we do have the shower on top, we want to lean back so that none of that is coming down our face. If we do have wounds, we're going to cover them with a water-resistant cover. And we're going to use gentle soaps and shampoo. And as Megan said before, we don't want to be using any hair conditioner because that might help to adhere that material to the hair and then ultimately lead to having to cut it off. Depending on the scenario, you also can use pre-moistened wipes if you don't have showers available or if you're in a water deficient area. And then patients also, if they're able to walk and talk and don't have any traumatic injuries, you can have them wash their area on their own. When we are decontaminating someone, we do have a list of priorities. So any way that external contamination can become internal, we want to try and prevent that. So first, we're going to decon any open wounds because that can directly get into your bloodstream. Also, our next step would be to look for body orifices, so eyes, mouth, and nose. And then after that, we would move on to intact skin. We won't go much into this in this lecture, but here is a brief summary of the agents that are available for patients who are internally contaminated. So the FDA has approved the following countermeasures. So zinc and calcium DTPA are approved for internal contamination with plutonium, americium, and curium, potassium iodide for iodine 131, and Prussian blue for cesium, and radioactive and non-radioactive thallium. NCRP also recommends the following countermeasures. So sodium bicarbonate if someone has an internal contamination with uranium, and calcium or aluminum phosphate for strontium and radium. As far as wound decontamination, right, this is our #1 priority for decontamination. We want to consider what isotope we're dealing with. And also we want to make sure that we're managing pain. Not only is irrigating a wound painful for patients, but the way that they got that wound is most likely through a traumatic injury. So make sure that we're adequately treating their pain before we go digging around in there. We want to irrigate away from the wound, and we don't want to do high pressure irrigation and push any of that material further in. So we want gentle irrigation. But know that even though we will decontaminate multiple times, some of these wounds still require more aggressive treatment and might require surgical debridement in the operating room. Next, we move on to our second priority, which was orifice decontamination. So if the patient is able to, have them gently blow their nose a few times. And then we can also irrigate their eyes with standard techniques. So whether a Morgan lens or a wash station that's available. But remember, if you are blowing radioactive material out of your nose or irrigating it out of your eyes, that water or that tissue is now also contaminated. And so we want to make sure that we are trying to contain that contamination as much as possible, that we're not spreading it to other locations, and that we will collect and, again, put that wherever our HP tells us is safe to collect that material. Finally, we move on to intact skin decontamination. So we're going to clean towards the center, or clean the site towards the center and move outward. We want to watch for redness or damage to the skin, indicating a potential cutaneous radiation injury or a thermal or a chemical burn. Also, again, this is a very stressful situation, so we don't want people, vigorously rubbing. We're going to be very gentle because we don't want to make any additional trauma to the skin that allows an entry path for external contamination to become internal. We don't want to shave. If we do have hair and we need to remove it, we're going to use clippers or scissors. And we're going to stop this decontamination effort once the counts on your survey return to less than 2 times of your background, or if your contamination counts are not dropping after multiple attempts. So how do we know when we're done? After each decontamination effort, we're going to repeat our radiation survey. We want to make sure that we're maintaining a consistent height and speed when we are performing our surveys, because if we're surveying our arm, we're going to get much different levels here than if we're up here and checking. So we want to make sure that we're maintaining consistency with each measure, after each decontamination effort. And then after that, we can make the decision of whether we need to repeat decontamination or if we need to escalate to something like a surgical intervention or considering one of our countermeasures for internal contamination. Finally, if we have a patient who is eligible to be discharged from the hospital, we're going to consult with our radiation safety officer or our health physicist. They might continue to need medical or trauma care in the hospital or outside the hospital in outpatient follow-up, and they still might have contamination present. We want to follow up, make sure that our follow-up instructions for our different treatments are very clear for patients for what signs and symptoms they might expect and whether or not they need to provide bioassays. So one of the common things is that we give someone a container for a 24-hour urine collection. And so we want to make sure that they know when to start that, what to do with it when they're done, and how to move forward. And then finally, we want to give discharge instructions for any other family members that might be in the house. So people will commonly have questions about, can I sleep next to my spouse? Can I hold my baby? Am I still able to breastfeed? So we want to try and address any of these concerns and give appropriate precautions for everyone who's in the house before the patient leaves the hospital or the healthcare setting. As far as doffing, again, this is that poster I was referring to before, where we have a step-by-step of how to remove our protective clothing. And what we want to do here, again, this is REACT's policy. You always want to follow your institution's policies that might be a little bit different, but we want to take care that when we've done such a good job at taking care of patients and making sure everybody is safe and preventing them from having internal contamination, we want to do the same for us. So when we are doffing, we want to make sure that we're taking our time, that we're being very methodical in how we're taking everything off so that we are also remain safe and are able to leave without any contamination. And the biggest thing when we're talking about external contamination is that we don't want it to become internal. Once it becomes internal, it's a lot harder to deal with. Whereas again, when we have external contamination, removing our clothing or our external PPE will remove the majority of that contamination. Once we discard any of our PPE, again, we want to make sure that we're putting it in the appropriate bags. And this will be part of your emergency management plan. And you can always consult with your HPs if you have any questions. Additionally, if we are able to, we want to collect any runoff from decontamination efforts, whether that be shower water or wound water, eye wash, or things like that. So after discharge, all of the equipment and staff must also be surveyed and dosimeters must be submitted for evaluation. The treatment area may be used prior to survey for urgent patients if there are no other options available. But we always want to prioritize who exits, or then we also need to prioritize who exit first. So it might not always be a physician or the nurse. It might not always be the patient. It's going to be different in every scenario, but realize that there's no necessary priority. It's going to be whoever needs to get out of there at that time. And then finally, doffing PPE. Again, REACTs can make recommendations, but make sure that we're following our facility guidelines and disposing of all of this waste properly. What do we do after an incident? We want to document any staff exposures. So again, ideally, you're going to have some type of personal dosimeter. And so we want to make sure that we are doing our thorough survey when we are leaving the hot zone. And then we also want to make sure that we send our personal dosimeter to be read and analyzed so that we can understand what our personal dose was. And then a really big thing that sometimes gets overlooked is that we have to address the psychological concerns, not only of our patients, but also of our medical staff. We want to make sure that we're debriefing after an event and that we're addressing any fears that the patient or that the staff may have, and also that their family might have for having them come home. So this is a really big part of this that we don't always think about, but it really is a stressful time for a lot of people. And we want to make sure that we're addressing that and making sure that the appropriate resources are available for people who need to talk about it. Finally, waste management. We want to make sure that our housekeeping folks are educated and trained. Again, this is part of our incident action planning to make sure that everybody is on the same page and knows what their responsibilities are. We want to know who is assuming the responsibility for the waste, where the water, what we're going to do with any of that water from the showers and all of our decon. And know that particularly if we're talking about a nuclear detonation or an RDD, dirty bomb, that a lot of this might be required for forensic evidence. So it is important that we keep that. And then finally, once we are finished with our entire incident and we're recovering, our HPs are going to help to support making sure that the areas that we use for this response are cleaned and ready to be used again at another time. Now, everything's a little bit different when we talk about a mass casualty. It is much easier to deal with 1 or 2 patients that come through and need to go through the decon process as opposed to 200. So as far as medical priority, nothing changes there. We always want to still prioritize our life-threatening injuries, but know that our symptomatic patients who are exposed may not have injuries, right? So just because they were exposed, like getting a chest x-ray, they might not have any injuries, but that doesn't mean that they don't have significant exposure. And likewise, contaminated patients may not require emergency intervention or emergency care. So just because they were in an area where a bomb went off doesn't mean that they were necessarily have traumatic injuries, but they might have had some of the material get on them. So we can't really put these people nicely into buckets, and we just want to make sure that we're getting a good history and good physical on anyone who comes through. We do want to be mindful of patients with special needs. So if someone's in a wheelchair, or if we're dealing with minors and trying to keep those families together, 1, just for the stress of the situation, but 2, they can also help in the decon procedure of their loved ones who might have different needs. And additionally, when we didn't talk too much about how you perform your radiation survey today, but if we have 200 people doing a full radiological survey might not be appropriate at that time, and we might move to a more brief survey of just looking at hands, feet, and face for contamination. We're always going to communicate with our HPs or our RSO for best practices on how to remove contaminants. They're going to be really key in these situations. And if we do have, large showers set up that we might, if we're planning, it takes about 5 minutes for one adult to shower, that we might only be getting about 12 done per hour. And so we have to see what resources we have available and figure out the best way that we can move people through. And I think I went a few minutes over, and I apologize, but thank you. And I'm not sure if we're taking questions right now or moving on.
You can take a couple questions, Dr. Kiernan, if you're ready.
Yeah. Sorry, I'm just seeing the chat now. So if anyone has questions that they see or have not answered, feel free to shout them out.
You've got 2 open questions in the Q&A as well. I'm not sure if you have.
Oh, I'm sorry. I was looking
No,
at forgot that there is more than one.
Lots of places.
In the treatment area layout, the separate entrance is inside the posted as contamination. In the treatment area layout, the separate entrance is inside the post. So I think it's going to depend on how your where you're actually setting up your treatment area. But ideally, you're having an entrance that, you're not having, let's say we have, again, a mass casualty and there are 100 people showing up. This is going to be a separate entrance than your, the front of the hospital or your standard emergency room entrance. This is going to be an entrance that we're going to be bringing people in specifically for decontamination.
Thanks, Emily. And hey, sorry I wasn't there for you to read the questions for you, but also Megan may talk about this a little bit right at the end of the day as well. So I think, yeah, I'll go ahead and read those off for you if you want, or if you've got them right there, feel free. I mean, it's up to you.
Actually, I might send this one to you. The next one is, we discontinued covering floors of treatment areas about 30 years ago. Do you have data indicating the need to return to this process?
Yeah, thank you. That's a great question, and what an easy breezy one. I appreciate that very much, especially after lunch. you can cover, you cannot cover. If you're going to cover, it serves a couple of things. Because we use a live liquid contaminant, when we spill something on the floor, we want to pay attention to it. We've got nice floors with the full treatment to where it's non-permeable, et cetera, et cetera. But we still like to cover the floor because you get a big psychological barrier. It's just like if you're going into an OR, you've got all kinds of bells and whistles and things telling you don't go in there unless you are appropriately attired. Let's put it that way. So yeah, it's not like it's an old or a new thing. It's whatever works for your facility. If you've got the epoxy floors, you've got some good barriers, great. However, we do catch things that do get spilled. When we do that, we're able to mark those. We're able to go over and survey those. Now, if you're in a busy trauma, you're not going to have people really paying that much attention to it. But you can imagine if you spill something that is contaminated on the floor and people are tracking all over the place, that could very well be a way to get things out of the controlled area if you don't have appropriate doffing and surveying at that control line. And oftentimes, if you've got another trauma, you're not going to go through the full doffing procedure. You're going to get the stuff off and go to the next room or what have you. So hopefully that answered your question. And back to you, Emily. Thank you.
Next, could you provide an example of an IEP for such an event? I don't know. I have our hospital's incident action plan, but every hospital, wherever you work, whether it be, again, in a hospital, in EMS or a paramedic or military, everyone should have their own emergency disaster plan. And a lot of times that'll be part of that. So if you are able to reach out to your emergency management or planner or whoever is involved in that for your facility, that would probably be the best place to get an example of that. It is important to collect forensic evidence and maintain a chain of custody for any occupational accident or terrorism attack. Absolutely. Obviously, if there's a terrorism attack, there's going to be a lot going on at the time, but a lot of that material is going to be very important for forensics later on. As far as the chain of custody, I think that might be a little difficult since there will be so much material and so many things happening. So I'm not sure where that would necessarily come into play. But again, that's probably more part of your emergency action plan as well. Does the runoff during decon need to be contained? Always a great question. If possible, it is best practice to try and contain as much of that material as possible. Again, if you have 1 or 2 patients, this is a lot easier to do and be able to contain that. And then again, your HP or your RSO will tell you where to take that material or where to store it. Once you start getting into these mass casualty incidents and you have hundreds of patients, you might not be able to contain it. And at that point, you're going to let it run off into the drains.
Fantastic. That was great. All right. I have not been looking at the schedule, but I believe, Dylan, are you back up again?
I believe so.
Or wait, or is it? Yes, it is you. Common radiation sources, correct?
Yes, ma'am.
All right. Well, thank you, sir. I'm going to go quiet here and let you guys get your stuff going.
And then he said, hopefully, everything worked.
Looks good.
Assuming everything works, I'll start talking about our common radiation sources. Welcome back. Hope everyone had a good lunch. I know I did. Thank you, Emily. Everyone just talked today. This is my last lecture today, but I'll still be looking around in the chat to answer any questions you guys might have about whatever I've talked about, whatever Megan might talk about, and however I can help with whatever the rest of the team has to talk about later on. This lecture will focus more on the sources themselves, kind of how we categorize those. I'm sure you guys have heard category 1, category 2 sources, all the way down to category 5. If you've wondered what that meant, we'll go over it and talk about how all that works. We'll also talk about a few of our common accidents, or a few accidents and what makes them common between each other, why these things start happening, how things start differentiating themselves in these accidents. Start going through all of that. I still maintain no financial interest in any of the things we're talking about. Any of the histories are just what we found in the literature, kind of going over all of those. We aren't really sponsoring anything or any kind of response to those. Our objectives are going to be kind of looking at how we categorize our materials, how we identify those categorizations, everything else that goes along with those, from labeling to safety concerns, and everything kind of in between that. We're going to look at which sources are commonly found in these accidents, kind of identify why they're hazardous, what the problems are, and then also talk about just look at them and kind of relate back to why those assumed radionuclides become what they are because of the commonality they have in these accident type events. And then we're going to look at what's causing these accidents, what are kind of the root causes, what are a lot of the things leading up to them. And just to kind of give a spoiler alert for that, it's a lot of the time it's going to be I don't want to say over familiarity with our procedures, but an overconfidence, kind of a lack of concern because we've kind of done them so much. We start taking them for granted and skipping steps that are vitally important without really kind of looking like they should be that massively important. So as we start talking about these, we talk about accidents to help prevent those in the future. So as we're going through these accidents, there's a few rhetorical questions I want you guys to be asking yourselves. I'll kind of give some examples from my time when I was working at the Savannah River site. A lot of things we're going to be dealing with are going to immediately involve that local area of our work site. The work site is most likely where that accident is going to happen, kind of seeing what's around there, what's in that company or organization. When I was at Savannah River site, we had our radiators, we had our source control room. So all the sources kind of in that area were things that could go wrong. Our radiators were cesium-137, cobalt-60, stuff like that. So those common sources there as well. But now in that irradiator format kind of become more of a hazard in a different kind of way. When we're looking at kind of the step further out, what are the radiation sources in your common area or region? I work specifically in like the dosimetry labs and the calibration labs. So this would involve something like the sources down the road in the other areas where they have either their storage facilities, where they either have the plutonium processing facilities, and kind of how do those propagate? If an accident happens there, now we have that distance, but how is that going to start kind of propagating towards me? If we start having plumes or downwind areas or kind of exclusionary zones, how is that going to affect the area around those? When we start talking about travel, we get a bit more concerned with what might travel through the area. This is a bit more generic and kind of present as we go about our everyday lives, as things travel across state borders, as they travel to final destinations. At Savannah River site, just off site, there is a waste repository. So anything can come from pretty much the region past by Savannah River site to there. I live about 15 minutes off site. So even when I'm at home, if something happens on the main road, how does that affect the area? What might happen? And then going a step farther, this one looks more outside that RAD area. What other hazards get associated from either vehicular buildup? There was a site that nobody will forget about 30 years ago. It's on Riverside. A chlorine truck kind of turned over just off site. So now we had kind of that RAD concern from the site area. We had that chemical concern from that truck, kind of how those mix. And then how do we start handling both these hazards when we also have to be concerned with the others? So as we start looking at these accidents, a lot of things start coming into play that we kind of have to be in mind of all at once. And that's going to vary from region to region, from area to area, and even between floors in the same building, or even between labs on the same floor. It's also going to matter with what and how we're working with and around that radiation. As we've been working with radiation, we kind of discovered it very quickly, and then very quickly and aptly kind of turned it into something that we as people love to use. We kind of worked with radiation a little bit in the late 1800s, very early 1900s. Megan talked about exposure. The unit for that, the Rontgen, is named after William Rontgen. He was working with X-ray tubes. He noticed that even with those kind of wood blocks around the X-ray tubes, his photo paper was still developing. So he said something must be exposing these films. Kind of does that kind of exposure, works with the X-rays, finds out how we can kind of harness those, develop those. That's in 1895. In 1902, just 7 short years later, we have the first documented case of really X-ray induced cancer. Around the same point in time, very early 1900s, very late 1800s, we start applying these X-rays to medicine. There's a doctor in France who says, I am a forefront leader in kind of this oncological field. I know that cancer is caused by these parasites that live in the gut. So if I have my patient and I expose them twice daily to 30 minutes of just direct X-ray radiation to the gut, and then to kind of help with the pain and the swelling, I'm going to give them morphine and laudanum, or morphine and laudanum, and a slurry of other cocktails. That should cure their cancer. And in very short supply, we saw a massive decrease in that tumor. In very short supply, we also saw the decrease of our patient. So very quickly, we learned we can use these. We started using them, and we learned they have really serious side effects. As we start moving up into the 20s and 30s, we really start seeing a boom in industry. We start seeing industry itself take notice of radiation, trying to work with these. We have the American Radium Corporation that found out we can use this very similar to kind of this radium paint or this glowing paint. I'm sure everybody or most people are at least a little bit familiar with those glowing stars that you can put on the wall, and then at nighttime they'll glow and you can almost watch them fade away. Those work very similar to those OSLs and TLDs I mentioned in the last lecture. Kind of as that energy comes in with that natural sunlight, we have those excitation events. Those electrons get trapped. When you stop giving them energy, they're able to fall back down. They give off light and they glow. Somebody said, well, if we put a continual energy source in there, we put something that's always giving off energy, like this radium does because it's radioactive, we can mix it in with this paint and we'll have something that glows forever. 1,604-year half-life. My great-great-great-grandkid can use the same watch that I use. And honestly, that paint's going to break down before the radium does. This becomes a massive hit. We start putting this on watch faces, on airplane parts, on dials and cars and trains and everything else. And all of these small materials that we're painting on all of these things. Well, the Radium Corporation recommends that all of these radium painters kind of take that paintbrush and kind of roll it around on the sponge they're given. But that doesn't really give you a really nice fine point to make all these nice fine kind of numbers with. But what does make a good fine point is if you take that paintbrush, kind of put it on your tongue, pull it between your front 2 teeth, you get a really nice fine point to write all your paint and write all your numbers with. That also gives you a healthy amount of intake of these radionuclides into your system. So as this continues on over the years, these girls aren't really made aware of what they're working with. They start becoming sicker and sicker, more lethargic. The company makes an attempt to kind of put this off as long as they can, kind of thinking if we just kick this can down the road, they'll die off and we'll be fine and dandy and everything will pass along. Thankfully for these girls, a bunch of lawyers kind of come out. They're able to put forward these kind of rules, regulations, and these lawsuits. They get as much compensation as they're able to from them. And these radium girls kind of being that very front charge for kind of industry safety that eventually kind of develops into what we see becoming OSHA and all the other regulations we have for worker safety. In the same kind of time frame as the radium girls, we have Eben Byers. He's kind of this rich socialite. His real only job title on Wikipedia is that he was an amateur golfer. He rides horses in his spare time. He ends up falling off one day, breaks his arm. His doctor has been working with this, I guess we'll call him a snake oil salesman, who's been promoting something called Radithor, which is basically just a small vial of water that's been highly radiated with a little bit of thorium in it as well. So we've got these alpha emitters in these vials of water being promoted as medical cure-alls. It'll boost your immune system. It'll effectively be an energy drink. It'll cure your impotence. It'll do everything that you would want it to do and everything that you couldn't even imagine it could do. The doctor's getting like $1 back a vial, which is just mad money at the time. And he promotes this to even buyers. Even buyers takes it. Apparently has a very good healing streak, falls in love with the stuff to the point where he's drinking 3, 4, 5 vials a day, filling up troughs for it with his horses, and even pushing it on his girlfriends at the time. Very similar to the Radium Girls, he quickly starts to kind of start deteriorating. He starts becoming lethargic. He kind of retreats from that public view. He very quickly after that starts to get necrosis of the jaw, as these radium products like to kind of transfer wherever the body sees calcium. We see a high buildup where the body turns over calcium fastest, which is the jaw and kind of those thinner bones. Before he dies, his lawyer comes in to kind of do his last will, testaments, and all his kind of financials in order. And the lawyer says it was a terrible, gruesome sight. He only really had like 2 teeth left. Most of his bottom jaw was gone. And there were just dents in his skull from kind of where all this osteonecrosis had started happening. So these things were not very monitored at all, and very quickly led to these terrible accidents for these individuals, all within some 20, 30 years of us even discovering radiation in the first place. So once we found these, we really liked to kind of apply it and use it and do pretty much whatever we could with it. We start seeing it pop up in universities as we start trying to study this radiation, become more prominent. That continues even into today's time, today's age, where in my undergrad, I was able to work with a small scale accelerator. This involves everything from trying to find out how things work, just doing our regular research projects. It immediately took off in the medical field, like we mentioned with that French oncologist. But even in today, we're still very massively familiar with it. It's probably one of the more prominent areas we use radiation. When we start looking into industry, we have everything from soil and agricultural gauges saying, is this arable land? What's the water content? What's the hydrogenous content of these wells, these fields? You can start kind of monitoring your gauges on oil tanks. You don't really want to run electric current and wire up one side and down the other. But we can take these radiation sources and then put detectors on the other side. And if we measure that attenuation, the same way that Megan mentioned the smoke detectors get blocked off, if we measure that attenuation, we can find out how full our tanks are. Government and military are kind of coexisting. Government is studying it and trying to use it for everything from identification of threats, being able to find these sources, getting involved with the licensing requirements, into weapons management, weapons de-escalation, and everything in between. The military aspect is very poignant, effectively for all of our national labs, especially coming out of kind of the Manhattan Project, as everything kind of scaled around that, using radiation, still using our radiation detectors today for testing, identification, and every other process as we start looking through all of it. So pretty much, if you can think of a way to apply radiation, we're doing it. Because it's so prominent and just everywhere in the field, we have to have some way to recognize these threats, identify these threats, and kind of let ourselves know where these activities are happening. So for the most part, this has come out with this trefoil symbol. The trefoil symbol is this circle surrounded by these 3 kind of circulating fans around it. Originally, it's meant to be that initial circle is the atom, and those 3 fans are the energy radiating off of it. But depending on which folklore you believe, that's where it comes from. We see a bunch of these labels with our rad 1, rad 2, rad 3, kind of showing where these things are going and kind of starting to get into how strong are these sources, to what extent are we really worried about these things kind of panning out. This is a symbol that hopefully we'll start seeing more often, or I guess I should say, hopefully you never see. This is the IAEA's new imminent danger symbol. A lot of folk like to call this, I may or may not be included in a lot of folk, like to call this the fans make pirates run away symbol. This symbol here is supposed to be that universal human language of, hey, this is dangerous. You either need to get out of here or you will no longer be with us very quickly. This symbol is meant to go inside those category 1, 2, and 3 sources right before you have access to that sealed source. And this developed out of the need to do something about these kind of orphan and sealed sources. especially into the late 90s, early 2000s, a lot of the accidents the IAEA was seeing and was concerned with were sources either going missing or becoming lost or just falling out of the system, getting lost in the wilderness for a few years, and then random civilians would find them, not know what they're dealing with, and end up being the death of themselves, their imminent family, their neighbors. So the IAEA wanted some kind of symbol that would go in there with these sources to kind of find out. In the year 2000, they did a study involving a lot of the localities of these kind of orphan source accidents involving Brazil, India, and Kenya. And of those individuals surveyed, only 6% recognized that trefoil as radiological and hazardous. So there was a big miscommunication about what this symbol meant, and it wasn't immediately kind of shocking enough to kind of prepare that. So the IAEA did a whole bunch of tests. There were like 13 other symbols. This is the one that eventually ends up winning out. So this should be in place, like I said, right before you get to those sealed sources, right before you get to that point of no return, for lack of a better phrase. When we start talking about these category 1s, 2, and 3 sources, the categories go all the way down to category 5. Categories 1, 2, and 3 are just the most severe amongst them. So we're starting to talk about how are we going to categorize these? Why do we want to categorize these? Why does it matter? Each of these different categories have a number of different uses that we can actually see, we can get familiar with, and can really show us kind of the hazard and how quickly these things can do some serious harm to the individuals near and around them. So if you're interested in this kind of stuff, the IAEA put out a book, The Big Dangerous Qualities in Radioactive Materials. This is about a 150-page document, the first 10 pages of which are a list of all the radioactive nuclides. The following 140 pages are kind of how did they come to the D values for those nuclides, kind of their assumptions, their algorithms they used, and the mathematics behind it all. When we start talking about these categorizations of sources, that D value only goes for each individual source. That D value gets compared to the strength of each source in terms of its Becquerel count. So those activities that Megan talked about earlier. When we're talking about these kind of things, we can almost see it on this logarithm scale. If we're dealing with something on the order of a few tens of thousands of becquerels down into our microcurie range, these really aren't going to be significant health hazards in general. Though we still want to control them as radiological material, we want to kind of have that level of control around them. As we go up into our megabecquerel ranges, we start getting into our millicuries. These start becoming potentially hazardous, so we want to start keeping them maintained the same way we keep the other ones, if not behind an additional layer. We want to start not handling these as much as we can with our, immediately want to try and put stuff between us, either using these long-handled instruments. And then that kind of doubles down as we get into those gigabecquerels or the individual curies. At individual curies, these start to become significant health hazards, especially as we move up into the few curies. And as we move up into the tens of curies, we actually start cresting into this terabecquerel range. The mnemonic we like to use at REACS is if you hear terabecquerels, think terrible becquerels, for the point of whenever we're dealing with accidents involving sources of this high activity, at best we're dealing with losses of limbs, and at worst we're dealing with multiple fatalities. So these things are significantly concerning just from how much activity we actually have. So the IAEA is really trying to crack down on making, especially these sources, a lot more secure, a lot harder to lose track of. So that goes for the activity of those sources. Like we said, we're going to compare that D value, depending on that radionuclide, to the activity of that specific source itself, and that will give us that kind of ratio. The D value is determined between the lower of either of the D1 or D2 value. Not particularly important, but it's good to know that the D1 value is effectively how hazardous is this source by virtue of its existence. If you were to have a chunk of this material on your countertop, on the table beside you, in your pocket, how hazardous is that to your life and limb versus the D2 value, where the D2 value is more of the malicious hazard of that source. If this were to be aerosolized or turned into shrapnel and spread out, how would that become effective? Which one And whichever one of those becomes the lower quantity needed to do significant harm becomes that overall D value. So once we have that activity, we can divide that number by our specific D value. That gives us that AD ratio. And then that AD ratio will tell us whether or not we're in the danger zone. So we'll find out kind of that ratio from there. As time goes on, that activity will decay away. We can have a category 1 source become a category 2 source as it just decays down. So that kind of tracks the difference between the specific source itself and the radionuclide the source is constituent of. So this is kind of where those AD ratios fall on this chart. And this is how the IAEA has categorized its categories 1, 2, 3, 4, and 5 sources. If we're over that category or over that AD ratio of 1,000, we have our category 1 sources. Between 10 and 1,000, we have 2. Between 1 and 10 is 3. And on down to 4s and 5s, becoming 5 is anything over exempt to 0.01, and then 4 is anything up to 1. These kind of fall off piecewise when we start talking about how quickly is this hazardous to life versus limb. So for example, with our category 1 source, these are extremely dangerous. We've got permanent injury being done in minutes. That's loss of limbs, significant injury. These are potentially fatal on the order of minutes to hours. When we kick down into our category 2, this does permanent injury on that kind of minute to hour time scale. And these are potentially fatal on the order of those hours to days. Category 3 becomes permanent, can deal permanent injury on the order of a few hours to days. Category 3s are unlikely to be fatal unless we're exposed for significantly kind of chronic exposures. So things on the order of days to weeks. When we crest down into category 4, we start not really being any kind of hazard to life and limb unless we have some extenuating circumstances or we have significantly chronic exposures to these sources. And then category 5 is not likely to be harmful, unlikely to be any kind of permanently injured outside of significantly extenuating circumstances and additional comorbidities. So we kind of see these things fall off from 1 to 5 in their hazard very quickly, but that does still make those first 3 categories significantly hazardous. One of the big kind of calls for improvement in this system is the fact that category 1 source category is unbounded. It's simply just anything over 1,000. I'll talk to you in a few minutes about an accident that occurs where the AD ratio is on the order of 22,000. So the fact that we can have something that's 22,000 AD ratio and 1,000 AD ratio is kind of one of the concerns for these. However, when we get that big, we start having entire facilities built around these sources, but that's one of the calls for argumentation. To kind of show how this works in perspective, let's take one of our common medical sources. Let's take something like a low dose rate brachytherapy source. These are typically made of cesium-137. They typically have an activity around 19 gigabecquerels. So let's try and look at these numbers and put them into perspective. We go into that big book of D values. We find cesium-137 has a D value of 1 times 10 to the negative 1 terabecquerel. The mathematicians say, oh, we have to convert that to gigabecquerels because that's the activity of my source. These have to cancel out and become unitless. So I do 19 gigabecquerels over that 100 gigabecquerel D value. I get a ratio of 0.19. 0.19 puts me solidly in the category 4 area. That's kind of what we're doing. We look at these for these categorizations. To show the difference between these two and how that D value changes, let's take another kind of common source of similar strength, something like a cesium-137 industrial radiography source or a cobalt-60 industrial radiator. Both of these are oftentimes on the order of dozens of terabecquerels. So let's take the one from the San Salvador accident I'll talk about later, 33 terabecquerels. Looking at the difference between these D values, the only thing that makes these sources different are those sources. We have a D value of 0.1 terabecquerel for that cesium-137. We have a D value of 0.03 for our cobalt-60 source. So when we divide these out, we get a massive difference. We have this AD ratio of 330 for the cesium-137, which puts us in that category 2 system, but that cobalt-60 source becomes a category 1. There's a number of reasons for this. One of the big ones is going to be how these kind of decay away. And it's also kind of related to our specific activity, if you're familiar with kind of that unit. Pretty much how radioactive per gram is this material. Cobalt-60 gives off 2 photons per disintegration. Cesium-137 only gives off 1. So that makes cobalt-60 a bit more radioactive, a bit spicier as we're working with these. So that's kind of the difference we'll see. So we kind of have to know what we're working with, what category it is, and kind of how it's all going to devolve if we want to start looking at these really critically. But we can still kind of use those categorization systems to tell us what we're probably working with, how hazardous they're going to be, and kind of how we can expect them to propagate if we start seeing accidents becoming involved. So when we look at our common sources, especially amongst our categorization system, we see things like these really big kind of facility level irradiators take up our category 1 slot. And these kind of make sense. They're putting out a ton of radiation. Their purpose is to either kill off these cancerous cells or purify any of the viruses, bacteria in these seed irradiators and these blood irradiators. The whole purpose of these is to sterilize. So we would expect a whole lot of radiation. We expect it to be significantly hazardous. With our category 2, kind of one step down, we have things like those industrial radiography sources, the purpose of which is to kind of push through these concrete, these steel pipes. If I put radio film paper on one side of a wall and I have my source on the other, I develop that film. If I see any brighter spots, I know that I have a hole or a crack in my wall, and we can kind of look into the structure of it without doing any kind of destructive assay. So we can kind of look inside, effectively doing X-rays on these big industrial type endeavors. We also have those high, medium dose rate brachytherapy sources. Once again, just a cancer treatment, but we're coming back multiple times, kind of for those types of treatment. So we expect these to be significant sources. We expect them to be kind of very penetrative, and they can be significantly hazardous, as is very easy to kind of think about. Going into category 3, we start having industrial gauges with those activity sources, any wall logging gauges or well logging gauges. The purpose of these, we're looking to kind of penetrate a little bit of depth into either whatever we're trying to monitor, or for our well logging gauges, we're looking for the attenuation of those potential wells that we've dug. If there's either oil or water or any other kind of material in the surrounding dirt and rock, the attenuation coefficients vary, so we can kind of put a detector behind that as we drop it down the hole. And the attenuation we see coming back will tell us kind of the makeup of what we're dealing around with that. With our category 4 sources, we start dealing with our lower dose rate brachytherapy sources, also any kind of industrial gauges with these low activity sources, things that are just kind of doing more of the monitoring aspect, or things that we're doing, again, for cancer therapy, but for kind of smaller, kind of more pinpoint areas that we can kind of effectively get contact doses on when we're using these catheters. And then going into category 5, we have any kind of these X-ray fluorescence devices, electron capture devices, and a ton of other different kind of small scale industrial meters and gauges and whatnot. Things that are there just to monitor and either see small amounts of changes or differences as we're looking at these, whatever product we're trying to analyze. When we start looking at these sources and how we're actually using them, there's a number of different things that start coming up. Most of the time, we're working with these kind of sealed sources that look very similar to what I have pictured here. At least for my American and English speaking population here, if after this lecture you go out to your car, you notice outside your car there's a small little rod, you pick it up, you see this, it says drop and run, cobalt-60, 350, 3,500 curies. You say, oh man, that's really bad, that's really dangerous. You drop it and you run. And for the most part, you're probably going to be fine. Hopefully we'll monitor your hand and everything comes out nice and easy. But what the IAEA was trying to get at with those earlier sources we mentioned and kind of how the orphan sources all come along, if we start seeing this happening somewhere like Meat Hafa, Egypt, where the common language isn't English or the common population isn't really read up on radiation, if someone finds this, looks really nice, looks shiny, really heavy, a lot of times in these accidents, we see them attempting to use these for scrap. So they end up taking these home and irradiating themselves, their families, to some very severe consequences. So that's kind of what we're working with as we talk about all of these. When we start looking at where these accidents are coming from, we start seeing the accidents kind of propagate in correspondence to kind of how often we're using them. The big ones here are those fluoroscopy and radiotherapy kind of accidents. And this isn't because our nurses or our medical practices aren't safe. These really are just statistically what we'd expect to see with just how much more common these medical procedures are, especially nowadays. So we see a lot of these accidents made up on those medical procedures because that's just far and away where we use these. After that, we start seeing it in industry, which again is just kind of making up what the kind of usage rate is amongst all of these. We look at the orphan sources, they make up about 5% of these accidents. We've kind of harped on that a lot this lecture, but when we look at our serious accidents into our fatalities, that number really blossoms out. And then the other percent's made up kind of just where we see them as well. So the accident rate is kind of respective and representative of how often and how common these are being used. When we start talking about accidents, it's also very important to start looking at how the IEA both defines accident versus incident and how they scale them up. First and foremost, when we talk about the IEA defining incidents and accidents, the accident is anything over that level 4. The incident is anything from that levels 1 to 3. The big difference between these two is they all take into concern effects on populations, effects on the environment. The incidents, however, really care about something that's called defense in depth. And when we start looking at this defense in depth category, this really is defined as kind of our safety alerts, kind of our fail safes. Where do things start coming into play, and how do we stop them from happening? So if we lose power to half of our facility and our backup generator kicks on, that might be a level 2 or level 3 accident. But those backups kind of came in, they saved us, they kind of prevented this from getting worse. That maintains what becomes our incidents. When we talk about our accidents don't care about that defense in depth anymore because the fail safes did not work, because they did not either kick back on or we had significant kind of damage to our population or to our facility. At accident level 4, we have significant effects up to and including at least 1 death. And when we look at these scales, they're supposed to be logarithmic. So the same way the people don't like to use it anymore, but the Richter scale was kind of a 10-fold. 3 is 10 times worse than 2, 4 is 10 times worse than 3. That's supposed to be what this is representative of as well. With that said, there's only ever been 2 major accidents of the level 7 category, and those are Fukushima and Chernobyl. Into our category 6 accident, we only really have 1, and that's going to be the Kashtim disaster. Accident level 5 is something akin to the wind scale fire or something like Goanya or 3 Mile Island. And then accident level 4 is kind of respective of single fatalities. A lot of these are going to be our orphan sources involving a family. So this is kind of these are including stuff like the Meat Haifa incident and a few others. When we start looking at what makes our accidents, this graph looks a lot different. Radiotherapy has kind of taken up the rest of fluoroscopies. Fluoroscopy goes to 0. Industrial stays kind of right around the same. And that orphan source has blossomed from 5% to about 20%. A lot of things go into this. A big part of this is also just how common we're doing these procedures. It also goes into respect with kind of the reporting requirements for these different procedures, especially in the medical field. Fluoroscopy already has such a high kind of intensive expected rate. For there to be kind of these severe reportable accidents, we have to have significant overexposures. For radiotherapy, we kind of have that broad scope of how often we're doing that kind of falling into there. With the industrial, we stay right around the same percentage, but the orphan sources are really what makes the difference in this chart. 5% of kind of all the accidents, but about 1 in 5 of the significant kind of deaths and significant overexposures doing with significant damage to life. And now a lot of that's going to be just because of those, the lack of knowledge, not entirely sure what they're having, and just oftentimes with these orphan sources, where we don't know, we're not able to get that medical intervention quick enough. So when we start talking about these category 1 sources, like we said, that's going to be anything over that level, over that AD ratio of 1,000. These include things like our radioisotopic thermoelectric generators. These are really good at providing power for a very long amount of time. during the late 1900s, so the 80s, 90s, that kind of a time frame, to the 60s and 70s even. The Russian, I guess the Soviet bloc countries like these a lot to kind of power their way stations and their lighthouses, things that were miles from civilization, just for that to be another way station or lighthouse. You basically take a beta source on like strontium-90, we slap that around this, we surround that entirely with a tungsten or steel kind of block shield. If you remember from Megan's lecture, that generates a lot of brimstone radiation. But as those betas are kind of interacting with and colliding with that steel, we get a lot of heat buildup. If we put kind of we can attach a heat sink to that, start converting that heat energy into electric energy, we have a really good battery. Then we have to shield for those strong X-rays that we've created. And we see a lot of accidents happening with these getting lost, people breaking in. They see an unmanned facility out in the middle of the woods with a bunch of do not enter signs. People go in looking for scrap. They start getting into these sources. They start exposing these thermoelectric generators, taking away all the shielding. We now have a massive X-ray source, and we have a number of accidents coming out of kind of these Soviet countries with these. Today's day and age, we're really using these predominantly for kind of space travel, as we effectively have a battery with a half-life of some hundreds of thousands of years. So we have these really significant batteries we can send out into space. With our industrial radiators, these are massive facilities. We'll show a more specific example of these as we go on. One of the accidents we talk about involves one of these. When we start talking about teletherapy, we have these really strong sources kind of for this cancer treatment. When we start talking about gamma knives particularly, this gets into the fact that when we have aggregate sources, like our gamma knives, which are made up of some 200, quote unquote, weaker sources, each one's still significant. But when we take all 200 of those sources kind of in aggregate, that activity is what we account for. Our blood and cedar radiators also fall in these categories, just because they're these massive radiators with the intent to kind of sterilize and purify. So when we're looking at a source like this, let's look at one of our industrial radiators, typically made either of the cesium-137 or cobalt-60, oftentimes on the range from a few hundred terabecquerels to a few hundred petabecquerels, which is just an unrealistic amount of activity. The terabecquerels, we told you, think terrible becquerels because they're significantly hazardous. Getting into petabecquerels is 3 orders of magnitude higher, so we can do some significant damage very quickly. We typically have facilities built around them like you see in the picture here. And we'll talk about the accident that happened in San Salvador, where we had a bunch of these pellets kind of stacked together into pencils. We take these pencils, stack them together into sheets. We take these sheets and stack them together effectively into this source plane that we'll see at the bottom of this pool. Typically, we have about a 5.5 meter deep storage pool that'll stay in most of the time, acts as a really decent shield, acts as a really great way to keep it away from any of the workers, especially as we kind of go in, place these boxes for sterilization, take them out after radiation. We'll have some pneumatic hoist that will raise and lower the system. So when it's raised up, it starts delivering somewhere in the order of 20,000-ish gray to these boxes and packages over 10, 12 hours. There are a number of safety locks that go into this. Anybody who's worked with the radiators are familiar. There's typically a switch at the top that says, hey, the source is up. If you come in here, you'll die. There's a switch at the bottom that says, hey, the source is down. It's safe to come in here. If neither of those is on, it's in transit. It tells you and screams to you saying it's there. And we typically have gamma detectors all over the place that says, hey, if we're detecting gamma, if we're detecting radiation, period, we're not going to let that door open. So normally there's tons of safety interlocks with these systems. When this source specifically was installed, we had about 4 petabecquerels of activity, which is absolutely crazy. 108,000 curies for those of us who prefer the American system. At the time of the accident, we had decayed down to about 0.66 petabecquerels. That's 660 terabecquerels, or 18,000 curies, depending on which system you prefer. So if we do our math really quick, we'll see that if we take those 660 terabecquerels, divide by that 0.03 D ratio, or D value, we get a ratio of 22,000. This activity right there, if you stand 1 meter from it at that 3-foot distance, you get about 244 sieverts per hour, which is about 24,000 rem per hour for those of us who like those American units more so. So this is an insane amount of activity, just an insane amount of dose coming off of these. We start talking about this incident, a few things start happening that we almost always see. This incident doesn't really happen in the middle of the day, so everybody at work kind of work on it. This happens at 2 o'clock in the middle of the night. Earlier in that shift, we had a few different power outages. This incident happens right in the middle of the San Salvadoran Civil War. So the power grid was kind of less reliable than we would have liked it to be. But the facility had kind of gotten used to kind of dealing with these incidents, kind of cycling power until everything comes back on and letting everything kind of run its course. At some point in the night, around this 2 o'clock in the morning, the worker kind of notices that the source transit alarm has been going off for a long amount of time, saying that, hey, that source has now at some point been caught. Something's going wrong in here. His plan to go fix it is to go outside, kind of climb up on the roof where that winch connects and raises that kind of coil with the pneumatic system. He applies a manual overpressure of the system. Theoretically, that pushes it all the way to the top. He then cuts the pneumatic line system. So theoretically, it falls all the way back down. And then for good measure, he goes ahead and says, I'm going to go ahead and manually flip that safety switch on the top to the down position. So right here, we start seeing our first of a few different mistakes of massive import, kind of manually overriding any system with the intent of that system being to save you or tell you what is going on in that room is a big should not do. So we have our first kind of massive incident. There are a number of different safety interlocks, one of which, the next being the door to the facility. And originally, this facility had this fixed radiation monitor that kind of reads the radiation in the room, and if there's radiation, kind of locks it, preventing the door from opening. But one of the capacitors inside this detector had kind of blown out about 5 years prior, and so this device had become massively, the device no longer worked. They called to the manufacturer in Canada. They tried to come down to do maintenance. Right after they land at the airport, there's a rebel attack off base. The Canadians kind of say, all right, we'll come back later. They fly back and never end up coming back to kind of do this maintenance. So what had happened is, in the meantime, they don't just not use their irradiator, but they found that if you push the alarm button and then hit the check and test buttons really quick back to back, you can trick our system into thinking that this door will open. So again, we've now overridden a safety interlock. We've overridden something with the intent of keeping us safe and alive. We kind of manually done away with that. One of the next things that happens is our worker opens the door and does what he procedurally is supposed to do. He opens the door and it says he's going to let that kind of radiation vent out of the room. This is why it's important to know our procedures and to know why we do our procedures. He was right to kind of let the room vent, because in these massive kind of flux environments, we can generate ozone. So that is to let the ozone kind of fluctuate out, make sure all that air in there is safe and breathable. But not knowing the radiation doesn't vent out, or not knowing kind of the further steps in those physics, really starts leading to his demise. He kind of comes in here, walks around, he removes these first few boxes right next to the source, actually looks at our source plane and sees the problem. About halfway up between these two levels, the pneumatic cable has gotten wrapped around some of these distended kind of polyethylene boxes. He says, well, this is kind of a problem. I can't really do this myself. So his plan is to go out, get 2 other individuals from the different department, kind of bring them in and start removing these boxes so they can unwrap this coil. So this plan goes through. They remove these first 3 boxes on kind of this upper level, start kind of finagling right around this source. The plan being that individual A is our RADCON worker. He's going to be the one that kind of leans over, unwraps this cable, lets it go down. Person B and C are both in their respective positions, kind of pulling on that cable to give him enough slack to kind of unwind it. Everything goes through. Their plan works great. When that source plane kind of hits the water, we start seeing that really nice blue Cherenkov radiation glow. And our rad tech starts to realize maybe they shouldn't be here. They should leave the room. If you'll remember from Carol's lecture about kind of how these things start progressing, as they leave the room, individual A immediately throws up. So we know that he has some significant dose acquired. He entered the room roughly at about 2:30, kind of looked at everything, said, okay, went back, did about 5 more minutes of work with these other individuals. So we really only have about 10-ish minutes of exposure. 30 minutes later, we have our first issuance of emesis. All that said, we can start expecting significant doses. Individual B actually drives individual A to the hospital. We start seeing all these individuals start taking some pretty serious turns. When we start looking at individual A, based off how they were standing around the source plane, it was mostly centered around their lower body. So we see massive dose to all their lower bodies. But individual A, being so close up on it, gets a whole body dose somewhere between 10 and 15 gray, which is above survivable even with these significant medical standards. He starts showing signs of erythema on day 3, which is significantly faster than we would hope to see it, kind of showing the extent of his exposure. Eventually, he ends up passing away due to his wounds on day 197, which kind of goes to Carol's point when she mentions that LD 50-60. It's not that if you make it to that 60-day mark, you're fine. These things can be kind of very worn out, very drawn out, and very traumatic. All those comorbidities, just making that mark isn't necessarily your saving grace. We start looking at individual B. He was just a few steps back, maybe 1 or 2 feet from individual A, and that dose kind of goes to show a massive point, or that distance goes to a massive point to his dose. He gets about 30 gray to his feet, gets a massive dose to his lower torso between 3 and 16, but around that mid-torso area, he's now a little bit safer. He actually is able to go back home after he drops off that individual. Everything kind of goes fine with him. He actually goes out and plays soccer on days 5 and 6, ends up back in the hospital on day 9. He ends up getting a double amputation, but eventually is released from the hospital. So with just that one-time exposure going into that room, we have a double amputation. Individual C followed a very similar kind of prognosis, but went in significantly later. Individual C ends up going to the hospital on day 26 with a little bit of foot pain. Based on the estimates he told us, their dose rate should have been lower, but based on what we saw responding in his feet with that kind of desquamation, we know that his feet had to have gotten at least 10 gray. So this is what we're talking about when we say you make a very good dosimeter. The body will tell you kind of what dose you acquired. He got away with no amputations, but he did walk with a limp for the rest of his life, and he stayed in the hospital for roughly he stayed on sick leave from work for roughly 200 days. So once again, with just that short kind of exposure of roughly 3-ish minutes based on their histories, we see a fatality, a double amputation, and a permanent limp. So these category 1 sources are significant. There's a very similar accident that happens in Samutprakan, Thailand, with one of these teletherapy sources. So significantly smaller, only, quote unquote, only around 150 terabecquerels for these cobalt-60 sources. This one's only 15. It gets donated to a clinic. Eventually the clinic goes under. It basically gets end up in a scrap facility. Some individuals try and collect this for scrap as they kind of tear apart this teletherapy head. Our source container falls out, ends up kind of mixed along with the rest of the scrap, eventually leads to the exposure of 7 individuals being injured to these exposures and 3 deaths from our scrapyard workers kind of working directly with it, and the scrapyard kind of assistant who stayed about 30 feet away inside most of the time, but spent so much time there that unfortunately the dose was too great for them to overcome. We're looking at category 2 sources. We do take a step back, but we can still see these significant kind of doses and these significant kind of dose rates. These are going to be our industrial gamma radiography sources, those high dose rate brachytherapies, and some calibrations. These involve sources like the ones Carol mentioned with that radiography source in Yanango, kind of showing you the size and scale of everything we're dealing with here. When we're looking at these are typically what we're working with. Far and away, the most common ones are going to be cobalt-60 or iridium-192. Again, these are only on the activity of maybe a few terabecquerels. That number alone is more than enough to cause significant damage. In 2011, we actually have an incident with a radiography trainee. As they're kind of retracting the source, the final bit or that pigtail sticks out, not wanting to go through the proper kind of procedures and maintenance. He kind of finagles with that with those first 3 fingers of his, takes about a minute or two kind of pushing it back into the box. And we see some pretty significant kind of numbers on this dose rate. So kind of putting those numbers from Carol's slide back into this, what we see here, we end up seeing heme blistering on those 3 digits. So we know that he gets about 20 to 30 gray to those fingertips. However, if we recall that importance of distance, his whole body dose is only 1.4 rem. So we have a really high amount of exposure to our fingertips. We have a few bit of those amputations of those posterior digits, but the whole body dose is less than what we could have gotten as a rad worker. So this is what we talk about when we start talking about point problems and how we can start making these assumptions in general. Going into category 3 sources, kind of taking a further step back, we start having those well logging gauges I was telling you guys about. These are typically very well-maintained sources. We see them most of the time being lost on highways as the industrial crews kind of put them on the back of their trucks. They aren't loaded down properly, or they bounce outside their containment. They fall off the back of the truck, kind of explode down the highway. But those sealed sources hold up, maintain, and just end up on the side of the road. So what we do is we just backtrack that route with some of our detectors, and we can effectively drive right back up to it. This happened, I want to say, in 22 in the Australian outback, a pretty big, well-known case. But because of how easy they are to find, we really just drive right up to it, and nobody's any worse for wear than maybe a few dingoes. We got category 4 sources. We don't expect these to be any kind of hazardous unless we have significant kind of exposure times or significant comorbidities. These are our low-dose brachytherapy sources, some industrial gauges, bone densiometers. The big one that we have for category 4 as an example of those comorbidities is that Indiana-Pennsylvania case where we had, I want to say she was 80 some odd years old. We had a rectal cancer therapy patient. The brachytherapy source kind of broke off, disconnected from the cabling inside the catheter in our patient. She gets continuous exposure for about 72 hours and then eventually passes to all these comorbidities. It kind of goes unnoticed for a few days, kind of as expectant end of life care. We don't find out about it until this ends up in the waste stream, goes to one of the waste facilities, and flags their detector. Luckily, as we kind of figure that out, write about it, a very similar incident happened about a week or 2 after we found out and the report was filed. And those techs were up on their stuff. So when they had a few issues with their detector, they were able to pull out their detector. It's going to go right up to their patient and find out the exact same thing that happened. So this is kind of why we like to do our review of accidents, to kind of keep them ever present in our mind, have us think about it, just to be safe and overabundance of caution. Looking to our example of category 5 sources, these are these significantly low dose sources. These include our PET check sources that we can use for our operational checks and our calibration sources. These include the brachytherapy plants or implant sources that we could probably put inside an individual and let them decay away on their own due to that low level activity. Electron captures, a few consumer products fit into this category. And once we breach into that and the exempt quantities, we get so many more of these uses of radiation. So it's really important to be kind of present and kind of ever mindful of where we're going to find these, what we can see of them, especially those of us who work with radiation kind of on that more present field. I hope I'm okay. I don't think I'm only a few minutes over. Any questions on that? Thank you.
You do have 2, if you can hear me okay.
Yes.
The first one is just the difference between an accident and an incident. And if you don't mind, I'll take that one, Dylan. It's something that we do in the disaster medicine world because you can have an accident that isn't meant to happen. An incident can be on purpose, or it could be accidental. So verbiage tends to lean more towards calling everything an incident, even though it could be an accident, but not all. Well, it gets a little splitting hairs after that. So I'm going to leave it at that one. That could be a longer philosophical discussion. The second one for you, let's see. It looks like this is a lingering question from the previous lecture, but relates to this one as well. Are ALIs calculated for adult exposure without regard to age, i.e. children with growing bones, etc.? How do you communicate risk for the patient themselves or the loved ones they may be in contact with, say a nursing mother? Same concept and question applies to the AD ratios. Is the harm calculated with healthy adults in mind only, or are there considerations for variations in age, etc.? And you may want to read that one. That was a multifaceted question. Good question.
That's all right. If I don't clarify it enough, let me know. And if I say anything either non-conclusive or omissions, fill out for me instead, Carol. The ALI, as far as I know, is developed and intended with the adult population in mind. It's based off of reference man and materials. So it really takes into account, because it takes into account reference man, it's not a very good model for, I shouldn't say it's not very good. It doesn't exactly match most individuals. Reference man, I think, is somewhere around like 5'11", 160 pounds, with a breathing rate of X, Y, Z, and a few other things. So the ALIs, as far as I'm aware, don't really account for minor populations. And I can kind of look into that and find out what we would do for a minor on that front. As far as the AD ratios are confined, or the D values are defined, I don't think they take any population into concern at all. I think for the most part, those D values are defined as how much radiation they give off, and then kind of relating that back to not ALIs and RLIs, but kind of dose conversion coefficients. So we'll look at how strong the dose rates are, how well it would be aerosolized, how well it would be spread out, and then kind of go from there. We start talking into, if we have a patient with 10 ALIs or 5 ALI, the big way to get risk across is going to be kind of the, I want to say it's Megan, if I miss, one of the ICRPs quotes about a 5% increased cancer risk per sievert, or something along those lines. 1 sievert is 100 rem. So if we only have 1 or 2 ALI, we're at 5 or 10 rem. We only have 5% more likelihood of cancer over the lifetime. For 100-ish rem, we can kind of start putting those into question there. My boss has a great anecdote. When he met his wife, she had asked about his rad work stuff, and he kind of used that risk relation and pretty much told her if he did the same job and he got the same dose rates for the 200 years, his rate of cancer would go up 5%. Counterpoint, when you're talking to patients, especially those who are more concerned or scared, I think quoting them direct numbers and risk relations and 5% per sievert is a good place to start. But when we start talking about the numbers correlating with people, I think finding the humanity in it all is going to be a lot more important. And that could be anything from relating it back to stuff like it's equivalent to Grand Central Station, or saying it's equivalent to X many bananas, or saying it's equivalent to the amount of radiation you get over so many X-rays, might help put them at more ease. And I hope that answers the question.
I think that was great. I'm going to reach out to our ACMT coordinators here. I think it would be cruel to not give everyone at least a 5-minute break. If that would be good with you all, we can certainly still finish on time, and we might even finish in, I don't want to get the hopes up for a little bit earlier, but we should still finish on time. Is that good with you guys?
Sounds great.
Okay, so what time do you want us back? You know, just say 25?
Yeah, let's say Eastern time 3:25. So
Great, thank you.
thank you.
All right. I did want to share before we get going. Hopefully, you can see this the John Hersey book, Hiroshima. Links are in the chat, so please make sure to look at your chat. Girls of Atomic City. Excellent read. These are all very short read times on these because they're so interesting. This is just one of the FEMA documents. This is the guidance for the first 72 hours. This is an excellent resource to have. And last but not least, and which leads into this discussion, is NCRP 161. This is volume 1. There is a volume 2. Anyone who deals with internal contamination, this is what you want. You can get it digitally. You can get it hard copy. So I am going to share. And yes, you may see my dog again for a minute. Let's see if I can, still not sharing, share. And let's pull that over and let's get it in presentation mode. And all right. Let's see, except now I can't advance it. Yes, I can. All righty. So a lot of my work here has already been done, which is so wonderful having the team that we have. They are so awesome. So we'll be able to get through a lot of this with no problem. So everybody sees it. Everybody can hear me. No worries. You've seen my disclosure. I have nothing to disclose. So we shall keep going. Yay, thank you for the thumbs up. We're going to talk about methods of management for internal contamination. You have already seen the cool graphics. Megan and Dylan have shown you a lot of this. I'm going to jump more into the medications. I am going to focus on FDA approved medications, but we'll mention some of the others as well. So, okay, I don't have exciting graphics. They had some really cool graphics. What I can add to the mix here, if you will, is just that I'll digress. I'll go down any rabbit hole that within a mile away. So As far as inhalation, I already told you earlier about the two cases we had during COVID where they were just wearing the procedure mask and ended up having an incident, an accident. There we go. That's a good. That was a good question. I might not have given you an all-inclusive response to that, but that's how I look at it. So, but at any rate, they were using a procedure mask for COVID precautions, and they ended up getting the contaminant on the mask. It wasn't a job that required respiratory protection. Perhaps they reevaluated that job afterwards because stuff can happen. Ingestion. I will briefly show you a slide on Guyana. If you're not familiar with that case, it's an IAEA publication. There have been many other publications regarding that situation. Very sad one. A little girl literally did ingest some cesium-137. So we'll go through a little bit about that. Absorption through wounds or skin. Now, part of what Dr. Kiernan was talking about, and part of what Megan will talk about just briefly on the next one, deals with the absorption through wounds. We consider that a very high priority because direct access to the systemic circulation. And then skin. Tritium is a classic absorbed through the skin. However, all you have to do is wash it off and then it's not really an issue. And then injection. I do like to give this example. A lot of and one of the questions earlier dealt with the types of situations for these incidents. We get a lot of calls. For whatever reason, we get a lot more calls than we used to get. It's not a bad thing per se. We do get a lot of calls from concerned public. Megan already mentioned the veterinarians and the I-31 cats. I actually had a cat undergo iodine ablation of his thyroid. That was back in the day when they only did that at veterinary schools, and they kept the cats for a very long time. We had and I'm just going to go down a different rabbit hole with that. We had a great call from an individual who happened to be a healthcare provider, and she was really worried because she had brought her cat home from having this ablation done, and I won't say she was frantic, but she was clearly upset, and she said, "Oh, I fell asleep on the bed, and my cat, when I woke up, my cat was about 3 feet away from me, and I slept at least 3 hours." And Dylan and I happen to be big cat fans, dogs too for me, but big cat fans. And we were on the call and we were going, "Oh, you lucked out," because well, we happen to really like cats. And basically, from what you're telling us, you have no concerns. I mean, maybe don't strap the cat to your body for hours and hours and hours and hours. So that'd be a whole lot more dangerous than radiation from that. But essentially, we told her, "Hey, your cat's been through some trauma. Love your cat. It's all good." We did have an injection injury, not really an injury, an injection case. And we've had a second one recently similar to it, where the individual had no idea that they had had any type of a puncture. And this is working in glove boxes, and you have your inner cotton gloves. And then, they get into these big, think Homer Simpson, glove box type situations. No offense to those in the industry, because I don't mean to, it's just making light of it. But this individual had been in a glove box. He was getting ready to survey out of the radiation area, and he found contamination on a hand, and he's sitting there thinking, "Okay, this is really weird. I didn't do anything." So he stops immediately. He gets the radiation control professionals to come over. They start looking at everything, surveying him, and they finally got to looking at the PPE. And when they inverted his cotton liner glove for the one hand, there was a single little dot of blood. And as it turned out, he had this very microscopic injection through that glove. turned out to be nothing significant. But just my rule of thumb on these types of any type of radiological or a nuclear incident is always expect the unexpected and never say never. Those are two of my rules of thumb. All right, so you have already seen really good graphics with these phrases: intake, uptake, incorporation, so it gets included in the metabolism, decorporation, again, the Latin decorp, removed from the body, so just kind of a cool term, I think. And then a few additional terms that we'll talk about: target organ. Everyone can come up with an example of this, and if you were in here with me, you'd all be going, thyroid gland, and I'd be going, yes, spot on. That's exactly it. I will throw in one more thing, that for this Goiânia case, these individuals had internalized cesium. And when they, much like a lot of our nuclear medicine radionuclides, the cesium would come out in some bodily fluids, particularly the sweat. So every time these individuals started sweating, their sheets, their bedding, their clothing, etc., they would be contaminated. And did it scare the environmental services people away? No, they wore gloves. They put it in trash bags. They put it in the rad waste area. So there are some ways to deal with that and to stay pretty cool and collected while doing it. So if I go too fast on these, let me know, but I have a feeling nobody's going to object since you've already heard a large part of this. And we really want to get to the medical treatments here. But physical properties obviously make a difference. And I am preaching to the choir. I know there are a gazillion toxicologists on here, and you guys, please forgive me, because some of these terms I'm not going to deal with them as a purist would deal with them. So I just ask a little bit of leeway on some of this. But I think we all agree physical properties, chemical properties, and the radiological properties, all very important. Dylan and/or Megan, I forget which one covered this, but talked about whole body counting. This is something, and I think there was a question that was asked about, are these portable? As a rule, not a whole body counter generally isn't. However, and you guys, I'm sure there are a lot of people that would jump in to correct me on this. I'm pretty sure you can have mobile units, but it's not easy and there's not a lot. So I'm just going to leave it at that and leave it at you guys can discuss that with Megan and Dylan later. But certainly, that is a helpful tool. Bioassay. And this is something we learned very recently. And some of you all who may be on this call or on this webinar, we have probably spoken to quite a bit recently, because I've been remiss in really saying we love doing this course. We love all of our colleagues at ACMT and NAACT. We have had a long-standing relationship. We really work well and integrate well together. So just want to get that one out there. But we recently learned through a case that we shared with one of the poison centers that CDC does, and I knew they did bioassays, radiochemistry bioassays on urine. What we learned was that they will do a spot sample, not a 24-hour collection. Well, that makes sense, because they're really in place for like mass screening capability. And that's what they're really designed to do. However, they were great to work with. I can't say enough good things about John Button, who runs that CDC lab. He's a great guy. But urine is often done. Feces also. If you want to read, and I'm not, I really, sad to say, I'm not sure if you can get all this digitally. We published proceedings from our 2011 International Symposium. And in that symposium, it was after Fukushima, so we had some good article or good presentations and subsequent published articles, chapters, if you will, in this proceedings book that covered Fukushima. We had a lot of the major accidents that have occurred in the more recent times. And we had a speaker from the United Kingdom and from England specifically at that time, Public Health Service. And she talked about, actually, I can tell you her name, Jill Mira. She spoke about the Litvinenko situation, that incident, and how difficult it was to do all of the urine collections and the fecal collections for that case. I imagine you can find other publications by her. I'm going to work on getting that digitized and somehow put on our website or something. That's a big wish list, because I'm not sure it's out there digitally, and it should be. But at any rate, if you have the opportunity to access that, please do, and you can certainly look her up and get her publication. Also, excised material from wounds, that can also be used. Now, I don't know, I think maybe Megan mentioned EPR, electron paramagnetic resonance. EPR, essentially, I'm going to simplify this, is going to measure the radiation-induced free radicals. And it can be done on textiles, bone, tissue, lots of things. It's still in a research status in that you can't just call up LabCorp or someplace like that and have your test done. It still takes time. The U.S. Naval Dosimetry Center can do this. There are EPR centers around the world, so it can be done. It's probably not going to be the test at this moment in time that will give you the clinical guidance, but I don't know. It may have evolved, and I have just missed that evolution of it. But it is out there as an example. Also, when we get an alpha emitter, and oftentimes with DOE sites, we're dealing with legacy waste. We have, obviously, there's plutonium, there's americium, there could be all kinds of things. So that when we get alphas internalized, those can be very difficult to get a dose estimate on because they're going to be so easily shielded, which our team has done a lovely job of discussing that. So at the end of this, we'll get to some techniques that can be done using excision, and also I'll give you some maybe not precautions, but just some things to consider when using that as a method. Nasal swabs, nose blows. We've also done this fairly recently. I believe that was in conjunction with another poison center. We also have one state, and we won't call it out because the state's done a great job, but we've had one place in one of the states in the U.S. who's had multiple different incidents, and the nasal swabs, nasal blows were quite helpful for us. And I had someone say, well, then why didn't you do an oral swab? And it's like, the oral cavity clears so rapidly, it's not going to be that helpful. If anything, when you're doing the survey, spend some time around the nose and mouth and then do the nasal swabs and blows. Oh, and I also had someone say, well, wait, some of these countermeasures are all for oral to prevent absorption. We're talking about an inhalation. Well, there are a couple of things to know with that. You have to look at the kinetics of how that particle is processed through the body, particularly when we are exhaling and we're swallowing. We tend to get a lot of orally ingested and nasally inhaled things getting into our gastrointestinal tract. So that some countermeasures do work well to block absorption where there's really no other way for them to be all that beneficial. And that goes down another rabbit hole that if you come to REACT sometime, or if I see you out at a course, we can sure discuss that one in a lot more detail. Sputum. Actually, the French like to induce sputum and use that. So, I mean, it's there. You can do it. You can do a spot check on urine. And this doesn't mean sending it to CDC, though that's a good technique. You can get a sample, do a spot check. Obviously, if it's an alpha, it's going to be probably shielded. The other thing is there is a commercial lab. There's more than one, I'm sure, but one that we know and have used in the past is GEL Labs in South Carolina. They do both urine and feces, and they do 24-hour collections. And if you go to their website, they'll tell you how to collect and where to send it and how to do all that. All right, the inhalation pathway. Size, yep. Size is going to help determine where it's deposited. I feel certain that almost everyone on here can tell me, let's see if this is my next slide. No, it's not. Hang on, it must be the next one. Oh, well, it still works, but oh no, let's stick with this. What is if you were trying to design a biological weapon, what would be your, this is a bad question, I hate even asking it. What would your goal be for particle size for maximum bioinfectivity? And I know you really can't answer, and I'm not monitoring chat right now, but certainly at least 1 to 5 microns, or yeah, nanoparticles obviously would be the best. But this 1 to 5 micron, you're going to be depositing whatever particle it is into those terminal alveoli, pardon me. This is just showing you how quickly, as a rule, the anterior nares clear, and the nasopharynx, as you can see, is pretty quickly. We did have a case that you can look up. I did put in the links, a link to our publications, and I think most of them you can just pull up for your use. But we did have an americium inhalation case where we worked with a toxicology fellow, at least I'm pretty sure he was a fellow, and we worked with the VA Medical Center, and there were many players involved, but this gentleman had positive nasal swabs and blows 2 days after inhalation. This should have cleared in 60 minutes. So that's when you really have to, stand up and pay attention. So those terminal alveoli, we're talking months. So keep that in mind. GI tract, average clearance. Okay, I'll go with 48 hours, 1 to 5 days for a range. So if you had something that was radioactive and it's sitting there in your intestines, and let's say you're someone who, for whatever reason, your typical clearance is 2 or 3 days. That's not a good thing. I mean, it's okay for you, but not if you've got a radioactive substance in your intestines. You would want to decrease that stay time. Quick and easy ways to do that. Increase fluids, mild laxative, assuming there's no contraindication for a mild laxative. All right, general principles. Again, I'm preaching to the choir for the vast majority who are on this webinar, but for those of you who aren't toxicologists or want to be toxicologists, a lot of these insoluble substances, they're going to go out through the feces, and it makes sense. If you think about fiber, if you think about insoluble fiber, what does it do? It speeds up the process through the GI tract. It passes through with the feces, and obviously soluble is going to go out through the urine. Now, this was something we did in we published it in 2019. So think we looked at 2008 to 2018. And, oh wait, it was published in 22. Well, okay, but at any rate, a 10-year period at REACTS. You can see all the cases that we dealt with. And it may be a little surprising to you. And the reason we were prompted to do this article and look at this is when the meeting was being put together, we had a very well-known internal dosimetrist from another country say, no, we shouldn't even have, we should not even have internal contamination as part of this meeting. No, it's so rare. No. And then there were a couple of other countries along with us kind of raising our hands up going, lucky for you, but no, it does happen. So just looking at these statistics, you've had some time to look at some of the oddities, and that's why I always say expect the unexpected. You can see the top 3 we had down here, tritium. We had some overseas calls with these in general, not just the tritium, although I think one of the tritium could have been overseas. Iodine, those were mostly from veterinary treatment with the cats, and the veterinarians must have a superb network for spreading our phone number because our calls have increased dramatically with that, and we're happy to do it. They're wonderful people. And they do fantastic work. And then uranium. Now, some of the uranium calls, a lot of our toxicology friends, I have heard, at least in the past, talk a little bit about uranium hair sample test and all of the pitfalls that can come from that. So we have had some legit, and we've had some maybe not as legit. But over this 10-year period, we had 250 people impacted by this. We had it was either 4 or 5 administrations of DTPA and in multiples in some cases. And again, it was at least 4 different countries in addition to the US. So as you see, it can happen. It's not frequent, but it happens. This will rub some people the wrong way. We've taken some real liberties with how we describe the treatment method, and it's done for simplicity's sake. And one of the questions earlier I saw was something about the periodic table. And I answered back, and I sure wasn't trying to be snarky with it, but I answered back, you'll be able to rewatch these videos, make sure you watch that section. When I first sat through this lecture way back in the day, first time I'd ever heard it, it was a beautiful discourse on the periodic table. I mean, it was fantastic. At the end of it, I couldn't tell you one single countermeasure to use for any radionuclide other than iodine and the iodide, potassium iodide for iodine 131. And I already knew that one. So we've come up with these 8 categories, and I'm going to give you examples of these as we go through. And again, give me some liberties with this. It's not for the purist at heart, but it is simple and it gets the point across, and that's what we're after at the end of the day. So ion exchange under the category of reduce or inhibit GI absorption. Well, we're going to talk about Prussian blue or radiogardase in just a moment. It is FDA approved. These are not cathartics, laxatives. I mean, obviously, if there's no other contraindication, a lot of the over-the-counter antacids. And no, we're not saying go out and take Tums, but there are some things that can be done that will reduce and or inhibit GI absorption. Just makes sense. It's intuitive. The one that isn't as much intuitive is Prussian blue or radiogardase. I am going to go on this recording with a memory tool I use, and I can't say I'm proud of it. It's very, very crass, rudimentary, but you will remember. I would bet some money on, not a lot, but I'd bet a little money on. But I'm not a betting person, so sorry. So at any rate, one of the side effects of Prussian blue is blue feces. Prussian blue gives you, and again, pardon the term, blue poo. So Prussian blue, blue poo. So you want to seize the blue poo. Think Prussian blue. I know it's ridiculous, and thank you. At least there's one person who finds it funny and not offensive. So, but you know, a stupid memory thing. It'll help you remember it. So this is what is used for cesium or thallium. Oh, thank you. Thanks so much. I always feel really weird saying that. But yeah, so what this does, I mean, the Prussian blue or radiogardase, I mean, it passes essentially, you know, unchanged. Very low side effects. Again, blue feces and constipation. Now, I will throw out there, keep in mind that if it's for, yes, that was a good one, for thallium, thallium can cause constipation. So that's going to be a difficult thing for you to figure out, you know, which is causing the constipation. I was about this is my gut tells me, my intuition tells me that I would rather err on the side of thinking that the constipation is caused more from the thallium than it would be the Prussian blue or radiogardase. So I'm beating this. I'm digressing. Let me catch up and move on. So essentially, this is going to pass through. It works extremely well. We particularly get to work with our Poison Center colleagues on more of a frequent basis than I would like, unfortunately, on thallium poisonings or alleged thallium poisonings. This one I was very well aware of because I was in Chicago teaching a course. And we got the phone call, you know, hey, you know, they're needing to get some Prussian blue to New Jersey. And it was during one of those massive snowstorms that, yes, I know in Minnesota they call it a Tuesday, but it was like Snowmageddon. I think it was the first Snowmageddon. And they didn't realize this was happening until the patient was really starting to crash in the unit. And it was one of the nurses that did kind of come up with thallium as a possibility. And she had read the Agatha Christie novel, I think it's The Pale Horse. I've yet to read it, but it is about thallium toxicity. And a lot of people, here's an interesting bit of trivia. A lot of people, after she wrote that book, really got onto her because they were saying, hey, you're teaching people how to poison people. And then later in life, she was then kind of lauded for it that, oh, thank you. You're actually helping us figure out what's going on by increasing awareness. You will probably hear some very interesting things about thallium tomorrow. I would bet my hat on that one. So I don't want to steal any more thunder from our wonderful toxicology friends. So I'm going to switch over and talk about Goiânia for a couple of minutes. If you want a great example of how to handle a radiation dispersal device, or dispersal event, however you want to call this. This was the massive spread of a handful of cesium salt, cesium-137 salt. That was obtained in a very interesting way. How am I doing on time, guys? I don't want to go over. Oh, and I need to pick it up. So I'm not going to go into details on this, but needless to say, it was stolen from a teletherapy head in a pretty much abandoned clinic. There's a lot of stuff that goes with that incident. But the bottom line, they surveyed 112,000 plus people in a soccer stadium using a beach chair with their whole body counter that initially they had to raise so high because the rates coming off of these people was just crazy. And as time went on, they could lower the device. 46 individuals were treated with Prussian blue or radiogardase. Now, I'm going to kind of foot stomp on a couple of things. Do not go to an art supply store. Do not go get your nuke med, DTPA, essentially. No, we're not even on that. Don't go anywhere. Don't go anywhere to get your Prussian blue, except from a pharmacy. Make sure it's radiogardase / Prussian blue. And the only reason I say that is because that is a purified FDA approved form and it can cause damage if you do otherwise. So with this, 4 individuals died. This was the biggest amount of data obtained for the FDA to secure FDA approval for Prussian blue or radiogardase. Initially, and this is important too, because this came out recently as well, some of the adults in this case received up to 10 grams a day of Prussian blue. So talk with us. If you've got a thallium toxicity case, if you got a cesium case, I'm pretty certain we're going to be in on it. But if you've got a thallium toxicity case, please give us a call. Let's talk through it. We've even gotten some pretty good literature that we'll share readily. The FDA recommended dose for adults, 3 grams orally 3 times a day. Now that's a lot of capsules. And yes, you can put it down an NG tube, make a slurry, what have you. If they take it orally and the capsule ruptures, it will stain the teeth. I don't think it's forever, but they'll have blue teeth for a while. For children, 1 gram orally 3 times a day. We talked about the side effects. Block the uptake to the organ of interest. Every single one of you knows this. The thyroid gland. And what do we use? Potassium iodide. Iodine 131 is one of those fresh fission products. After a reactor incident, after a weapons test, after a weapons detonation, all things involving fresh fission products. The best thing is to take it before you enter the area of the plume. And a lot of you may say, well, that's ridiculous because that doesn't really work. Well, it does. Our nuclear power plants within their 10-mile EPZ do have distribution for KI. Certainly a lot of other countries have their certain stocks where they keep in certain strategic places. Plus, you could be a first responder, military personnel, DOE, NNSA personnel, or others responding to this and having to go into an area where the plume is still there. Now, it is best if you can be in adequate sheltering and or evacuate prior to. That being said, give this within the first 12 hours. Otherwise, it's really not going to have enough time to saturate your thyroid gland. This is an old table out of FDA, and I love it. I'm going to keep using it as long as I can access it. The reason I like it, adults over 40, your predicted absorbed dose to the thyroid gland should be greater than 500 centigrade. That is a whopping good dose to your thyroid gland. So keep that in mind. There are some benefits to getting older. That may be one. I also like that it breaks it down by number of tablets and gives you the dosage for each age group on here. Now, ideally, you should continue the dosing till the risk goes away. That would be the plume cloud passes over. The area is evacuated when it's safe to do so. Sheltering, adequate sheltering is done. the food, milk, and water supply are contained. Now, with pregnant patients, ideally they should only receive 1 dose unless they can't avoid the risk. And then that's a different situation. With Chernobyl, and my apologies, it's not spelled Chernobyl, but hopefully no one's offended by that. So Chernobyl, 200-fold increase. Why? It wasn't even admitted for days that there was an accident. There wasn't adequate supply of food, milk, water, there wasn't control of the supplies of those things. And they didn't have KI. Japan, they did the right stuff best they could. Here they had 2 historic disasters, but yet they've been screening more. They still are. These are a little bit older, but they're still doing screening. They're doing an excellent population monitoring program. If you want to learn anything about population monitoring, look to the Japanese and Fukushima. They have found a little bit more thyroid cancer, but they're screening more. It hasn't been significant, statistically significant. It's because they're screening more. We don't routinely screen for that. Side effects, yeah, there can be some. And I hate to, say over 40 would count as elderly in this situation, but over 40, that's when you're going to start seeing some of this stuff. A whole bunch of different issues there. There are a lot of and KI is FDA approved as an over-the-counter for internal contamination. There are other non-FDA approved uses. We're not going to go into those. You could probably figure them out. Things that block the thyroid are things that you could use, but they're off-label uses. Neonates are a special category for many reasons, but particularly with KI, they can have intellectual development deficiencies profoundly. You must do thyroid function test if you've got neonates. Isotopic dilution. Dylan talked to you about this. Tritium. Tritium's water, right? It's tritiated water. So it's going to do just like water. So you can flush it out just like water. I like to not say force fluids, but to increase fluids. Now, some people would consider that forcing to drink 4 liters a day, but hydrate to get the excretion going. Also, if it's on skin, wash off the skin. Alter the chemistry. We're cruising through now. So here's another memory tool that we'll talk about here in just a second. I think I got 5 minutes, but we're in the home stretch. So with uranium, and here's an age-old debate, at greater than 18% enrichment, it would be radiological issues versus the chemical. Well, we all know it's still the chemical issue as well. It's the metal issue. However, at greater enrichment, we can have that radiological toxicity to the kidneys. So this is, again, where we share with our counterparts, our toxicology friends, that the importance of this, and here is a real basic way to remember what to do for uranium. When you're dealing with uranium, think of urine, and the basic way to treat it is to make the urine basic. So alkalinize the urine. You all know how to do this. You can do it, IV, you can do it oral. It really doesn't matter. You just want to avoid the nephrotoxicity. Keep in mind too, to do renal function test, beta-2 microglobulin, things like that. And here we go. So you can do this orally. Dr. Goins has experimented on himself with his sodium bicarbonate tablets, and he does a test that this will work. Actually, there's a lot more evidence than just Dr. Goins. But you can also, you can do IV sodium bicarb. It's up to you. This is not FDA approved, but it is NCRP 161 recommended. Yes, you could do diuretics. Yes, you could do dialysis. Displaced from receptors. Oh boy, this is where it gets really interesting too. Strontium and radium therapies. Outside of the radium dial painters, we've had very few radium calls. And one fairly recently that some of you on this call are probably very familiar with. There are numerous non-FDA approved therapies for radium and or strontium. We generally don't have to worry about these, even with strontium being a fresh fission product. We have had maybe one case, maybe a couple of cases, and it wasn't clinically significant, and that is over 50 years. And actually the data goes back even further. The data is 78 years, I guess. So this would be a rare thing, but if you wanted to treat, there are lots of ways to do this. You can do blocking agents to keep it from being absorbed. I will caution and say only if it's really significant to think about barium sulfate, because I personally have had 2 upper barium studies, and I've prescribed lower ones, and I have seen what that does. You can also have diluting agents after the fact. As you can see, these are pretty benign types of treatments. I would go with certainly some that are absolutely benign, or you can't say absolutely, but mostly benign, versus some of the others which may have some issues like calcium gluconate. Chelation. Hey, now all the people are happy now. The reason this is here is that REACTS through DOE had the IND, investigational new drug status, for DTPA, both salt forms, and radiogardase. And we held registries for these once they became new drug approval. They then became prescription medications. We no longer could maintain a stockpile of them and just send out these medications to other sites, signing on the treating healthcare provider as a co-PI. So once these got their FDA status, it squelched us being a stockpile. So now you can look to the Strategic National Stockpile. They're only going to have zinc, DTPA. They will have some radiogardase. They are not going to open up that stockpile for small events, 1, 2, 3, 5, maybe 10. I don't know what their limit would be, but it would take a whole lot of individuals. We have on our website, our app, and maybe even in Megan's lecture coming up, some ways on how to get this. And also I put a link into the chat that has the resources that has how to get this. What we recommend is that toxicologist, work with your state departments of health, work with your healthcare coalitions, and have a small amount set aside outside of the actual push pack that can be accessed, just like you do with antivenom. So treat it just like that. It isn't expensive, it's cheap. There is an issue with production of DTPA at the moment. We'll talk about that as we go. All right, so another stupid memory tool. I'm showing you the name. Don't worry about the rest of this right now. So DTPA, diethylene triamine pentaacetate. That is what DTPA stands for. Let me go back up. Think of this: drug, treatment, plutonium, americium will cure you. So DTPA, plutonium, americium, curium. It can be used off-label for a lot of other nuclides. You can consult so many things, NCRP. You can consult our website, app, et cetera, for exhaustive list of these. Just know it's off-label uses. It's important to give these rapidly. Ideally, it'd be great if you could give it within 2 hours if it's a soluble compound, because it's going to get into the bone and it's going to stay there. And it can do that as rapidly as 2 hours. Now, as quickly as reasonably possible is also good. That's a good answer as well. The liver is the other place where this is going to end up depositing. We have, and I don't have my statistics on the top of my tongue right now, but we have data of use of DTPA since the 1950s. As far as significant adverse reactions, none in all of that data for the US. The French have not, the Japanese have not. We have had more in more recent years, maybe some adverse reactions that might involve some of the newer medications that individuals are on, and certainly the psychological aspects. That is a big thing that has to be addressed and dealt with and follow up. Don't just leave these patients hanging. Make sure they have long-term follow-up and ways to get in touch with mental health professionals. Your first dose, ideally, is calcium. It is such a good chelator that it can deplete the zinc, magnesium, manganese. I haven't actually seen that, and you can certainly supplement even with, over-the-counter supplements. However you want to do it, you can supplement. The one thing I would say probably not use it to the calcium would probably be pregnancy. Let me show you on this one. Actually, I think I've got another slide after this. The dosing of this, 1 gram IV, unless it's an inhalation. If it's an inhalation, use a nebulizer, and it's just a 1-to-1 dilution. Asthmatics, there have been a few, I think 3 documented cases where asthmatics had shortness of breath, trouble breathing, didn't cause any asthmaticus or anything like that that I'm aware of. But there is some documentation out there. So caution with asthma. And then you can do slow IV push. If you have lots of repeated treatments that must be given, put in a hep lock. Don't re-stick the person every time. That was one of the cases that had the adverse reactions because they were getting stuck literally every day and so on. I won't digress any more on that. With pregnancy, these studies to evaluate carcinogenesis, mutagenesis, the mutagenesis, I'm pretty certain were just the rodent studies, and in fact, mice. The fertility in canines, beagles, but for all of these, this has not been shown in humans. That being said, there is a risk of contamination with the fetus, but you can use zinc DTPA, which is certainly considered safer. So it's going to be a doctor-patient decision. It's going to be a clinical judgment decision. So these are just considerations. There is no labeled contraindication for use of DTPA. Now, the good news is there is another agent, HOPOs. I always get the numbers mixed. I think it's the 14-1 HOPO, and I'm not going to say it. It's hard to say. But it is in phase 1 clinical trials, and it would be an oral administration, better efficacy. Still has a few years to go, unless maybe it got EUA approval, but I'm surmising there. I don't know anything on that. As far as impaired renal function, it's just because they're not going to excrete as rapidly. So the consideration is get those individuals excreting more rapidly, whether it's diuresis or what have you. So The other consideration for DTPA, wound irrigation. Now, I'm not going to say a country. Some of the countries will use this as a treatment dose. I recently heard a report that was, hey, using this to irrigate the wound really did a great job in decontaminating the skin. Yeah, hey, what a neat trick. We don't consider this, using a DTPA for irrigation, we don't consider this a treatment dose because it's not, I can't give you a number of what percentage is absorbed. For us, we don't feel comfortable with using that as a treatment dose. All righty. Excise radionuclides from wounds. I was kind of alluding to this before. So this is good for alpha emitters. You can use the DTPA for irrigation, use it for chelation, but in some situations, it may be helpful to do small excisions, tiny punch biopsies. And I'm going to the next slide. Consider surgical consultation, particularly a hand surgeon. These are often hand injuries. They're usually occupational injuries. The reason I say that is because there was a series of a few cases that had less than optimal outcomes with their excisions. So be smart. There's a good publication. Steve Sugarman's the primary author on it. Health Physics Journal. It's a Savannah River site case. Feel free to look that one up. It's a great case on how to deal with an alpha emitter. Bronchoalveolar lavage, not British anti-loose site. This can be done. It can be done. You have to have a very large burden to consider this. I mean, sure, we do BALs. Yeah, sure, we're safer than we used to be. Sure. Huge burden, huge burden. So think about that. This, and I really need to clarify this, the last thing 30 years ago was a review of the literature. It wasn't new literature, it was a review of the literature. So don't make that your default. We can't really do the review, and I didn't put in my polling questions, my apologies. So we could go to questions. I'll try to find the questions again. Or if you guys want to read them to me, here we go. I think I just maybe found them. Anybody want to read them to me, if there are any? Or have we just exhausted everyone? Q&A. Oh, there are some. Okay, I got them. Does handling blood and urine samples from internally contaminated personnel for investigation give dose to medical personnel? If so, what are the safety precautions? Great question. Great question. I am going to use this example because I think this will be maybe most reassuring. And then Megan and Dylan are certainly welcome to pile on to it. During Guyana, again, I was talking about these individuals sweating out contaminated sweat with cesium. If someone's telling me it's time. Oh, answer that in the chat. Yeah, you know what? Can everybody see the answers? No, I'll put it in the chat. Never mind. I got it. We will do this. We will absolutely get you guys set up with this. Just some references. Take a picture if you need to, or else it'll be in the video later. Thank you all. Let me let Megan get started. My apologies, Megan. And thank you for that ping. It's going again. All right, let me stop sharing. Thank you, Megan. Thank you, Michael. Thank you, panel. Thank you, audience.
Thank you, Carol. All right. So, my screen. All right. So I think for this lecture, I'll start with doing a presentation, and then if we have time, kind of based on the time, there's a 30-minute video that we made kind of demonstrating how do you decon a patient. And it kind of nicely shows what we would do if you were at a course with us in Oak Ridge, how we wash out wounds and don and doff. So if we have time for that, we'll watch that as well. So again, I have no financial interest in this lecture. So the objectives of this lecture are to describe the use of personal protective equipment, or PPE, discuss when PPE does not protect from ionizing radiation. So like I talked about earlier, alphas are blocked by paper, betas are blocked by plastic. But if in the case of gammas or X-rays or even neutrons, you're going to have to think about different ways of protecting yourself besides just PPE. And then lastly, describe situations in which respiratory protection should be employed. So that kind of goes back to the question that we had earlier after my first lecture. So hopefully that answers your question once we reach that. This is an example of PPE that we use here at REACS. It's just things that you can find in a hospital. A normal face mask, latex gloves, a Tyvek suit, a face shield, hairnet, booties, tape, things like that can be used to treat patients that have been contaminated with radiation. And again, going into the nuances of contamination versus irradiation, if you have an irradiated patient, you definitely don't have to take as many PPE precautions as you would with a contaminated patient. The one thing to note with an irradiated patient is that their immune system might have been affected. So in that case, you dress in PPE more to protect them from you than you from them. Some important things to note when choosing your PPE is to make sure that it's functional while doing medical procedures. So if you're investigating a wound, or if you're taking nasal swabs, or if, whatever you may be doing with that patient, you have to still have that dexterity of your hands. You still have to be mobile, able to see them. When we think about shielding, you could protect yourself from gamma rays if you had a 30-foot lead wall between you and the patient, but that's not really practical when working with a patient. So really just trying to mitigate contamination getting on yourself is really the main goal of PPE. You also want to watch for heat-related issues. When we do our drills here, we're dressed out in Tyvek with the gloves and booties and face mask and everything. And we're in PPE for about an hour to an hour and a half. And even at that point, people are sweating profusely. And, the first thing you do when you get out is go get a drink of water. That's just from that short amount of time. So if you're in PPE for, 3, 4, 5 hours, that's going to get exhausting. So watch yourself and watch your coworkers for heat-related issues. PPE can also be de-escalated when the risk is determined. So if you have a patient come in and they say, I think I've been contaminated with radiation, you're going to dress out in full PPE. And then later on, if you determine that, no, they weren't contaminated, they were only exposed, then you can start to de-escalate the PPE that you have on to kind of fit the situation. The same thing would go if you had a respirator. If your patient came in thinking that they were contaminated with something that was aerosolized, or you think you're going into an area where there has been some sort of aerosolization of radioactive material, you wear something like a PAPR. And then later on, if you determine that's not the case, then take off that PAPR and save yourself from that issue. Like I keep harping on, normal PPE doesn't protect from penetrating ionizing radiation. It will protect from alphas. It'll protect from low energy betas. But if your patient is contaminated with gammas or neutrons, then any sort of PPE really is not going to protect you. So think more about that time and distance aspect of shielding, and use your PPE more as a way to keep contamination from getting on you. It's not protecting you from the radiation, but it's just protecting you from contamination. Lastly, if the patient's only exposed, you want to think about protecting the patient's immune system versus really protecting yourself from any rad hazard, because there will be none if they were only exposed. Emily briefly touched on this during her lecture. I'm going to go through how we don and doff at REACS, and everyone has their own way. I just really want to emphasize this is our way. So if your facility doesn't have a donning procedure, or you're looking to maybe adopt a new one and update yours, this is great. We have all of these PDFs, pictures of donning and doffing procedures. They're available on the app and on the website, and you can print them and post them in your facility. But again, This is just our way. There's hundreds of different ways to do it. So the first thing you do when you're going into a contamination situation is put on your Tyvek suit and your shoe covers. So one of the most likely things to get contaminated is your feet, because you're going to walk in that contamination. So put on your shoe covers and then put on your Tyvek suit. And again, it doesn't have to be Tyvek, just a kind of a general suit to keep the contamination off your clothes. And then the next thing you want to do is put on your first set of gloves. So we like to have people wear 2 sets of gloves, typically different colors if possible. And again, if your facility only has one color, totally fine. But we like to say that two sets of gloves that are each a different color is great, because if you get a tear in your outer layer of glove, it's really obvious because you'll see another color poking through that. Also, if you take off your second layer of gloves and forget to put on a new second set of gloves, your glove color will be different than everyone else's. So it will be obvious that you haven't put on that second set again. So we say, put on your first set of gloves and stick the cuff of the glove underneath the cuff of the Tyvek. And this creates a nice seam so that the radiation can't get kind of like into the glove and onto your hand. Then you want to tape all of your cuffs, so on your hands and on your ankles, and then also your zipper on the Tyvek. Oh, and also some Tyveks have hoods. The ones that we use don't, but again, if you have a hood, then you want to kind of tape the seam of the hood onto the Tyvek as well. We also like to use what's called a buddy tab. So if you have your strip of tape, fold one end of the tape over onto itself, so that it's not sticky, and then have that on top of whatever tape you have. So that way, when you're doffing, you can just pull that tab, and it's much easier than trying to pick at the edge of a tape when you're hot and sweaty and you just want to get out of Tyvek. So your coworkers will thank you for buddy tabs. Next, you want to do a head cover. This is like a lunch lady hairnet, just to keep your hair out of your face and out of the contamination. Then a face mask. And the face mask that you choose will depend on if you are concerned about a volatile or aerosolized radionuclide. When we teach here, the radionuclide that we use is not volatile, so just a standard surgical mask is perfect, or an N95 or something like that. Then we use a plastic face shield, and this can prevent splatter from getting on your face. There's one time we were teaching and I wasn't irrigating the wound. I was standing a couple feet away from the patient, and the water they were using to wash the wound actually splashed me in the face. But we took a survey meter and surveyed it, and it was just clean water. It wasn't contaminated. But that just emphasizes the need that you need to wear a face shield. Even if you're not treating the patients, it's always a good idea to have more PPE than less. Then, like I said, the second set of gloves. And this second set of gloves is meant to protect the patient. So you don't tape down the second set of gloves. You can switch them out if they get contaminated or if they get a hole in them. Anytime that you feel like they can get contaminated, either change them or have a health physicist come and scan them. And if they are contaminated, then just get a new set. So yeah, don't tape these because they'll be switched out a lot. Next, you'd want to put identifying information on the Tyvek of each individual. Once everyone's in Tyvek, you all look like giant white marshmallows. So it's really hard to tell people just based on their eyes what their role is and who they are. Even if you've been working together for years, it still is really difficult. So normally we like to write the last name of the person and then also their role. So HP, nurse, doc, scribe, whatever it may be. And then the last thing you need is a dosimeter. Dylan talked a lot about different types of dosimetry that you may encounter. Here we have images of an EPD, so the electronic personal dosimeter. These are kind of nice because you can set them to a certain dose rate alarm. And so if you are standing near a patient and are receiving a certain dose rate, the dosimeter will start to alarm. So that gives you an auditory cue to back up away from the patient. And then, by increasing your distance, you decrease your dose. It's also important to note that if you have an EPD, you can put it in a plastic bag and then tape that onto your Tyvek. So that way the dosimeter doesn't get contaminated, because if it's contaminated, then it will only read that there's radiation in the area. And plastic bags are a lot easier to clean. So that's just one caveat with that image. And then the other image is just a standard pencil dosimeter. So with doffing PPE, again, this is the REACT's way. It's not everyone's way, and that's totally fine. This is just what we like to do at our facility. And feel free to download and print these images of the posters. So the first thing that you're doing when you're doffing PPE is remove the most likely contaminated thing, which is your gloves. So take off your outer set of gloves, but leave the inside ones on. The next thing you want to do is remove the tape. And this is when you'll thank yourself for making those buddy tabs. So remove the tape from your hands and your feet and your zipper. Next, you'll want to remove your head and face covering. And the best way to do that is when you take it off, I don't know if you can see me, lean over the trash can and then just drop that directly into the trash can. That way, if there's any contamination on it, it's not falling into your nose and mouth. Also, when you're doffing, if you put something in the trash, don't like shove it down and force all the air out of it to compact the trash, because that will just make all the radiation come back up, and then you're breathing it in, and then now you can be a contaminated patient. So just drop it in gently as you can. And make sure that this trash is marked as radioactive. So that way it doesn't go out with the normal trash, because there's a good chance that something in there will be contaminated. Next, you want to remove your coveralls. This is one of the hardest parts of doffing, just because it's kind of awkward, because you want clean touching clean. So your inner gloves should be clean and the inside of your Tyvek should be clean. So you want to grab the inside of your Tyvek with your gloves. The hardest part really is getting it over your shoulders, because it's just a very awkward motion. But if you have someone in the room to help you pull it down, that's always a nice option. But kind of shimmy it down over your shoulders. And then once it's off your arms, you can kind of roll the Tyvek up to trap any sort of contamination in the Tyvek itself. And then if you have a chair available, sometimes that can be really helpful with doffing. And we get mixed reactions about having chairs available for doffing. If the chair is a hard surface, so something like plastic that can be easily cleaned, or if you can throw a trash bag over it, that having the chair there is kind of nice, just to prevent any fall hazards. So if you're getting out of Tyvek and you're hot and sweaty, you are kind of more of a fall hazard. So it's always kind of nice for stability. Yeah, so you want to roll your coveralls and then again, gently place them into the trash can. Next, you want to remove your mask, and much like the head and face covering, you'll lean over the trash can while you're doing this and just grab the mask by the straps and just drop it in. And then shoe covers. This is kind of notoriously the most difficult one, just because it's kind of a strange doffing procedure. But when you're taking off your shoe covers, if you want to sit in the chair or stand or however your facility likes you to do it, have one foot closer to the exit than the other. And typically at the exit of the contamination room, there will be a step-off pad. And this is just kind of a sticky pad that will trap any sort of contamination that might be on the shoe so that you don't track it all over your facility. So with the foot that's closest to the step-off pad, go ahead and take off that shoe cover and leave your foot up in the air. And then your health physicist or RSO or whoever it may be with a meter will come and scan the bottom of your foot to make sure that nothing got through the shoe cover. Once they've scanned your foot, then put that foot down on the step-off pad. Then do the same thing with the other foot. Take off the shoe cover, have the bottom of your foot scanned, then step it down. And you always want to have the first foot be the one that's closest to the step-off pad, because we have some people, if they're sitting, they're like trying to play Twister because they did the wrong foot and now you're all tangled up, and it's just a lot harder to stand up once you're in that position. So that's really the hardest part of doffing. Lastly, you have your inner gloves, and ideally the inner gloves are still clean, but always treat them as dirty. So if you can grab the cuff of each glove with your finger still in the glove of the other. This is really hard to do. I should have brought gloves down here. You kind of want to bring the gloves into each other and trap any contamination on the outside inside the gloves, if that makes sense. So like that image, grab it at the cuff, but do it with both hands, and then drop that into the trash can. And once that's all done, you want to survey. And this is really frustrating when you're hot and sweaty, you just want to get a drink of water and go to the bathroom. Because personnel surveys can take between like 5 and 8 minutes, depending on the person that they're surveying and the person that's doing it. But it is honestly the most important process or step of this process, because if at any point you did get contamination on you, the survey should find it, and then that will allow you to wash off that contamination or change the clothing that's contaminated or whatever the case may be. So when doing a personnel survey, if ideally there's no wounds on your treating staff. So you start with the body orifices, so eyes, ears, mouth, and nose. Next, you want to survey the hands. And then lastly, methodically go down the body, starting head to foot, including arms and legs. You want to go at a speed of about 2 to 3 inches per second and be about 1 to 2 inches above the person's body. So this is why it takes so long. And then once you do the front of the person, have them turn around and do the exact same thing again. If you come to our on-site courses, you get to practice all of this. It is super fun, and I think it's good to do at least once if you haven't done it before. And Emily already went over how we treat patients that have been contaminated, and she did an amazing job, so I don't want to steal any of her thunder. So I do have a video, if we have time. Carol, is that all right with you?
How long? I think it's a 27-minute video. Sorry, I was
Yes.
typing and not listening.
Oh, no, sorry, you're fine.
Yeah, I think we have time. We're supposed to finish up at 5:10. Yeah, you go. You got it.
Okay.
And if people have to drop off a little early, we understand, but it is a good video. Highly recommend you watch it, and you might pick up something from it. But if not, thanks, and
yeah,
let it roll.
All right, pull it up. Let's see. So I just want to make sure that I have the share sound. Here we go. Okay, perfect. And once it starts playing, someone can let me know if you can hear it.
All good.
You can. Can you hear the video?
In a radiological incident,
Yes.
many medical providers are concerned about bringing a radiologically contaminated patient into their facility, often due to fears about personal safety or the incorrect belief that the treatment area will have to be closed afterwards. As you will see in this decontamination demonstration, simple steps can be used to limit contamination spread while treating a radiologically contaminated patient. By implementing good contamination control techniques and proper personal protective equipment use, patient care can be accomplished with mitigation of risk to the caregivers. Most radiation-related incidents bring little risk to those providing patient care. When compared to caring for some chemically contaminated patients, in radiological incidents, the key is that life-saving interventions take precedence over decontamination. Radiation-related injuries and illnesses rarely present with immediate signs and symptoms, and restricting a patient from access to critical medical and trauma care because of radiological concerns can lead to poor patient outcomes. To start, let's consider room setup from a medical treatment standpoint and with an eye to radiological contamination potential. If time permits, the emergency treatment area can be prepared before the arrival of the patient by designating an area of controlled access. Non-critical equipment can be removed or covered so that there is less likelihood of contamination spread. Ideally, The facility would have sinks and floor drains collect in holding tanks prior to discharge to the sewer system to mitigate contamination. Floor coverings are optional. Floor coverings like heavy paper can help providers see where materials have been spilled, areas to avoid, and may aid in the room cleanup and decontamination process. But putting down floor coverings takes time, so do not delay patient care just to cover the floor. Plastic floor coverings should be avoided because they become a slip-fall hazard when wet with body fluids or water used for decontamination. Extra sheets, at least 3, can be placed on the bed to facilitate ease of decontamination efforts and to provide a clean surface for the patient to lie on as decontamination progresses. Only necessary personnel should be allowed in the controlled area, but a minimum number of staff should be present to ensure good patient care. Additional staff can be staged outside the controlled area in a ready state to assist with patient care or additional patients as needed. Access to the controlled area should be through a designated entrance and a controlled area well marked. This can be accomplished in many ways, including doorways, tape, cordons, or cones. Controlling access to the treatment area at the boundary or control line helps limit the potential for contamination spread. Control line personnel should establish the controlled area, post signage as required, and gather supplies. Preparation at the control line is an important part of the overall process that enables a lot of tasks to be performed while limiting cross-contamination. For example, patient registration is often a task that can be accomplished from outside the controlled area. In some facilities, medical documentation can also take place outside the controlled area depending on the area's setup and local protocols. In addition to access control line personnel can assist with sample processing and tracking, facilitate communications, provide a conduit for additional supplies, help manage waste by limiting the radiological material in the area, and, once the patient is transferred, survey personnel exiting the controlled area. In this demonstration, a lot of these tasks will be performed by a single person, but in reality, it may take several people to accomplish. If you work in a medical setting that provides emergency care, you already know what you need to do to set up for patient arrival. This video will focus on equipment and supplies that may be needed in a radiological incident. Personal protective equipment, or PPE, should be readily available, and personnel should be skilled in its use. If caring for a patient who has only been exposed to radiation, no radiological risk exists for the caregivers. In this instance, the patient is not contaminated, so only standard universal precautions are needed. In this video, the team members are wearing various examples of PPE that may be readily obtained in a medical environment and that provide sufficient protection from radiological contamination. The key is to keep contamination off the provider by covering the body and protecting the airway. Pre-hospital and hospital staff may be trained with different types of PPE than that worn in industrial or research settings. Use what you have. If it protects you from biological materials, it will also protect you from radiological materials. Calibrated radiation detection instruments should be available and accessible. If health physics or radiation safety expertise is not readily available, medical personnel should be trained on the use of survey instruments in the emergency setting. The simple pancake probe used for radiological contamination surveys is an extremely versatile instrument. Prior to using, the instrument should be checked for damage, batteries should be tested, the instrument's calibration date recorded, a response check performed, and a background reading with units documented. Just as with medical documentation recording radiological instrument setup is an important step. Additionally, personnel should understand the approach your facility is using to track external dose. If using personal dosimeters, personnel should be trained on their use prior to an incident. It is important to practice the integration of radiological surveys with the medical treatment team so medical and radiological tasks can be accomplished concurrently. The radiological survey process will be used to locate contamination, identify the magnitude of the contamination, determine the type of radiation, reassess contamination after decontamination, and perform final surveys prior to release from the controlled area. Most of the time, radionuclide identification is not possible in real time, but it is important to identify the material as soon as practical. Remember that radiological surveys should not interfere with life-saving interventions. Detailed radiological surveys of the patient should be delayed until the patient is medically stable. The following demonstration deals with a single patient and may not be applicable in a multi- or mass casualty incident. As this demonstration progresses, remember, as with any medical assessment or set of interventions, and depending on the number of caregivers available, many steps in this process may happen simultaneously. Life-saving interventions should take priority over clothing removal and patient decontamination. Life-threatening issues with the patient's airway, breathing, and circulation should always be addressed first. This demonstration will follow the radiation patient treatment algorithm available on the REACT's website. As radiological incidents are infrequent events, this algorithm is a useful tool to help remember the steps involved with treating a patient in a radiation incident. As you can see at the top, patient stabilization is paramount, and a history is important in order to determine which pathway to follow. This demonstration deals with care of a contaminated patient, so it will focus on the contamination pathway on the left side of the algorithm. For purposes of this demonstration, pre-hospital patient transport has taken place either via ground or air. The patient arrives cocooned in a sheet to contain radiological contamination and help prevent cross-contamination, and the patient is admitted to the radiological control area. Before clothing removal and other interventions begin, ensure wounds are covered with a dressing and the patient's airway is protected from contaminants that may become airborne during clothing removal. An inverted face shield or mask, if needed for oxygenation, works well for this purpose. Early external contamination control helps prevent internal contamination. Removing a patient's clothing will help remove a large amount of contamination. Clothing removal should be done in a controlled fashion to minimize the spread of contamination. If the patient is wearing any, shoes should be removed in a controlled manner. Shoes should be placed in a bag using a method that protects the hands of the provider. The bag should then be sealed. The shoes can be bagged along with other clothing once removed. Clothes should be cut in a head-to-toe direction, moving away from the patient's airway. An even, controlled method should be used to remove the remaining clothing. The outer surface of the clothing should be rolled away from the patient's skin to contain any contamination. Once the clothing has been cut and rolled away from the patient's body, log roll the patient and fold the sheet in a manner to contain the clothing. Log roll the patient in the opposite direction and repeat the process. Roll the folded sheet from the head of the bed to the foot of the bed, capturing the contaminated clothing, and place it in a bag to be removed from the controlled area. Rolling this material from head to toe helps to keep any trapped contaminant away from the patient's airway. When the second log roll occurs, this is a good time to do a trauma survey, along with a rapid radiological survey of the patient's back. If patient acuity allows, this is a good time to change gloves before touching the patient's bare skin. The patient should now be lying on a clean surface. Contaminated clothing and linen should be bagged, sealed, labeled with pertinent patient data, content information, and double bagged at the control line. The outer bag should then be labeled again and placed in a pre-designated area for appropriate disposal, or, if significantly contaminated, may be used for isotope identification. This same procedure of labeling and double bagging should occur for any item, such as labs, that go out of the controlled area through the control line. Further medical assessment and interventions can now occur. Some caregivers worry about starting an IV through potentially contaminated skin. Do what is medically necessary, but also remember that as the IV site will be cleaned thoroughly via standard procedure prior to cannulation, the concern about contamination at the site is minimal. Labs can be drawn when IVs are started so that the lab personnel do not have to enter the room. Other interventions, such as pain management, should be done as with any emergency patient. Many other diagnostic procedures can be done at the control line. For instance, the patient can be taken to the control line on a stretcher, and x-rays can be obtained without the radiology technician or the equipment having to come in the room. If the contaminated patient must be taken to another area for diagnostics or care, such as CT or surgery, the contamination can be contained by cocooning the patient in sheets or fixing the contamination in place. If the radiation type, alpha, beta, or gamma, has not already been determined, this is the time to do so. Knowing the radiation type helps in understanding the magnitude of the hazard to the patient and the caregivers and informs any additional protective actions that may be needed, such as more robust respiratory protection. Use any available data or contaminated samples, such as clothing or wound dressings, to identify the radionuclide. Depending on the situation, the patient may be able to tell medical providers what they were working with, or similar information may be available from the pre-hospital report. If the contaminant is not an alpha emitter, the survey probe may be covered with a glove or other occlusive material to prevent contaminating it. This helps keep radiological and biological materials off the probe. If using this technique, ensure the fingers of the glove are not hanging loose to spread contamination. It is essential that the medical and survey personnel communicate about patient status and determine if the patient is stable enough for a more thorough radiological survey to take place at this juncture. When the survey process can continue, survey the patient's whole body and document, prioritizing wounds, body orifices, and then intact skin. This is the priority order that will be used for decontamination also. For beta and gamma emitters, it may be necessary to move limbs away from the torso while surveying to avoid interference with readings and contamination from other areas influencing the survey results. Thorough documentation of radiological counts with units cannot be overemphasized. Remember that this survey process may be interrupted as needed for medical care. This process is always subject to missing areas and will later require a detailed, focused radiological survey before patient discharge out of the controlled area. If samples have not already been obtained, now is the time to collect nasal swabs, as well as swabs of the mouth as needed. Any material in the mouth will be cleared very quickly and, if found, may indicate a significant ingestion. For nasal swabs, a different swab should be used for the left and right nares. The swab should be surveyed in the controlled area, results documented, and then sent for further evaluation as needed. Even if the swabs have no counts above background, they should be considered a pertinent negative and stored appropriately until they can be sent for further testing or confirmation is received that they are no longer needed. Remember that if the contaminant is an alpha emitter, counts may need to be retaken after allowing the swabs to dry because of shielding that occurs by mucus, saliva, or other body fluids. Dose magnitude estimation based on the nasal swabs is highly inaccurate, but can provide magnitudes of potential intake and may serve as indicators for further evaluation. Once the patient is medically stable, decontamination can begin. To reiterate, decontamination efforts should be prioritized to wounds, body orifices, and intact skin. By doing so, the medical provider is addressing the areas where contaminant is most likely to become internalized, with intact skin last because it provides a reasonably effective barrier against most types of radiological contaminants. If it is suspected that internal contamination has occurred, for instance, significant counts are measured in a wound or body orifices, the healthcare provider should consider if administration of countermeasures is needed. If this is believed to be the case, interaction with health physics resources to determine next best actions is advisable at this time. Always stop decontamination if it interferes with medical treatment or the patient becomes unstable. When considering the overall decontamination process, remember that simple procedures may be sufficient to remove the contaminant. During wound decontamination, remember it may be difficult to detect alpha or weak beta particles in a wound because of the shielding provided by body fluids. Not all radionuclides carry the same risk when internalized. Intakes of alpha emitters typically carry a higher risk, and wound decontamination intensity may vary depending on the radionuclide. Wound decontamination can be accomplished by utilizing many of the same techniques used when cleaning or irrigating any wound. During decontamination efforts, controlling the movement of the radioactive material is the goal, and any material removed should be contained as much as possible. In preparation for wound irrigation, with a medically stable patient and with time permitting, place an absorbent pad underneath the area and then drape the area with waterproof drapes. taping the edges can also help prevent irrigation fluid from getting under the drapes. Absorbent pads, such as ABD pads, are used to catch irrigation fluid, and a trash receptacle is placed to catch runoff from the decontamination effort. Standard wound care procedures should be used, including anesthetics and exploration of the wound for foreign bodies. Control of bleeding and wound management may require surgery or emergent closure of the wound before decontamination is complete. Just like with reassessment after any medical intervention or medication administration, reassessment should occur after each decontamination effort. As you see here, a 4x4 is used to dry the wound by blotting the area one time and discarding. Do not wipe or repeatedly pat the area with the 4x4, as this may lead to cross-contamination. The wound should then be covered. The draping around the wound should be removed, the wound area placed on a clean surface, and a repeat survey completed. Make sure that consistency in measurement distance is maintained. Compare the readings to determine the effectiveness of the decontamination effort and next steps. Remember that many decontamination efforts may have to be repeated multiple times to achieve the desired result. Repeat decontamination steps until the contamination level is at most 2 to 3 times background. There are no changes in readings after multiple decontamination efforts, or the medical status changes and requires action. If the contamination readings are not lowered to background, consult with health physics to determine additional actions. Some wounds, such as punctures with alpha emitters, may be particularly difficult to survey and decontaminate. Expert consultation is advised in these instances. These types of decisions require clear communication between medical and health physics personnel to determine the best approach for the best patient outcomes. If contamination is detected around the eyes, nose, or mouth, careful techniques should be used to avoid further potential inhalation or ingestion of the material. If the patient is able, allow them to blow their nose to expel contamination. REACS does not recommend nasal lavage, as this could further distribute the contamination into the nasal and oral passages and the airway. If contamination is present in the eyes, standard eye irrigation techniques can be used. As with wound decontamination, containment of the irrigation fluid helps prevent cross-contamination. Using absorbent pads or a basin to catch this runoff before it reaches other areas of the patient's body is recommended. When decontaminating intact skin, simple methods may be best. Pre-moistened wipes may be used to pick up contamination off the skin using a grasping motion. Avoid wiping back and forth, as this can spread the contamination to other areas. Start from the outer perimeter of contamination and move towards the center. In this example, a drape is used to help control runoff, and a commercially available pre-moistened cleansing pad is used. When decontaminating intact skin, a primary rule is to be sure not to damage the skin integrity. Abrasive cleansers or materials should not be used. Do not shave hair, because shaving can cause microabrasions that allow an entry point into the body for contamination. For the same reason, avoid vigorously scrubbing the skin. Efforts should be discontinued if the skin becomes abraded. Consider stopping intact skin decontamination efforts when counts return to 2 to 3 times background, or contamination counts are not dropping despite repeated efforts. If the latter is the case, discuss with health physics personnel other methods to remove the contaminant, such as dressing the area and letting the body's natural sweating process help remove the contaminant. If medical concerns necessitate immediate interventions, contamination on intact skin can be fixed in place with an occlusive dressing to mitigate its spread until it can be addressed. Remember, decontamination is dependent on the chemistry of the material and does not require special cleaners. As an example, if the material is greasy, a cleanser that cuts grease will be effective. Once decontamination is complete, either because the counts are in an acceptable range or the counts are as low as can be achieved with current efforts, the patient is ready to be discharged from the treatment area, and a final whole-body survey must be conducted. At this point, survey techniques should be slow and methodical. The radiological survey process, conducted at 1 to 2 inches per second, 1/2 inch from the surface, is important so that no radiological contamination leaves the controlled area. If the patient is going to another hospital area, such as surgery or an inpatient floor, information regarding the radiological status of the patient must be conveyed to the receiving staff along with the standard medical report. If staffing allows, the person who has been functioning in the radiological survey role may go with the patient to the next treatment area so that they can provide more details or an observable illustration of the patient's contamination status. If the patient is being discharged home, they need to have a clear understanding of their follow-up instructions. These might include side effects of any countermeasures and signs and symptoms that would warrant follow-up care. If bioassays are being collected, the patient should be given appropriate collection containers and instructions on how to collect them and where to return them. Once care is complete and the patient is discharged out of the controlled area, there should be an organized plan regarding how providers will exit the controlled area. Prioritize who exits first. It may not always be the same. Personnel safety is still important. Does anyone have a medical need to exit? Is anyone overheated? Does a particular caregiver need to exit quickly to care for another patient? When exiting the controlled area, PPE should be removed in a controlled fashion and any personal dosimeters should be collected and read. Remember, there are always exceptions to the rules. If medical acuity of another patient dictates a caregiver leave the controlled area without a thorough survey, then so be it. Medical care of that patient also takes priority. Things like removing shoe covers and gloves before leaving the controlled area and donning a clean lab coat or gown are simple measures that can be used to rapidly exit the room to provide emergent care. In this instance, the controlled area would expand and the survey process would become larger, requiring more area to be surveyed during the recovery phase. Otherwise, those who have been working in the controlled area should be thoroughly surveyed before leaving. Although everyone is often hot and tired and ready to exit the controlled area quickly, a thorough personnel survey is one of the best ways to assure the providers and their families that they are not leaving the area with any radiological contamination on them. Use the advantages that radiation instrumentation provides to reassure personnel. If any contamination is detected on the skin of a medical provider, the same decontamination process and techniques just discussed can be used. When the incident is over, the controlled area needs to be cleaned and surveyed for contamination before being returned to full service. This will be done in consultation with local protocols and authorities. Remember, once again, that patient care takes priority over decontamination in radiological incidents. This means all patient care. If the room has not yet been surveyed, but it is the only place where another emergent patient can be cared for, then it should be used. Simple steps like wiping down or covering high-touch areas, such as bed rails and cabinet handles, will help mitigate the risk. Lastly, it is important to consider that caring for and decontaminating patients who are radiologically contaminated can generate a great deal of waste. A plan should be in place regarding where to store this waste until it can be retrieved by the appropriate entity, be that the industrial setting where the material was being utilized or the investigating law enforcement agency in a terrorism-related or other unlawful event. Again, it is important to emphasize that those who will be helping with the cleanup be educated on contamination control and any potential risks. The decontamination demonstration contained in this video is resource-intensive and intended for an event with a limited number of patients. In multi-casualty or mass casualty events, survey and decontamination techniques may be vastly different out of necessity. In these incidents, life-saving interventions remain a priority. If showers are used for decontamination, make sure that water runoff is kept away from the eyes, ears, nose, and mouth, and that any wounds are covered with an occlusive dressing. These simple measures help mitigate the internalization of radiological material. Remember that symptomatic, exposed patients may not have injuries and contaminated patients may not require emergency medical care. As with other forms of mass casualty decontamination, special considerations including personnel and time will have to be planned for children, the non-ambulatory, and those with access and functional needs. Decontamination may have to be performed for transport devices such as wheelchairs and stretchers, and for assistive devices such as prosthetic limbs or medical support devices. And a plan should be in place to return those assistive devices to the owner. For more information on the medical management of acute ionizing radiation illness and injuries, or for our REACTS course schedule, please visit our website. REACTS may be reached for advice and consultation 24 hours a day, or for general information during normal business hours.
Well, hey there, Megan. Yeah, please come back
Hey.
on camera. And also, Dylan, if you can come back up. Thank you, Megan. That was great.
Yeah, of course. I hope that
Yeah,
was helpful.
we've gone through, Dylan and I have been working the Q&A. The only one we're not quite sure of, but we'll get information back to Dana, is how to get the video. So we'll get that to Dana, get the information back to her for tomorrow. But we are right at time. That was fantastic. You finished right there at the end of it. ACMT, we really appreciate this. Dana, Sarah, Nisha, everybody else that I'm probably skipping, sorry. Our team, of course, thank you guys. And thank you all for sticking with us for an entire day. We really, really appreciate it. And please come visit us in Oak Ridge, or keep an eye out if we're going to be in your area, and sign up to take one of our courses. And don't miss tomorrow. It's going to be another great day. So that's it for REACT. So Dana, whenever you want to close us on out, we'll let you close us on out. Thank you to the REACT panel, Dr. Balaji, Michael, and Dylan. I never saw you come back up, but that's okay. I know you're working. You're helping us out. And Megan, thank you. That was a great job. So, and Emily, I think Emily had to drop off, but thank you, Emily. I don't know if I think she is there, or maybe not. Yeah, she's a busy person. So you'll see more of Emily tomorrow as well. But yeah, thank you. That's all we've got for you. Please visit our website, download that app. All kinds of resources, pretty much everything you've seen today, you can get right off our website. So thanks, guys. We appreciate it. And we'll catch you down the road, and take care of yourselves. Bye-bye.
Thanks so much, Dr. Iddens, and everybody on the REACTS team. We hope you have a great rest of the day, whatever time of day it is where you're at, and we'll see you tomorrow morning at 8:50 Eastern Time for the TICs and TIMs, toxic industrial chemicals, toxic industrial materials, another great full day planned. Thanks so much. If you have any questions, please feel free to write to us at events@acmt.net, and we'll help you out. Thanks so much. Have a good evening.